Почему бы я ничего не слышу? Why do not I hear anything?
Я слышу.
Excellent. Thanks.
Okay, Timur, I think you can start now introducing the speaker.
Okay, so we can start now. Okay, good. And okay, we start in our morning session, at least according to Eastern Daylight Time. And so I'd like to ask speakers to check not only their microphone for everyone can hear them, but also their speakers and headphones. Because in my case, yesterday, my speakers, that was Bluetooth speakers, and they were in energy saving regime. They at some point got disconnected, so I couldn't hear the instructions from chairman of the session. Okay, so and now we start, and the first speaker is Leonid Skripnikov, and he'll tell us about use of heavy atom molecules to search for new physics effects and study of nuclear properties. So Leonid, please.
Okay. Good day, everyone. First of all, I would like to thank the organizers for the opportunity to give a talk at this fantastic workshop. And so let us start. So there will be several topics in my talk, and the first one is the PNC nuclear spin-spin coupling in the thallium fluoride molecule, and this work is made in collaboration with Mikhail Kozlov, Dmitry Butker, David DeMille, and John Blanchard. And Dmitry Butker has already introduced the main points of this proposal, and in these slides I'll show you some theoretical details of this proposal. So we are considering some diatomic molecules such as thallium fluoride, and we consider the following P and C interaction with induced by two nuclear spins, for example, spin of thallium and spin of nuclear. So we consider J Paritinan considering J coupling effect. And it is interesting that almost all we need for this is already in progress in the centric experiment about which Dave DeMille have told yesterday. And so we have two polarized molecule. This is requirement for the experiment. So let us consider the thallium fluoride molecule in the ground singlet sigma plus state. And we can consider, for example, the ground rotational state or first excited rotational state. And we are interested in transition between the singlet state and triplet state, which are induced by nuclear spins of fluorine and from thallium. And this is the Hamiltonian of our system placed in the external electric and magnetic field. And we consider it for two-level system. And what we search for is the interference between the Zeeman transition and the PNC transition. So both interaction can mix this singlet and triplet state, and we consider the interference between these two effects. And this is some scheme of the experiment. Dima has already told about it. So we prepare our system, for example, in the singlet state, and after this system is passing the electric and magnetic field, we measure the occupation of the upper level. And so if we solve the Schrödinger equation for this Hamiltonian, we result in this simple formula for the signal to noise ratio. And here M is the number of molecules, T is the interaction time, and W is the constant that encodes the PNC effect. So it is proportional to the G PNC vector length. And so this is the goal of our theoretical treatment. And to calculate it, we have to perform accurate electronic structure calculation. And in this calculation, we have to include the nuclear spin dependent PNC effects and also the hyperfine interaction. And so we need to calculate this quantity, which can be expressed as XY component of the asymmetric PNC J coupling tensor. And this tensor can be calculated by using this equation. And we suggest that the main part of effects comes from the thallium nuclear spin dependent PNC interactions. And for comparison, we can also calculate the usual J coupling components of J-coupling interaction, which can be measured and which has measured many years ago for the thallium fluoride molecule. And I would like to know that in the one particle Dirac picture, the components of this tensor can be calculated this simple equation, and here n runs over both positive and negative energy states, and the similar classification into the positive and negative energy states contributions can be retained in the many electron case. So let us consider results of the calculations, and you see here the negative energy states contributions and positive energy contributions to the isotropic and anisotropic components of the usual P-conserving indirect nuclear spin-spin coupling in thallium fluoride. So one can see that there are no problems to calculate the negative energy state contribution. But the calculations of the positive energy states contribution is more difficult, because here electronic correlation effects plays important role. For example, when we go from the Dirac-Hartree-Fock value to the density functional theory, we can see that there is a strong contribution of correlation effect. Of course, we do not stop at the density functional theory, and we use the all-electron couple cluster approach, and we include the single, double, and triple cluster amplitudes. And so our final values are given in this line, and they can be compared with the measured components of this J-coupling tensor, and one can see that the agreement is rather good. So, but of course, we are mainly interested in the length of this JPNC vector, which has been calculated in these units. And here, G Tally is constant that characterizes the nuclear anapole moment and other spin-dependent effects. So one can see that in this case, there are also no problems to calculate the negative energy states contribution. However, the positive energy states contribution strongly depends on the electron correlation effect. For example, we start from the Dirac-Hartree-Fock theory, and we get this value. But when we take into account electronic correlation effects, this value drops by a factor of 10. So the final value is given here. So this value can be also compared to the value that can be calculated using a simple analytical formula that has been derived in this paper. And however, one can see that the difference between the between our calculation and simple estimation within this formula is about factor of 3. There is some difference, and we have analyzed this the source of this discrepancy, and it seems that the main point is that in the derivation of this equation, one has suggested that one can replace this denominator for the negative energy states with 2 mc squared. So actually, it seems that in the present case, this approximation is not good. However, in any case, we have considered thallium fluoride molecule, and I think that this formula can be used to, for example, to get some first estimates for some radioactive molecules which contain heavier elements. And what is interesting with this formula is that it also gives the Z dependence of this effect, and one can see that the effect strongly increases with Z. So finally, we can put our numbers to this equation, and we can use for our estimation some parameters of the Centrex experiment. And it seems that in half an hour, it would be possible to accumulate the signal-to-noise ratio of about 100, which seems to be very, it seems to be fantastic. So now I'll move to the next topic. It's about the Schiff moment in molecules with F elements. So this work is done in collaboration with Viktor Flambaum, Anatoly Titov, and Nikolai Mosyagin. So in previous talk, it has been already said that the deformed nuclei such as radium or actinium have a strongly enhanced Schiff moment with respect to spherical nuclei like thallium or mercury. And therefore, we have tried to calculate the possible effect in molecules that contain such elements as actinium, thorium, and other. So this is the Hamiltonian for the diatomic molecule of the interaction of the Schiff moment with electrons. So here S is the Schiff moment and Ws is the molecular constant that describes the interaction of the shift moment with electrons. And in the experiment, it is possible to measure some energy shift, which depends on the value of the Ws constant. And so we have considered a list of different molecules containing F elements with deformed nuclei and calculated this Ws constant. So one can see that for some of molecules, this molecular constant is even slightly larger than for the thallium fluoride molecule. And for this molecule, we have also calculated other parameters such as molecule frame dipole moment or internuclear distances, which can be important to prepare experiments. And finally, we have made some estimation of the possible effect. So we can take the expression of the shift moment in terms of the theta parameter of CP violation forces inside the nucleus, UCD. And for the estimation, we suggest that it is about 10 to the minus 10, this parameter. And using our calculated Ws constant, we can estimate the possible energy shift in molecule. And so one can see that in such molecule as actinium nitride, the effect can be larger than in the thallium fluoride molecule. And as I told, now there is a very sensitive, extremely sensitive centric experiment by the group of David DeMille and Tatiana Zivilinsky. And one can imagine that if someday it will be possible to achieve the comparable sensitivity for such molecule as actinium nitride, then it will be possible to set several orders of magnitude better constraint on this parameter theta. So now I'll move to the next topic. It's about the nuclear magnetization distribution effect in molecules and atoms. And there is some motivation. So the first motivation is to test the electronic structure theory. As you know, in order to extract the value of the electron-electric dipole moment, one usually needs the theoretical value of the effective electric field, which interacts with electrons and produces the energy shift that can be measured in experiment. At present day, I guess the electronic structure theory is rather good, but in any case, it would be nice to have some checks of this theory. And usually for this, one calculates the value of the hyperfine structure constant and compare it with experiment. And my talk about this hyperfine structure constant. And other motivation is that maybe one can use the approach that can be explained to study also the nuclear structure. So this is the expression for the hyperfine structure constant. So this is constant can be measured in experiment. And one can express it in terms of two terms. And the first term is the hyperfine structure constant in the point magnetic dipole approximation. So we consider the hyperfine structure constant induced by some heavy nucleus which has such finite size, and actually we suggest that this nucleus has only point magnetic dipole moment. Of course, it is just an approximation, and there is some nuclear magnetization distribution inside this nucleus, and it is expressed by the second term, which in atomic physics is known as the Bohr-Weisskopf correction. And it seems that in all previous all-electron calculations of molecules that are considered at present day to measure the electron-electric dipole moment, one only calculate this I0 constant, and this constant has been neglected. So we have suggested some approach that can be used to calculate this contribution. So for this, let us consider the hyperfine structure Hamiltonian, and here we can see the value of the nuclear magnetic moment, and here we also see some function that describes the finite nuclear magnetization distribution inside the nucleus. And we can separate out some operator T Bohr-Weisskopf, and expectation value of this operator will give us the Bohr-Weisskopf correction. So there is some problem in that this function of the nuclear magnetization distribution actually is not known from experiment, and maybe a nuclear theory can provide this function. However, we have considered some approach that can be used to avoid any explicit consideration of this function and use some experimental data instead of this. So we have shown that it is possible to factorize this Borovitskov correction to the hyperfine structure constant into the pure electronic part and into just one nuclear magnetization dependent parameter. And expression for this parameter is given by this equation. One can see that from the electronic structure point of view, it is the simplest possible matrix element. It is just expectation value of some operator over the one as function of the hydrogen-like ion containing the heavy nucleus under consideration. However, the problem is that, as I said, actually we do not know this operator with good accuracy because it depends on the nuclear magnetization distribution. However, we can use this factorization, and this is what we've done. So let us consider the radium plus cation. For this cation, we have considered ground and several excited electronic states. So let us consider, first of all, the ground electronic state. We have performed rather good calculations, which takes into account high order electron correlation effect within the couple cluster with single, double, triple, and even quadruple cluster amplitudes, and obtained the value in this point magnetic dipole approximation. Also, we need to calculate this Borovitskov correction, and instead of calculating it by this formula, we have suggested to use this equation to extract the value of this BS parameter, and it can be extracted by combining the theoretical value that we have calculated and also the experimental value of the hyperfine structure constant. And in the denominator, we also have such some pure electronic structure parameters that has been calculated. So we combined experimental and theoretical data and extract the value of the BS constant. So, okay, next, due to that factorization that has been shown, it is possible to use this universal one BS parameter to predict the Borovitskov correction to any electronic state of the radium cation or radium or neutral radium atom or any molecule that contains radium, for example, radium fluoride molecule. And for this, we calculate this pure electronic structure part and use the same value of the BS constant that has been obtained for the ground electronic state. And we did it for the first excited electronic state of radium plus cation. So the hyperfine structure constant in the point magnetic dipole approximation is given here. And also we here one can see the value of the Borovitskov correction that has been calculated in the suggested approach. And this is our final value of the hyperfine structure constant for the first excited electronic state. And this is the experimental value. So one can see rather good agreement with this. However, of course, the most interesting application is the molecule, and it is radium fluoride molecule. And we have calculated a hyperfine structure constant for the first excited electronic state and the ground electronic state of this molecule. And of course, in this case, we have actually not one, but for each state we have two constant hyperfine structure constant, parallel and perpendicular. So we have, as usually, we have calculated the I0 constant within the point magnetic dipole approximation. And using this approach, we have calculated the Borovitskov correction. And so we have calculated these electronic structure parameters, and for prediction, we use this BS constant that has been extracted from the ground electronic state for the radium plus cation from the previous slide. So these are our final predictions for this hyperfine structure constant. What is interesting is that this Borovitskov contribution is actually not negligible. It contributes about 30% into the, even for the ground electronic state of the radium fluoride molecule. And actually, it seems that at present level of theory, this contribution should be taken into account. So now I'll move to the last topic of this talk. It is about quantum electrodynamics effect in molecules. So, for example, let us imagine that we would like to measure the energy shift in some radioactive molecule. And of course, it is extremely difficult task, and it would be nice to have some theoretical prediction for these transition energies. And what we need to get an accurate theoretical prediction of these transition energies. Of course, from theory point of view, we have to use good basis set. We have to treat electron correlation effect very accurately. And finally, we have to use good Hamiltonian. And in best previous molecular calculations, one have used Dirac-Coulomb and sometimes Braid Hamiltonian. But actually, it is known that for atoms, people goes beyond this approximation, and now they can take into account the quantum electrodynamics effects contribution to the transition energies. And there are some model operators of quantum electrodynamic effects suggested, for example, by Victor Flambaum, and another operator has been suggested by Vladimir Shabayev. And actually, there are some other proposals for the form of such operators, maybe more simple. However, no such attempt to take into account quantum electrodynamics effect into transition energies of molecules has been undertaken up to now. So we have developed our version of the QED Hamiltonian, then can be conveniently used in molecular calculations. And I should note that its operator is very close to the suggestion by Shabayev for atomic case. And so we have applied this approach to predict transition energies, first of all, for the radium plus cation. So let us consider some transition energy, for example, transition energy between the ground state and the WD 5½ state. So at first approximation, we consider the Dirac-Coulomb Hamiltonian and perform calculation within the couple cluster single, double, and triple amplitudes. And this is at present some standard approximation. We try to go beyond this approximation and take into account higher order correlation effects. So, but one can see that the agreement with experiment actually is not very big, because this unit is in milli-electron volts. It is about 8 wave numbers, so actually it's not very bad. But this agreement is not excellent, and then we taken into account the GAUNT interaction. It's the dominant part of the Braid interaction, but the agreement is still not very good, not very excellent, and only when we taken into account the QED contribution, we obtain the very good agreement between the experiment and theory. The agreement is within just a few milli-electron volts. And what is interesting, so let us consider some case. For example, we can consider the ionization potential. So one can see that, for example, one can compare contribution from the high order electronic correlation effect. So we can compare this first approximation with this extremely high approximation within a couple cluster with single, double, triple, quadruple, and even pentaple cluster amplitudes. We can see that this contribution actually is not very big. It is smaller than the effect of QED contribution. And this is true for all the considered cases. So QED contribution actually it is important contribution, and we have tried to take into account this contribution for the transition energy in the radium fluoride molecule. We have considered the transition between the ground electronic state and the first electronic state, and this electronic transition can be used to laser cool this molecule. So we have also taken into account high order correlation effect, and finally we have taken into account QED effect, and the final discrepancy between theory and experiment is just about 2 milli-electron volts. So one can know that in this case also the high order correlation effects gives smaller contribution to the transition energy than the contribution of the QED effect. And so now this effect can be taken into account explicitly into the molecular calculations. And this is a brief summary of the talk. And so radioactive molecules with default nuclei are extremely sensitive to the parameters of the CP forces. Actually, tiny nuclear structure effects such as the finite nuclear magnetization distribution can significantly influence the hyperfine structure constant. And at present level of theory, I guess that they should be taken into account. And finally, now QED effect can be also included in the molecular theory. So there are some topics which we are working on in my group and our laboratory. And thank you for your attention.
Okay, thank you, Leonid. So we are perfectly in time. And are there comments, questions? I see one question from Shane, please.
Yeah, hello. So this is really cool, especially with this Bor-Weisskopf effect calculations. I'm wondering if you calculated it for any other states in the radium fluoride, in particular the pi 3/2. For sure, this year we will measure the A factor in 223 and 225 in this sigma half to pi half transition. But are there any other states that you've calculated it for? Because we can maybe do measurements in those as well.
Okay, yes, of course, it is possible to predict these transitions. And actually, the most interesting, I guess, it's maybe D states. I guess the Bor-Weisskopf effect will be.
The reason why I would like to do two transitions is that the Bor-Weisskopf effect is present in this transition, but experimentally we can only measure an A. We can't say how much of that is the actual effect. So my idea was, is there another transition where you expect the sensitivity to be much less? And then we can kind of, get a feeling for what the contribution would be in this transition. So I'm just wondering what ideas you might have for this.
Okay, great. So I guess that it will be sensitive, yes.
Okay, so we have a next question from Timo, please.
Yeah, hi, Leonid. It's a wonderful talk. Thank you. And I have a question about the last topic, the QED corrections, QED effects in atomic transitions. So what basis sets did you use there, and what is the basis set error?
Basis set error, I guess it's just maybe 1 or 2 milli-electron volts. The basis set is extremely high. It includes K and L function explicitly, and actually there is some extrapolation on infinite L. So it is extremely large basis set.
Okay, how did you construct them?
There is some scheme that we have developed. It is some natural. It is natural-like basis. We construct natural-like basis set for high harmonics because, as you know, we cannot include many harmonics with high L into the calculation. So maximum maybe 8 of them, I function and so on. So actually, we can also test it in scalar relativity calculation. We can use much more number of basis functions. For example, 15I, 15H, 15, and so on functions.
Okay.
To test the uncertainty of basis set.
Yeah, thanks.
Okay, thank you. So the next question from Anastasia, please.
Yeah, thank you for the nice talk. I was curious. So you include the QED corrections, but you use GONT instead of Bright. So
So actually, one can see that GONT interaction is very small, and actually we have made some previous tests that GONT contribution really gives them the large part of the Bright interaction. And for atoms, for example, there are some calculations by Ephraim Eliav who calculated the contribution of the remaining part of the Bright interaction besides the GONT interaction. And actually, for the radium plus cation, the maximum deviation of Bright and GONT interaction is just 1.4 milli-electron volts. So it is negligible.
Yeah, sorry, can I ask something else about this? I guess.
Okay.
Yeah, go on.
Yeah. So the GONT that you calculate, that's also on a couple cluster level, or is
yes, it's Fock space couple cluster level.
So it's introduced as an operator in the iteration procedure, basically.
Yes, of course.
Yeah. Okay, thank you.
Okay, and next question from John.
Hey, just more of a comment. Thanks. It's really neat to see the F electrons calculated for the shift moment business. But actinium 227 is not a case. 225 actinium is terrific. It's got really good experimental evidence supporting it. We could go through that in the panel tomorrow, but 227, it's explained by parity symmetric potentials, reflection symmetric potentials. There's strong experimental evidence against that being an octopole deformed case. I'm sorry. That's being ignored. So, but 225 is great. So your calculation doesn't depend much on the hyperfine structure details, right?
Yeah, right.
So 225 is good for you, right? Yeah. That's great.
So actually, our molecular constants do not depend on the isotope. So.
Yeah, great. Awesome. Okay. So people should work on 225. It's a 2-week half-life. It's made by a long source. It's okay. Thank you.
Great. Thank you.
Okay, next question from Jaideep.
Hi, thank you for a wonderful talk. I was curious, you mentioned on your very last slide that you are also interested in let's see, shift moment enhancement in crystals. I was wondering if you could briefly talk about that. That sounds very interesting.
Yes, about 5 years ago, we made a paper where we have calculated the shift moment enhancement in the lead titanate crystal. And actually, as far as I know, this crystal has been recently used in the Casper experiment, where one measured the shift moment induced by axions. So this is some varying shift moment, but as far as I know, they used our prediction for the enhancement in crystal. So we have developed some technique that can be used not only for molecules but for crystals.
Okay, thank you.
Okay, so I don't see more questions. So did I miss someone? I guess perhaps not. Okay, so if we don't have any further question or comments, and yeah, we are actually quite in time. So I guess we now can go to the next presentation, and it will be given by Konstantin Gaul, who will tell us about fundamental physics with molecules. So Konstantin, are you ready? Leonid, you show stop sharing. Okay, cool.
Now you can hear me? Yeah. Can you hear me?
Yeah.
Okay. I just closed my window. So now it should work. Right. So, okay, yeah, then thanks Timur, and thanks to the organizers for setting up this great workshop with all these interesting talks and giving me the opportunity to show our research on fundamental physics with molecules. I'm working in the group of Robert Berger in Marburg. Yeah, and so I think the start is very clear. We have seen this many times in this workshop, so we are all agree that the standard model seems to be incomplete, and there is a discrete symmetry violation connected to some of these problems which cannot be explained within the standard model. So it's really really interesting to search for this discrete symmetry violation. So, and in molecules, this is very interesting place to search for discrete symmetry violation, because in molecules these effects are largely enhanced, and we have heard a lot about the PT violation in diatomic molecules already, but we have also heard by Dima Butger that you can go to chiral molecules and search for P violation in the standard model, and together with Misha Kozlov and Timur Isayev, we have also worked on how to sense dark matter with chiral molecules. But also there, radioactive molecules can play a role to increase the size of the effects. but today I will talk about the PT violation in diatomic molecules. And yeah, and to tackle this problem from a molecular theory side, the first thing, of course, is to predict molecules which have large effect sizes, and also to interpret the experiment is to look where do a molecular EDM come from. So what are the sources of the molecular EDM? And we have seen flavors of this graph also many times in this workshop. So we have to start from the fundamental theory, and what we want to learn is where does the PT violation comes from, and then we see that there are many fundamental parameters which can be the source of PT violation, and they are predicted differently in different theories. And on the hadron level, then they contribute to, for example, the proton EDM, and we have seen this also before, and then on the nuclear level to the nuclear magnetic quadrupole moment and the Schiff moment, and even higher moments can be considered. And on the molecular level, this is very important, because then in principle, all these effects can somehow contribute directly or indirectly. And there we can have mainly these two groups of open shell and closed shell molecules, or also often that is diamagnetic and paramagnetic atoms. And in these two types of molecules, the effects contribute differently. And then it's also very much dependent on what is the nuclear spin, or which nucleus is the molecule made of. And then we can have contributions from many effects. So, for example, in the open shell molecule, usually we consider the electric dipole moment of the electron and the nucleon-electron current interaction, the scalar pseudoscalar one. But when we have a nuclear spin unequal 0, then of course Schiff moment and valence proton and so have also interaction with the electrons in this molecule. And if we go beyond 1/2 nuclear spin, then we can have also the higher moments like nuclear magnetic quadrupole moment. So there are a lot of parameters contributing to one effect which we can measure, the molecular EDM. And so to write this down in equation, one usually goes to effective spin rotation Hamiltonian and use effective parameters to describe these effects. And we have already heard that polar linear heavy elemental molecules are very good for this, because they have the strong internal fields and are easy to polarize, so you need only the small external electric fields to align the angular momenta and do the measurements with a high resolution is then very good for these molecules. So what we have when we have an electron spin is these electron spin dependent terms like electron-electric dipole moment and nucleon-electron current interaction scalar pseudoscalar. Then when we have the nuclear spin, then there come a lot of other parameters, making it really complicated, and then we can have even the higher moment. So this means we have a lot of parameters contributing to the same effect. And what you see here is this W. This is the electronic structure parameters we have to calculate in order to say how sensitive is this molecule and to interpret the experiment. And usually we say large effective electronic structure factors means high sensitivity, but we have already heard that this is not always the case. So it is like this, but we have to be careful about this general statement. So this is why I put this question mark here, because when we have all these parameters and we would have only very large or the same parameters for 2 times the same molecule, then we of course cannot say anything about the disentanglement of these parameters. So I will talk also later a little bit about this. And yeah, so what we want to do is less sophisticated than what we have heard from Leonid or yesterday from Anastasia and Timo. So we don't do we don't try to do the most accurate computations, but we try to find molecules where we can look for, and also find general trends in order to understand what makes this effect large and where to look for future experiments. What kind of molecules shall we choose? So what we do is we do quasi-relativistic Hartree-Fock and DFT calculations on a proton symmetry level. This means we include spin polarization effects, and we can compute arbitrary properties in this approach. And usually for simple molecules like radium fluoride, we are within 10%, and even for mercury fluoride, for example, or mercury hydride, which has a little bit complicated electronic structure with more electron correlation, then we are within 20% usually. We can even do excited state calculation within a self-consistent manner. With this method, then we can compute, so I developed some toolbox approach to compute in this approach arbitrary properties. This means we can compose our properties generally with arbitrary derivatives, and so we can really fast compute these things. So normal calculation for a small molecule can be done within hours on your laptop and on your notebook, and then we can make fast statement about a molecule. But of course, when it comes to interpretation of the experiment, then you have to go to the more sophisticated methods. So what we want to learn in is periodic trends and general selection rules for where to look for good candidate molecules to search for fundamental physics. So let me first look at this case where we have only electron spin and no nuclear spin, and Anastasia has shown this yesterday, and this picture from this paper by Ramsey Musaev and Chubb was also in the talk by Ramsey Musaev, where it's shown how to disentangle these parameters from different measurements. And then what we want to have is, of course, measurements with high sensitivity, but they should be more or less orthogonal to each other, so that we can decrease this coverage region as much as possible. This means we need at least 2 experiments to say anything about this, so to not have an infinite coverage region. And the more experiments we have, the better. And of course, they should be somehow orthogonal to each other. So what I will show you on the next slide is we have studied several diatomic molecules with doublet sigma ground state in order to learn something about these periodic trends of these effects, and look for what is the chemical enhancement to this. So apart from the atomic models with the Z-scaling, what can we learn about how large is the enhancement in the different groups of the periodic table, and then learn something on how this coverage area in this parameter space depends on the nuclear charge and the chemical influence. So what I have done here is I calculated all these molecules across the periodic table, going down up to element 120 and 121, which are not even found so far or produced. And then we looked in the groups of the periodic table to what is the trend of this parameter compared to an atomic model. And then we use this empirical atomic model. So empirical because this enhancement factor gamma to the power of 4 is from the empirical model. And we see, okay, it should scale as c to the power of 3, and this gamma depends also on c, but not polynomial. So we say, okay, if this gamma to the power of 4 is okay, then we multiply our numerical calculations by this factor, and then we should see, if we do a double logarithmic plot, this linear behavior, so that we get the c to the power of 3 scaling reproduced. And what we find is then that the scaling in group 2 and group 3 is lower 3. Z to the power of 3, so somehow chemically suppressed Z scaling, and we find larger effects in the group 4 and 12. And unfortunately, also these groups show larger electron correlation effects and maybe have a more complicated electronic structure. So, so it's more difficult to do really most accurate predictions for these molecules. So what we then also looked at is in the row of the periodic table, how large is the enhancement when we go from, say, radium fluoride to actinium oxide to thorium nitride, and then we find that the dependence on the nuclear charge there is much larger. So the chemical influence by the substituent really changes the effect more dramatically when you go along the row than when you go along the group in the periodic table. So you can really tune somehow this effect by changing also the substituent. And there was also some study by Sunaga and co-workers who looked at this SP mixing to maximize this matrix element, which is connected to this. So then we want to disentangle this coverage region. So we want to minimize this coverage region and disentangle the parameters. And then one has to look at the ratio. And here I want also to refer to a nice paper by a team of Fleike and Jung, who also looked at this ratio before, and they also suggested how to use diamagnetic atoms in order to get orthogonal measurements to these diatomic molecules. And what we found when we look at the ratio is that this really does not depend on the chemical environment and follows some simple exponential law. So there are also these analytical rules derived by Chyblovich originally, and then later revised by Chuba Flambaum, and they work good for the molecules between Z to the power of 20 and Z to the power of about 100. But of course, as they assume a point-like nucleus, the model they have diverges then for heavier nuclei and cannot be used for nuclei with larger Z than 100. So, and what we then did is we find this simple exponential law and then put together with the chemical enhancement we have shown before, and then we have a simple model to say how can we minimize the coverage region from molecular theory point of view. Of course, it's proportional to the uncertainty of the experiment. And then we can compare to the atomic model and see that this is really really qualitatively the same. And then when we change the groups of the periodic table in our model, then we see that we get little asymmetry in this contour plot. So red is the best. So red is the lowest coverage region. And this is, of course, when we use two heavy atoms, but they should not be too similar, because in the middle there's this infinity of the coverage region, and then it drops dramatically. So they should be different, but they should also have a large sensitivity. Then I don't want to talk long about polyatomic molecules. Nick Hatzler has shown how important they are, and they have shown in this nice paper from 2017 that they are really promising candidates, because you can, due to this internal co-magnetometer states, reduce the experimental uncertainty. From theory perspective, there's of course no real advantage in using them. So when you only look at the electronic enhancement of the new physics effects, because they are almost the same, and they also fit perfectly in this line here. So the ratios are the same. So you wouldn't gain much when you have the terbium hydroxide and the terbium fluoride with the same uncertainty. Then you get 2 times the same thing and have no complementarity. So for this one really has to look in diamagnetic systems and maybe more complex polyatomic molecules, which are not linear anymore and have then a different spin rotation than atomic. So what we have seen is also that this breakground of diatomic linear molecules is somehow restricted, and we see large effects in group 4 and 12, but of course then we see also that the electronic structure is more complicated, meaning theoretical predictions get more difficult to have really accurate predictions to interpret the experiment. And so with this, I want to go one step further, and this is looking now on this global parameter space of all the relevant parameters. So I have now 6 parameters, which I take into account here, only from molecular theory perspective. So of course, in nuclear, when you count for the nuclear structure, everything gets even more complicated because you have the parameters which also depend on each other partly, and then you have also to see how to disentangle this on the nuclear structure perspective, but also on the molecular structure perspective, we have already all these parameters, and this is what we have to look at is at the different cases, and then how can we disentangle all parameters from such an experiment and get robust bounds on all the parameters. So the case we looked at is before us this open shell molecule without nuclear spin. Then it's this 2 parameter space. Then there's a closed shell molecule with a nuclear spin, and then you have this 4 to 5 parameters. So because you have this shift moment, you have this tensor pseudo tensor coupling, and if you have a valence proton, then there's of course this other contribution to the shift moment, which has also another interaction in the molecule. So this is directly then proportional here to the proton electric dipole moment. And then you have also this magnetic interaction, hyperfine induced interaction with the electric dipole moment of the electron, and this nucleon electron current interaction with the scalar pseudoscalar. These are suppressed in comparison to the open shell molecules by the proton mass, and so it's much smaller. So we have here also different sensitivity to these parameters. That's the other side. So for disentanglement, it's good that we have different parameters. Then we can have open shell molecules with spin I1/2, and then what changes is that the main effect here is, of course, again, the direct expectation value of the electric dipole moment interaction. And then there's the fourth case where we have the open shell molecule with the open shell nucleus with higher spin, where we have also nuclear magnetic quadrupole moment. So this means we have different cases of molecules which we can choose to disentangle this parameter space. And here radioactive molecules come in play because they have long isotope chains, and then we can choose one molecule and cover 4 classes. One molecule in quotation marks, because you need to ionize or so in order to get from the open shell to the closed shell one. So what we know already, radium monofluoride is really an excellent candidate because it has simple electronic structure, is controllable, so seems to be laser coolable, and they're really nice isotopes. So we have the spin 0 isotope, which is a class 1 molecule. We have class 2 when we have the ion. So one can also look at the ions which were presented by Andrew Childs. And then we have 225 radium fluoride as spin 1/2 and 223 as spin 3/2. Of course, we have not the unpaired valence electron as I think so. The nuclear physicists have to correct me here. Where to look else is, of course, when we search for nuclear spin dependent things, and radioactive molecules, then we go to the actinides. And so the first idea would be to look at isoelectronic actinides. And then we have heard already that so these isotopes are from nuclear structure perspective really interesting. So I have to cross out this 227. So as we have heard in the discussion before, and there we have also open shell, proton shells, open neutron shells, depending on which isotope we have. And then there's of course this protactinium, which is also in discussion the whole week, which looks really interesting, at least in order to find out what really the nuclear structure is. And embedding it into the molecule may also have to use precision spectroscopy to learn something about the nuclear structure. So from electronic structure perspective, the actinides also are really good molecules. So we all know the best experiments so far is with thorium oxide, so the best limit on the EADM. There's this thorium fluoride plus experiment planned. Then we also computed in this study where we computed across the periodic table molecules actinium oxide and thorium nitrate, and there find also large enhancements of the effects. But here one has of course to look how the electronic structure is for doing precision spectroscopy. But if I understood correctly yesterday in this one talk, that actinium oxide may be available out of the box at TRIUMPH also. And then yeah, of course, we can also look at the cationic species. We have heard this by Leonid in the talk before and by Anastasia yesterday, actinium hydroxide, for example. So the question is, what about protactinium? And so the last slide I will show you is on protactinium, and I will propose one molecule one can look at. But then I will also say we have a better molecule, and you have to wait some days or weeks until we upload the paper, and then everything is finished. So we have actually a master student, Carsten Zürch, who's working on protactinium, and it's really really exciting results about protactinium molecules. And so what we looked at is to find, of course, isoelectronic to radium fluoride, because we have then easy electronic structure. But one could also look isoelectronic to thorium oxide, but then so in protactinium it's even more F electron dominated. We have strongly mixed ground state. So for example, protactinium oxide plus. This was also calculated in 2013, and yeah, it looks really complicated, the electronic spectra. But there's also protactinium nitrate plus and protactinium oxide 2 plus, which were actually experimentally observed. And there's a theoretical study on protactinium oxide 2 plus, and yeah, it's looking really nice because it's dominated by a non-bonding orbital, and for one electron in this orbital. And this is the F electron. And here I show you now this orbital. So it has a 5-half ground state, which is mainly phi. And this is a yeah, I will thank you, Timo. And this electron is in this F orbital located at the protactinium and has no almost no probability density at the nucleus because the F electron. So this means we have an open shell molecule where we can do nice things with, which behaves what enhancement to new physics is like a closed shell molecule. And then we calculated, so I can say already the shift moment here is strongly enhanced. So in this unit, what we get with the same method for thallium fluoride is a value of 5,000. So it's more than double that large. So the shift moment enhancement due to the electronic structure. The electron spin-dependent effects, of course, are suppressed in the ground state as it's an F electron. And as we have protactinium oxide 2 plus, so it's mass to charge ratio is in the range of barium plus. So in its ion may be sympathetically coolable in an effective way. So, and with this, I say continuation follows, and we will soon present an even more exciting candidate. And with this, I want to conclude. So that what we need for the future is many good experiments, and there are already many good experiments, and there are many plans for new experiments, and that's good because there are so many parameters. And in order to get robust bounds, we really need experiments involving non-zero nuclear spin, and then radioactive molecules come in play, because here we have all these different isotopes and can play around with this. And yeah, we should focus on polyatomic molecules because of the experimental advantages. And of course, as I said, non-linear polyatomic molecules are also an interesting thing to look at, because then we have a different spin rotational Hamiltonian for the PTOR properties. Yeah, so then for you, so the protactinium molecule I say is really good, is protactinium oxide plus, oxide 2 plus, which is has a simple electronic structure and large enhancement of Schiff moment, and more interesting protactinium candidates will follow soon. And with this, I want to thank you, and I want to thank Carsten for all his work on protactinium he did in the last month. And yeah, then I'm happy to hear your questions.
So thank you, Konstantin, for very nice talk. And are there questions, comments? Okay, I don't yet see anything, so I can perhaps ask you something. So you use this nomenclature of class 2, class 1 molecular species, but I'm afraid it's not a likely designation, because we are using this class 1, class 2 with Robert for this non-bonding orbital.
Yeah, so of course it's a different context then, yeah.
Yeah, so I mean, okay, I now see a question from Jaideep, please.
Hi, thank you for a very nice talk. And I wanted to also, I appreciate the sentiment that there is a lot of complementarity depending on the particular molecule that you choose. So I'm glad that you emphasized that. The question I have, and you probably mentioned it, but I kind of missed it. Could you describe again what PaO2+ looks like in terms of electronic configuration?
So it's a 5-half ground state, so omega is 5-half, and so it's a F electron in the, and it's phi-like. So so the F electron looks like this. So this is now the complex spinor. So it's like an F 5-half hydrogen atom electron. So
I see. Okay, thank you.
Okay, and I see a question from Anastasia.
Yeah, hi, that was a really nice talk, and yeah, nice results. So I was wondering, maybe we could go to the spin rotational Hamiltonian that you presented with all the.
Yes. So can you see it? No.
No, I can see Timur.
So
you're not sharing.
Okay.
You have to share your screen.
Yeah.
Yeah.
Yeah. So yeah. So for example, yes. Yeah. So this is familiar, and for example, for yeah, molecules like barium fluoride, we just care about the blue term and so on. Yeah. And you mentioned that this would look different if we have bent polyatomics. So, I mean, in what sense would it be different? Will it not be any more this linear combination, or?
We wouldn't have this simple expression here, and we wouldn't So especially when we have, so the most complicated case would be, of course, be a asymmetric top. Then we would have a tensor for this. So it's like, so this is like the PT odd contribution to the normal PT converting spin rotation interaction. So, and there we would have also the spin rotation tensor then. So this is mainly what would change, so that we have not only this isotropic contribution, but also anisotropy and these constants.
But that would be in all the terms, right? Not just in the...
In all the,
Yeah.
so we would get a much more complicated spin rotation.
Mhm. Okay, thank you.
Okay, more questions, comments? Okay, I perhaps have one comment to your report. And you mentioned then in 3 atomic molecules, they somehow don't present interest from theoretical point of view. I mean that, of course, they don't present interest from the point of enhancement of PT.
Yeah, so this is what I try to emphasize. So it's only from this
molecules which could be quite interesting. In
yeah, so especially from
yes,
okay, only from this enhancement point of view and this
enhancement
this
is
entanglement of the sources, they have
and
no new advantage over the other, but of course they are highly interesting, as I said.
Okay, so very good, and we are in time, so we can go to our other talk, and this talk will be from Svetlana Kotachigova, who is going to tell us about creating molecules with unstable isotopes. So Svetlana, please.
Okay, good morning. First of all, I would like to thank the organizers for inviting me to present our work on formation of ultra-cold molecules with unstable isotopes. I am a molecular physicist, mostly interested in electronic and vibrational properties of heavy molecules. In addition, I am involved in developing schemes for laser cooling and trapping molecules. And today, I describe our first steps in applying this experience to formation of polar diatomic molecules with laser-cooled atoms, one of which is radioactive. So motivation for our research is that molecules with unstable isotopes is now one of the main directions in search for new physics outside of standard model. So chart on the left, it's a chart of nuclei with the number of neutrons on the horizontal axis and protons on the vertical axis, showing a relevant nuclear landscape. Nuclei with the same number of protons but different number of neutrons are termed isotopes of the same chemical element. Stable nuclei are shown in black squares, and unstable nuclei are which are discovered and synthesized are shown in brown color. So we can see there are many unstable nuclei known very well. So unstable nuclei, among other things, have advantage for search for electron dipole moment in fundamental particles and for violation of both time reversal and parity symmetries. Many of these advantages are discussed in the last few days, so I'm not repeat them today. So, but it was also very well established that using diatomic molecules with radioactive isotopes in experiment for measuring ADMs is very promising. So I think this idea was first suggested in the 70s, or 60s, actually 70s, by Sanders, and then followed by Flambaum, Lapsowski work. In such a system, extremely large external electric fields are achievable. Or it's internal electric fields. So as a result, the internal effective field can be large enough to be measured, and value of this field required to extract to value EDM from experimental data, as I understand, must be also estimated by theoretically. It was also noticed that P anti-parity non-conservation effect are strongly infects in heavy atoms due to relativistic effects. And then a latest study suggested the possibility of further enhancement of internal fields due to omega doubling and the ground state molecules. But number of people found with colleagues and Misha Kozlov and so on. So today I focus on francium silver molecules. These molecules is of interest to experimental group of David DeMille of University of Chicago, Tanya Zelevinsky at Columbia, and as much I know, it's also the Triumph Laboratory. And we also heard yesterday a very interesting talk by Timo and David talking about priorities to use this molecule for new physics. So as I envision, this molecule can be used as sensor to measure nuclear shift moment. At the same time, for us, it would be interesting to assembling ultra-cold francium serum molecule to study, but also a way how to form molecules with unstable isotopes. But first, of course, we have to study scattering properties for both atoms in order to establish a way to cool a molecule. And also, indeed, our experience with forming this kind of molecule will be used in various quantum simulation platforms. First, a few words about francium. Francium is the biggest atom in the periodic table and first obtained in some chemical reactions and nuclear reaction actually by Margaret Perry in 1939. So unstable isotope of francium, it they all actually, there's no stable isotope francium, but they are located in a region of nuclear charge which exhibit octuple deformation. Such deformation leads to a reflection asymmetric nuclear shapes. They call it pear shape. It is expected as a result of such deformation, the orbitals of valence s electron, which belong to penetrating orbitals, are deformed in vicinity of nuclear as electron C column potential generated by the nuclear charge. So it was shown that, in fact, enhancement factor of electric dipole moment in francium and gold are also studied in a number of references. So cooling in general, cooling atom for precision measurements. So cold atom technology or techniques has been developed already over the past 25 years. So experiment by many experimental groups with these techniques provided already very high statistical power, and there is a way to monitor these statistical effects. So laser cooling and trapping of francium isotopes is extremely important for precision measurement, and advantage of laser cooling and trapping atoms for EDM studies is to increase coherence time and decrease motion-induced magnetic field. Optically trapped molecules provide long coherence time and excellent resolution. So, and now cooling and trapping of francium routine, and there are some references to some experiments, and I'm sure it's not all of them. And matter of fact, silver also was laser filled and trapped in the past, and 2000. So in principle, it is known that laser cooling on atom, ions, and molecules led to creation of high precision atomic clocks, meta-wave interferometry, simulation of exotic phases of matter, development high sensitivity sensors, and enabling of ion quantum computation. So that's why it is really important to cool these promising molecules to very low temperatures. So, and it seems to us that best way to create ultra cold francium silver molecules is to assemble them from ultra cold francium and silver atoms by photo association, so-called stirrup scheme. So first, near quantum degenerate gas of polar molecules of potassium rubidium action molecules were created in the absolute ground state at very low temperature. It's nanokelvin temperature by Gila group. And I was very fortunate to be part of this research, and I help experimentalists to find a way to cool this molecule, to photoassociate actually. So, here, on the right-hand side, there's a scheme which shows how this experiment was performed when two free atoms colliding in actually magnetic field, and they could create very weakly bound molecules, and that using Feshbach resonances, that molecules could be more stable, and then of course using stir-up and transitions to excited states, some of the vibrational level of excited states, and then vertical practically transition to the ground state. It was achieved to convert very fluffy big molecule to much smaller and coupled tightly bound molecule in the absolute ground state and the lowest low vibrational hyperfine states. So such massive 9 order of magnitude removal of collision kinetic energy can lead to, it was already shown, novel physics and very large improvement in control capabilities. So a little bit about these Feshbach resonances, because we actually working on this to observe Feshbach resonances with francium silver. So it was known that you can control much better interaction between atoms using Feshbach resonances. And also, there are many other things which would actually I can mention maybe later, but here I can say that two atoms come together prepared and actually in an open channel. Most likely they prepared in lowest hyperfine levels. So when they collide and the changing magnetic field, there are some other channels become coupled to the open channel. When at a moment when there's a resonance occur, when bound states of these other channels crossing the threshold of the open channel, and then you can see resonances. Accurate ab initio electronic structure calculation of the ground and excited francium argon so we supposed to couple this, oh boy, I don't know what's going on, sorry. These atoms from very long distance, I already mentioned about it. And we also need to analyze very accurately vibrational structure of ground and excited states to prepare coherent quantum control and transitions. So we also working on finding Feshbach resonances and then calculating hyperfine and Zeeman structure of X and A state potentials. So, and we also look at upward and downward transitions with sufficiently large transition dipole moments. So what other problems we have to solve? So we need to know Fermi contact interaction that couples electron nuclear spin. And we also investigate our dependence on this interaction. So spin orbit mixing vibrational levels in excited state is absolutely essential in order to provide possibility to go from levels one sort of states of maybe triplet states to singlet states. So we need also multi-channel calculation of transition dipole moment for Raman transitions. And also calculation of molecular dynamic polarizability of vibrational levels is important in order to determine how we actually trap these molecules in optical traps, whatever it is. So, but I just want to say from my experience that complete understanding of such structures coming from combined experimental theoretical efforts. It's supposed to be experiment are combined by theory because it requires extremely high precision in order to actually to find a way how to really create these molecules. So here's our ab initio results. This is in the first stage, as I mentioned. So we used, here it's non-relativistic results. For comparison with relativistic calculation, which I show on the next slide, here I just show ground state potentials, which are most important, of course, on the first stage when we trying to find Feshbach resonances. So there's a publication, a recent one, by Tomza's group from Poland, when they investigated number of molecules, but it's a francium silver also included in their study. And they, we practically performed similar calculation using approximately similar basis set. And we have very good agreement with them. And I believe potentials are pretty good. But I would like to point out that indeed what Timo and David yesterday discussing about silver, indeed we can see there is a unique coupling because potential for the ground state X potential is much, much deeper than potentials in alkali metal molecules. There is no ionic coupling. But at the same time, we see that a potential, a little potential going to the same limit as the X potential, actually a little bit more shallow. So here's a relativistic results of our calculation. And I just put next to it potentials also relativistic for cesium rubidium, pretty close to masses and so on. But we can see big difference. So ionic coupling really play a big role, maybe other things, of course, correlations with d orbital and so on. But I've shown his letters potentials which are of interest. And next slide, you can see it. And yeah, indeed, it's really, even excited states, it's much different. Avoided crossing, which is extremely important for us because we want to have STIRUP going through this area. It's totally different location. So, so we need also to know magnetic, of course, it's more easy, magnetic dipole-dipole interaction and the second order spin orbit splitting. So I just, I want to say that our potentials, electronic structure calculation provide good potential at small, short distances between atoms. So we analyze very, very accurately these potentials because we know we need long range potentials to match to short range potentials. And that is extremely important to have very good precise potentials. And so we sort of cut the electronic structure of initial potential by 12 atomic units. And we started long range potentials, which are C6, like dispersion, like due to C6, C8, and then we added exchange potentials as well. So that's all kind of intermediate long range, starting from 16, and then we smoothly connected these potentials. So, but also long range has the magnetic dipole-dipole interaction, and also there is also other interaction which we need to include in our scattering calculations. It's a second order spin orbit coupling, and it provides additional contribution. But this contribution, it is anisotropy, the same type of anisotropy as a dipole-dipole interaction, but it's also dominates actually short ranges. You will see, I will show you next slide, behavior with R, dependence behavior. So it's couples electric dipole, electric spin of francium and silver to molecular axis, and decouple, one rotation actually decouples. So here's second order spin orbit splitting, and we can see it's almost exponential up to 13 atomic units. And then comparison again with rubidium cesium. But there's a big difference because the most important to know what the value of spin orbit splitting for inner turning point of a triplet sigma potential. And in that sense, it's actually in a turning point, it's here I've shown for francium silver, but for rubidium cesium, this is in a turning point. So here's a much larger, 10 times almost larger. So might mean strong coupling between potentials. So we also used a couple of channel calculation. If I have something. So this is Haber-Pfeil structure, very well known for francium and silver. And here we calculated dependent contact hyperfine interaction between francium in presence of silver and silver in presence of francium. So this interaction is pretty big. We know that francium, of course, and it changes. No, maybe not too much, but it's normally supposed to increase to when you go to shorter distances. Here is an opposite sign, but it's also increasing in absolute value. So the only thing I would like to point out that if we look at the atomic value at long distances, we have excellent agreement. You can look at values. And what I just say, because I am using here valence bond method developed by Ilya Tupitsin with me, and there's a publication. We have a number of other publications on these topics. So I probably need to move on. And these Feshbach resonances we already calculated. It is, of course, very preliminary work. We try to make our potentials extremely accurate, as I said, and they are now accurate to 1%, both A and X potentials. How we know that? We change potentials slightly and see number of bound states. When they don't change anymore, when you change potential, it means, so it's a stable, and of course they calculate it very accurately. So I hope this really shows that potentials we can actually use for calculations of Feshbach resonances. And we did some, but we would like to improve, for example, change using hyperfine dependent behavior and see whether it will affect. Using, for example, a nuclear, not point nuclear, that's a special shape nuclear, so and see how it will affect on our Feshbach resonances. Here's just graph when you see highly excited vibrational levels near the threshold, which is 0 here. So, and they, this magnetic field change, they end up creating Feshbach resonances. There are not so many. It looks like for this molecule, we don't expect big, number of Feshbach resonances. For example, here's 7 resonances, and there is one very wide, but because it's so large, hyperfine splitting for francium, I think one of the reasons we don't see many. And of course, it's due to anisotropy, which is with second order spin orbit does not really contribute because it's a short range force. So magnetic dipole is small, of course, right? And so there's not, it's not hyperfine only practically working here. So, and for stirrup, we have to go, and it looks like if you focus on specific excited states, which is pretty known, A and B small triplet pi. Yes, and our atoms come together in kind of triplet character, most of it. It's a mixture with a singlet character, but majority we checked, it's a big portion of triplet character, and therefore most difficult transition required very good transition dipole moment. It has to be from very long range when atoms so far away, and you should put them together in a short range. Here, transition dipole moment has to be very, very high, the best possible. Therefore, we go to triplet B triplet pi potential allow transition. And most likely, one of the very low vibrational level is good for this purpose here.
Anna, we have
But
only
we would
5
like
minutes
to
for
go
question.
down. Yeah. So vertically, this is sort of forbidden transition, but because of mixture between B and A, pretty good. It's a heavy molecule, so we could get to the ground state, hopefully. So this is my summary. And I just want to mention our group member working on this project, and Kissinger collaborating with us. He's an expert in Feshbach resonance formation, and we are really lucky to work with him on this. Thank you.
So thank you very much. So we have time for a few questions. And I see one question from John.
Hey, can I see the slide on the Feshbach resonances again, please, of the francium silver? You had a very low field. It looks like there's something interesting happening, and very naively that troubles me, because it could be complicated for the handling the molecule if there's a Feshbach resonance with a tail at low energy, low field.
Sorry.
Well, okay, don't worry too much about showing the slide. Is there more structure? Is there more structure at low magnetic field than shown?
This is, yeah.
Thanks. Yeah. Is there more structure at low magnetic field than you're showing?
Here?
Yeah. At 10 Gauss, 50 Gauss.
Yeah. So, not so many. Yes, right now, but we checked near the zero. That's nothing really much.
Good. Thank you. Thank you. That's good to know. Could studying rubidium silver or cesium silver help these calculations, or is it all specific to the francium and the hyperfine structure of the 223 francium? Would studying rubidium silver help at all? Because that's a lot simpler to do.
No, it could be interesting, right? You're right. It should not be much difference, except, of course, in orbit get stronger and usual. So it could be something interesting come up, I mean, different. But in sense, for this field, when people interested in radioactive isotopes. Of course, it could be cesium as well, radioactive, but most likely it's probably there's nucleus not as shapy as francium. I don't know exactly. I'm sort of outsider to this field. I'm just learning. So, but it's interesting. It's always great to compare things. But most likely, silver will affect, certainly, the same way, I believe it should be. There would be ionic coupling. Maybe it depends on how heavy atom or even size of it affects and how much d electrons lying beneath 5s could actually couple to this. It is really most likely very fine effects involved in this too, because that most likely energies of both orbitals are pretty close, so some little effect will change.
Thank you. That's neat.
Thank you. So I don't see any more questions. So thank you, Svetlana, very much. Now we can go to the next talk in our morning session. And this is a talk of Robert Field about Rampant pulse field ionization detected Rydberg spectroscopy. So Robert, please.
Start video. Okay, now let's try it again. Okay, do you see my slide?
No.
Okay.
You have to press a button, share screen.
Yeah, I thought I did, but I will. Okay, where's share screen? Okay, there it is. And now.
And you have to confirm that you're sharing.
Oh, let's see, how did I do that?
Yes, now, oh yes, now we can see your screen, yes.
Okay. All right.
Yes, perfect.
Okay. I'm a small, first I want to thank the organizers for me to present a completely different point of view. I want to introduce Rydberg states. Rydberg states provide unique opportunities to look at the kind of electronic structure that we're talking about.
Robert, can you tilt your camera up just a bit? I can't see your face.
I'm trying, but my computer is it better now?
We still can't see all of your face.
Okay. If I do it more, I'm going to end up decoupling. So, okay, so let me just ramped pulse field ionization Rydberg spectroscopy of radium fluoride is a way of getting high resolution and complete information about scattering of electrons off of the ion core of radium fluoride in a way that may actually excite some of the people who have been looking at other ways to sample the core. So the present experiments have involved detection of transitions exclusively by ionization of a beam of radium fluoride. The signals are weak, the scanning is very slow, it costs a lot of money to do this, and if we want to learn stuff, we need to design experiments that ask not one question at a time, but multiple questions at a time. Now, radium fluoride is spectroscopically very similar to barium fluoride, a molecule which I have looked at a great deal. Everything that we can measure on barium fluoride, we should be able to measure on radium fluoride. Every experimental scheme, even some crazy looking ones, can be tested on barium fluoride, which is a stable molecule that you can make in any laboratory. Now, one special thing about barium fluoride is that the ionization energy, ionization threshold, lies below the dissociation energy. This means that one can look at very high Rydberg states without any interference. This is unusual. It's true for barium fluoride, but not for the lighter alkaline earth halides. And it's probably true for all of the actinide monofluorides, but it would be useful to know whether this is true. If it is, Rydberg states will have a fantastic story to tell. Okay, Rydberg states are basically a way of using the idea of the hydrogen atom to reveal electronic structure. every property of the hydrogen atom is described by a simple formula expressed in terms of integer principal and orbital angular momentum quantum numbers. If you know N and L, you know everything for a state. That really defines structure, and Rydberg states express the essence of the hydrogen atom. Okay, so here are some formulas for how everything in hydrogen scales with the principal quantum number. And we want to be able to take this kind of scaling over to molecules, and we can do that. And one of the exciting things to notice is that the dipole moment scales as the principal quantum number squared. And so that means that, say, n equals 40, we have kilodebye dipole moments, bigger than anything that anybody's ever talked about for a diatomic molecule or for a polyatomic molecule. The polarizability goes to the end of the 7th, and the radiative lifetimes are long, on the order of tens or hundreds of microseconds. So one can do all sorts of wonderful tricks to the molecules in these Rydberg states. So the Rydberg equation is a wonderful equation. And basically the only difference we need to go from hydrogen to many electron atoms or even molecules is to define an effective principal quantum number, which is not necessarily an integer. And the difference from the integer is called the quantum defect. And that's not a fudge factor. So using the quantum defect, which is really a phase, we can build a scattering model that explains everything. Now, one important thing about Rydberg series is that each series is built on a shape invariant innermost lobe of the orbital, where the amplitude along the series scales as the effective principal quantum number to the -3/2. I'm not going to prove this, but it's a wonderful exercise. So if you know the approximate ionization energy, you already start with an n-star scaled map of Rydberg state space. All of the energy level spacings from n to n+1 are predicted. And this n scaling of all matrix elements also predicted. Core non-penetrating Rydberg states, those with orbital angular momentum greater than 3, have nearly integer n-star values. And that's wonderful, because then you know a priori what the ladder of energy level spacings is. You don't have to measure it. And so this enables you to convert a simple laser or millimeter wave frequency scan into a double resonance experiment. Core non-penetrating Rydberg states are extremely sensitive to external electric fields, and core penetrating Rydberg states much less so. This is a useful trick in defining experiments. Now, after every laser pulse, an external electric field ramped can force ionization, and it forces the ionization in an independent way. And so one can look at successive n-star levels in a field ionization. So every experiment you do refines the value of the ionization potential and other things. As a result, all frequency scans, which take time, can be narrower, higher resolution, and richer in information. But it's a procedure which is well-defined and is highly interactive. One can get sub-megahertz precision in a ramp pulse field ionization short pulse millimeter wave spectrum. And Frederick Merritt has used this trick a lot, and I'm going to refer to him in several further transparencies. Okay. Every property of the H atom scales in the same way, and using the Rydberg equation. For one electron atoms, for one electron atomic ions, there's an extra factor of the nuclear charge. For many electron atoms, there is an L-dependent departure of the hydrogenic formula. And as a result, we have to replace integer n by the effective principal quantum number. And then this quantum defect is not a fudge factor. It expresses how an electron in the L orbital, partially shielded from the nucleus behind the centrifugal barrier, samples the nuclear charge or samples the nuclear structure. There is no centrifugal barrier for an s orbital, so the quantum defect for s orbitals is largest, and all higher L orbitals have near zero quantum defect. They're non-penetrating. The quantum defects along a Rydberg series are essentially independent of n. The amplitude of L equals 0 s orbitals inside the nucleus scales is n to the -3/2. They are going to be sensitive to the nuclear size. For molecules, it's more complicated, but it's basically the same idea. For molecules, one needs multi-channel quantum defect theory, which is expressed as a matrix equation. When n star is an integer, the regular Coulomb functions go to 0 as r goes to infinity. When n star is an integer, the Rydberg series is core non-penetrating. When n star is non-integer, the Rydberg series is core penetrating. Core penetrating and non-penetrating series respond very differently to an external electric field, which is really convenient. When n star is not an integer, the members of each lambda, m sub l, eigenchannel are an n star independent linear combination of L basis functions constructed so that all members of that channel go to 0 as r goes to infinity. So for different channels, one has different S character, and that's kind of neat. So barium fluoride, I've looked at a lot, and I know a lot about it. You don't want to know about that for me at this time. So the innermost lobe of the infinite number of members of any Rydberg series have the same shape and partial L characters, but scaled amplitude. This is the basis for all n star scaling in Rydberg land. 2 pi times the quantum defect is the phase shift for the NL orbital of a many electron atom relative to that for the corresponding NL hydrogen atom. Well, phase shift, doesn't that suggest scattering? And in fact, multi-channel quantum defect theory is a scattering theory. It's a scattering theory where we build a scattering matrix based on eigenstates, based on, as opposed to measurement of differential scattering observations. So again, we have this Rydberg equation, and we have a way of getting n star from 2 observable quantities, the ionization potential and the orbital energy. We know the energy difference between successive members of a series. It goes as 1 over n plus a half cubed. And the energy difference between 2 different states is given by the difference in the principal quantum number divided by the average of the 2 to the -3 power. All n prime matrix elements in Rydberg land scale as this combination of the initial and final n star values. Okay. Now, when we look at Rydberg states, state space is organized according to a priori known rules. And these rules are approximately valid, but strong enough so that one can use them to define a specific experiment. One thing that's very convenient in Rydberg land is that Rydberg transitions are almost perfectly delta V, vibration equals 0. There are electric field effects which are very different between core penetrating and non-penetrating electrons. Now, there was an area of spectroscopy called Ziki spectroscopy, zero electron kinetic energy. And this basically is due to the piling up of an infinite number of Rydberg states on different convergences to the rotation vibrationless level and to each rotational level. And so these are essentially an infinitely dense manifold of dipole coupled states. And so all you need is a tiny electric field and the electron falls off. One can do this purposefully by using pulsed field ionization, or even more purposefully by ramped pulsed field ionization, because then the electron falls off dependent on which, at different electric fields, depending on which L. Now, I should also mention that when you have two states of different L that are nearly degenerate, it doesn't take much electric field to polarize them. And as a result, one has, in a diatomic molecule, everything that you ever wanted from a linear triatomic molecule or a polyatomic, an asymmetric top. You can have as much dipole moment as you want. So we want to use these things to devise two-question experiments. But the first question, which I don't know how to answer, is we have this unusual situation that the ionization energy of barium fluoride is smaller than the dissociation energy. Now, in almost all of the other molecules earlier in the periodic table, this is not true. And when predissociation occurs, you wipe out all of the high N star Rydberg states, or even moderate N star. And so one can't use these Rydberg states to get as much information as you would like. So is it true? And I think it is. I think for the actinide fluorides, the ionization potential will be less than the dissociation energy. But I think that there needs to be some experiment and some rules about how this behaves. So I'm going to propose a new class of experiment, which may actually be impractical, but other similar experiments can be devised. So we want to be able to detect on-resonance production of radium fluoride ions or electrons. Now, Rydberg spectra are highly redundant. You can go anywhere you want in state space, and basically in an n to n+1 region, every Rydberg series is represented once. And so if there's a convenient region for the kind of spectroscopy you want to do, or the kind of property you want to measure, exploit this incredibly redundant and convenient organized state space. Rydberg states at very high principal quantum number can be extremely long-lived. And so that means you can do all sorts of things to them, and then they will report whether you succeeded or not. So many microseconds. And laser pulses are 10 nanoseconds long. You can do many, and you can do all sorts of clever things, and you can use chirp pulse microwaves. Okay, and one potential complication is vibration changing transitions. And that is not an important thing in Rydberg land. Okay, now this is a specific proposal, and it may be stupid, but it's the best I could do in the time available. So we've already got some high resolution or rotationally resolved spectroscopy of the A doublet pi state, and not yet of the C doublet sigma state. One wants to prepare the lowest possible rotational level because that leads to a relatively simple Rydberg structure. So if you excite to 100 wave numbers below a crudely known ionization potential, 100 wave number electron binding energy corresponds to n star of 33. The n 32.5 to 33.5 energy range is 6 wave numbers. And that corresponds to 200.03 or 1 gigahertz wide resolution element. So it's not a ridiculously complicated thing to scan with a tunable laser. One could do 2 scans, one at DC field of 0, and the core non-penetrating states will be absent, and one at 1 volt per centimeter, and the core non-penetrating states will be present. 1 volt per centimeter is very small, and maybe there are a lot of stray electric fields due to the dirtiness of the source, and that could be a flaw, but one can simply go to lower principal quantum number, and then the stray fields will be less of a problem. In this 6 wave number scan, all Rydberg series will be sampled once, and the core non-penetrating states will lie close to integer n star. And we can detect the different states by the n star and L dependent ramped pulse field ionization. Okay, here's a slide which illustrates this, which I've taken from a wonderful paper by Frederick Merritt, which has basically everything you need to know to use Rydberg spectroscopy to ask questions. And so what it shows is on the top right, we have a stepped scan of field. And at each step of the field, there is a signal which is associated with that step of the field. And so one can then, if you do this scan, this ramped segmented scan, one can, by scaling one's, gating one's detection for each step, one sees resolved peaks. Okay, this is a complicated looking thing, but it shows the Stark states. If you look at the top left is just showing how an electric field creates a maximum, a point at which ionization occurs, a big arrow. And the lower left shows what are called Stark states, and it shows that the lower L states, the P and D states, are not members of the Stark manifold until moderately high electric field. And this is sort of the map of how you do this sort of stuff. Okay, I'm concluding. Rydberg states encode scattering of electron partial waves by the ion core. S waves uniquely have amplitude inside the nucleus. Scattering is represented by a scattering matrix which depends on L and lambda, L and L prime and lambda and lambda, and no, not L and L prime and the same value of lambda, which is derived from an MQD fit to observed and assigned eigenstates. Isotope shifts of the SS scattering matrix element will sample nuclear size effects. I'll say that again. Isotope shifts of the SS scattering matrix element will sample nuclear size effects. The isotope dependence of scattering, all of the scattering matrix elements of heavy atom systems have never been measured. One can look at the P and D dependence of these isotope shifts and isotope and hyperfine effects. The redundancy of the Rydberg dataset makes it possible to focus on information-rich, a priori selectable regions of state space. So if you know what you want to measure, you can use a map of state space and scaling ideas, and you can get what you want. So again, I will remind you that the transition moments between the nearly degenerate core non-penetrating Rydberg states are greater than kilotopi already by N of 40 And so that this makes the core non-penetrating Rydberg states super sensitive to external electric fields. You can use ramped pulse field ionization to reveal the N star L structure of energy regions 100 to 1,000 wave numbers below the ionization limit. Okay, now I have some important references to tell you about. Gallagher talks about Rydberg atoms and with a lot of stuff that can be extended to molecules. There is the paper from which I've taken two figures is an incredibly informative thing, and it should be another map for how do you do experiments. Now, Frederick Merkt is part of the group that has looked in detail at the Rydberg states of H2, and they use this to measure the charge radius of the proton. Jakubak and I have looked at core penetrating Rydberg states of barium fluoride and at Rydberg at core non-penetrating states of barium fluoride. So there's somewhat of an experimental foundation for looking at the Rydberg states of barium fluoride. My former student Jeff Kay, Christian Jungen, Steve Coy, Brian Long, and I have built a complete quantum defect model for the core penetrating Rydberg states of calcium fluoride. This has never been done. And Frederick Merkt has written a paper showing how you use Rydberg state stark deceleration and trap to cool and trap atoms and molecules. So the idea of using the huge dipole moments, transition moments, but all dipole moment measurements are transition moment matrix elements to trap molecules. The last paper is, if anybody's interested in learning about MQDT, this paper is an extremely simple and a beautiful picture of what it is and why you need it. So I'm done. Thank you.
Timur, I think we lost our chairman.
Well, I'm here.
No, our chairman, Timur. But yeah, Robert, you can start with your question.
Yeah, thank you very much. Naively, one would expect that the nuclear size effects in those very high Rydberg states are a bit washed out, so that you are not so terribly sensitive towards it. Is this true or is this false?
It's false.
Okay.
The innermost lobe of any Rydberg orbital has an L structure, which is independent of N star and has the same shape and scales with the principal quantum number. The amplitude gets smaller, but it controls almost all of the dynamics.
Yes, so your argument is that the lobe is the more important factor and not the drop in intensity at the nucleus.
That's correct.
Okay. Yeah, thanks.
Sorry, I just missed the time actually. So I thought we have 5 more minutes, but okay, more questions. And I see, well, I don't see any questions. Okay. So now we have actually break.
So there are some questions.
There are questions. I saw.
I have some questions. So can we measure hyperfine structure constant for Rydberg state?
I have not, but using chirp pulse millimeter wave spectroscopy, it would be possible to do that. And the problem is that technique requires detection of free induction decay, which is wonderful. It's multiplexed, but you need a lot of molecules in order to do that. And so in the beam of radium fluoride, there are never going to be enough molecules in one quantum state to use chirp pulse FID detected spectroscopy, but one can use chirp pulse ramped ionization detection spectroscopy, and it would be possible to measure hyperfine. Now, the Rydberg series converge on different hyperfine states of the ion. And so one could also use Rydberg spectroscopy to make high precision measurements of the hyperfine structure of the radium fluoride ion.
Okay, thank you.
I somehow don't see any slides.
No, I have a question, Timo. So if you allow me, then I will ask. Yes.
But there is something strange. I don't see slides. Okay, Orbit, you can ask questions. So.
Okay. And another question which I have is, of course, the highly excited Rydberg states, they have a huge dipole moment. What is the heaviest molecule which have been stark decelerated by Frederick Merck? Because I know that they are mostly into the lighter molecules like H2, methane, and stuff like this. Do you know offhand what is the heaviest one which has been stark decelerated in the Rydberg state?
I'm sure your impression is correct. He has not looked at heavy molecules.
But do you know what the heaviest is, which they have tried? So methane or CH5 plus? Or?
It's possible. I don't know.
Yeah. Because the naive idea I had is once you apply your field, then you strip off your Rydberg electron, right? And then the stopping is gone. So one has to be very delicate on this in order to be able to allow for a cooling then. And yeah, might be tricky to achieve for the heavy molecules.
Well, I don't think there's any difference between a heavy molecule and a light molecule in terms of using Rydberg states to slow the molecules. It is destructive of what quantum state you're in a Rydberg state, but you can use the dipole moment, the very large dipole moments in a single stage to basically stop these guys. And I think we need to have a conversation with Frederick to find out whether he thinks it's reasonable to even imagine stopping a molecule like barium fluoride or radium fluoride.
But I mean, for the normal stark decelerators, the mass of the molecule plays an important role, right? So if you talk to Stephen Hoekstra, who does stark deceleration on strontium fluoride in the electronic ground state, I mean, the heavier you become, the more modules and the more length of the deceleration line he has to build. So I'm pretty sure they will play a role, right?
It certainly does, but we're comparing 1 debye to 1,000 debye.
Yeah, sure. Okay, thanks.
Okay, I see a question from Shane.
Yeah, hi, really interesting talk. So my question's not just regarding the Rydberg states, but actually distinct states above the ionization potential, because these may offer the most sensitive route for us to actually measure radium fluoride this year. So my question is there any way of predicting kind of where these auto-ionizing states above the threshold might lie from a given intermediate state in the neutral molecule?
Yes.
And how easy or hard is it? Is it okay?
Okay, so as I said, Rydberg transitions are delta V of 0. But from the lowest state, which is somewhat different in molecular structure from all of the other higher state electronic states, one can excite different vibrational levels. And so one does the same thing on the multi-channel quantum defect theory predictions for a V=1 manifold. And so one can easily predict what the energy of the vibrationally ionizing state or higher rotational levels. Each rotational level will correspond to a convergence of states. And so Ziki-like experiments can be done to get the rotation vibration structure of the ion. And there won't be, for radium fluoride, there won't be an electronically excited state until very high energy. And so I'm not willing to make any predictions about detecting them, but basically getting the hyperfine rotational and vibrational dependence or positions, one can look at the different convergences of Rydberg series that you select at the beginning and then carry on to the high end. This
Okay.
requires, go ahead.
Okay, thanks. Yeah. Okay.
Okay, I don't see more questions actually or comments. And now we have a break. See, for I think for 15 minutes, right? Yes, for 15 minutes, and then we'll continue. Okay. Yes. So speakers can join breakout rooms, but I don't know which room has to join which speaker. But okay.
Oh, that's easy. Just do it in the sequence 1, 2, 3, right? In the order
Yeah,
of
1, 2, 3. First speaker is
so Leonid is 1, Konstantin 2, Svetlana 3, Robert 4.
Yeah, Leonid. So then you join room 1, Konstantin room 2, and Svetlana room 3, and Robert room 4. Oh, not Robert. Yeah, from. Oops. Yeah, from Robert. Yes, room 4. Right.
Okay.
Nick from MIT, can you set up the rooms again?
They are. So
Oh, they are.
rooms
Oh,
rooms are
perfect.
open.
Yeah, exactly. Wonderful. Okay.
Hi, Nick. Can we bring all back? So I think we are 2 minutes late and I didn't realize.
Sure thing.
Thank you. Yeah, Timur, you can start in 1 minute.
Sorry, when do we start and who is the chair?
The chair is Timur Isaev. Timur, you can guide.
You're muted, Timur.
Yeah. Timur, you are muted. Yeah. Timur? Timur, you are muted.
Ah, okay. Yes. Now can you hear me?
Yeah.
Yeah. And according to my schedule, which I have in front of me, we have to start at 35 minutes. So but we are 5 minutes late, right? Or something like this.
Okay. Yeah, I think people are coming back. Should I share my screen now? I guess
yes,
yeah,
please.
You can share your screen, I guess, and we wait for 1 more minute and then we start.
So can you see my
because
PowerPoint?
typically this breakout room, they are closed when main session starts, but for some reason in this case they were not closed. So okay.
Yeah, you can start.
So can you see my PowerPoint?
Right. Yeah.
Yeah.
Yes, we can see your screen, so we can start. And our next speaker is Roman Krems, who will tell us about the enhancing scattering theory with machine learning. So Roman, please, stage is yours.
Yeah, thank you, Timur, and thank you also to the organizers for giving me this opportunity to share with you our excitement about applications of machine learning for ultra-cold quantum dynamics theory. Now, I don't need to tell this audience that quantum scattering theory is critically important for ultra-cold physics. You know, we use scattering calculations to predict scattering lengths, to identify scattering resonances, to predict visibility of sympathetic or evaporative cooling, to understand collision losses, to explore ultra-cold chemistry and understand collisional decoherence, among other things. However, scattering calculations, and particularly scattering calculations at low temperatures, are quite challenging. And here's a list of some of the challenges that we have to work around when we do numerical scattering calculations for ultra-cold systems. Well, first of all, despite all of the progress with quantum chemistry that Svetlana has told us about, atomic and molecular collisions, you know, well, the interaction potentials that we can get from quantum chemistry calculations, they're still not accurate enough to make predictions of atomic and molecular collision properties with precision that we require. And that's because atomic and molecular scattering are extremely sensitive to interaction potentials, and even, you know, accuracies on the order of 1% that Svetlana has been telling us about. A lot of times is not sufficient for many of the applications in ultra-cold physics and our chemistry. So the other thing is that external fields that we often have to include in the scattering calculations, they're non-perturbative in this regime of atomic and molecular interactions. And this complicates the scattering problem to a great extent. So this makes, this requires a large basis set for converged calculations of molecular dynamics. Now, if we want to extend scattering theory of ultra-cold systems to bigger systems, polyatomic molecules, we would like to be able to treat this kind of calculations using the time-dependent formalism, but time-dependent quantum dynamics calculations are difficult to apply to ultra-cold systems. It's not impossible. You know, I should probably mention that we had a paper a couple of years ago where we showed how to perform time-dependent scattering calculations in the ultra-cold temperature regime, but it's actually quite challenging. Now, a lot of times, for many of the applications of interest to this group, one needs to solve the equivalent of inverse problems. For example, we often use measurements of resonances to determine scattering lengths or bound state energies to determine fine and hyperfine structure couplings, etc. And inverse problems are quite challenging, especially for complex molecular systems such as the John-Dole kind of molecules. Okay, now for these kind of molecules, even the direct problems are quite challenging. And again, the problem goes back to the difficulties of obtaining accurate potential energy surfaces that describe interactions of atoms and molecules. Okay, so like I said, potential energy surfaces, they always come with errors. And one of the greatest challenges, when it comes to the theoretical analysis of atomic and molecular interactions at very low temperatures is how to determine the effect of errors in potential energy surfaces on predictions of dynamical observables. So a lot of times when we calculate dynamical observables, we want to be able to calculate the error bars associated with uncertainties of the interaction potentials. And a common practice in the field is to vary the underlying potentials by a scaling factor, by simply scaling the underlying potential energy surfaces. But this does not account for errors in the anisotropy of the potentials, neither for the fact that the accuracy of the quantum chemistry calculations is going to be different at, say, long range than it is at short range. So what one requires is analysis of scattering observables as functions of both the strength and topology of potential energy surfaces. Okay, and this is particularly important for polyatomic molecules because the interactions between such molecules are quite complex. So now inverse problems are of course even harder when it comes to this kind of complex species, because these are high dimensional problems. So the interactions between polyatomic molecules in general are high dimensional. And a lot of times, inverse problems for molecular systems like these ones are considered unfeasible. Okay, so what I will try and show today is that and how these kind of challenges can be addressed with machine learning. Okay, so to begin with, let me outline our approach. Now, the traditional approach to quantum dynamics will always begin with electronic structure calculations that will produce potential energy surfaces that will be used along with other parameters relevant for experiments such as energy, angular momentum, external fields as input into the Schrödinger equation that you would solve to, for the dynamics problems to obtain observables. Now we're going to modify this traditional approach by treating all inputs into the Schrödinger equation as machine learning models. And we're also going to treat the output of the Schrödinger equation as a machine learning model, okay? And in particular, what's important, it's actually quite important for what I'm going to talk about next. So these machine learning models are going to be non-parametric probabilistic models, okay? Now, if you do that, what you get on output are machine learning models that are functions of other machine learning models that, again, model the inputs into the Schrödinger equation. And then you can use that to, for example, solve inverse problems that I've mentioned. And I'm going to talk more about this a little later. Okay, I guess one way to think about it is that unlike the traditional approach that treats atomic and molecular dynamics as evolving on a well-defined pre-computed potential energy surface, our approach treats atomic and molecular dynamics as evolving on a non-parametric series of potential energy surfaces that is conditioned by observables. Another way to look at it is like this cat walking on a series of potential energy surfaces, and now you throw observations at the cat, and depending on what the cat sees, it will choose one or the other of the potential energy surfaces to walk on. Okay. Now, much of machine learning that you've probably heard about is done with neural networks, and I've got a picture of a very simple neural network up here. Now, neural networks, they require big data to produce accurate models. And a lot of times they're also quite challenging to train. Like if you go through the literature on neural networks, it's not uncommon to come across quotes like this one that says that suffering is a perfectly natural part of getting a neural network to work well. Now, in physics, data come from the solutions of complex equations or from experiments, which could be quite time-consuming. So I would argue that in physics, data are expensive, and the focus should be on making physical predictions, with machine learning based on small data as opposed to big data. Now, if this is the goal, then deterministic neural networks cannot be used for such problems. Okay, but then there's another way to make predictions in machine learning, and that's probabilistic modeling, which is at the core of Bayesian machine learning. I'm going to tell you a little bit about this before we move on to look at the results. So probabilistic modeling basically uses distributions of random functions like the one depicted here to build models of data. And this kind of distributions, they can actually be produced with neural networks. If you take a neural network like the one depicted here, a deterministic neural network, and you make it a probabilistic neural network by promoting all of the parameters of the neural network to random variables. So if you do that, and then of course the output of the neural network is going to become a random function, okay? And this is what I'm plotting here. I'm plotting the distribution of outputs of such a neural network with parameters of it all treated as random variables. So the problem I guess the goal of probabilistic modeling boils down to conditioning this distribution by the data points represented by the red dots here. So what you want to do is go from a distribution of white these gray curves, functions represented by the gray curves, to something like this. Okay, so that's going to be the model, the goal of building the models that we're going to look at. Okay, so yeah, again, what you want to do is go from something that's depicted on the left here to something that's depicted on the right here. And this is done, with the help of the Bayes theorem, and that's why it's called Bayesian machine learning. But we're not going to talk much about that. Now, if we go back to the neural network that I showed you at the beginning of this discussion and make the number of hidden neurons in that network very large, this actually simplifies the problem, because the Bayesian neural network then becomes a Gaussian process. And what a Gaussian process is, it's actually a random distribution. It's a normal distribution of such random functions. In other words, like if you take this distribution and cut it in the perpendicular direction, you're going to have a normal distribution of values. Okay. So now Gaussian processes are a lot easier to work with than Bayesian neural networks in general, because they're completely determined by a mean function and a covariance function that describes the covariance between Gaussian, these Gaussians evaluated at different positions of the input space here. Okay, and the covariance function is also going to be called kernel function for the rest of my presentation today. Now, choosing the proper kernel function, choosing the proper mathematical form of the kernel function is going to be key to the performance of the models that we're going to build this way. Okay, and unfortunately, I don't have time to tell you how exactly we do this, but I'm going to refer you to these papers that basically describe the algorithm that we use for all of the results that I'm going to show you today to build the best kernel functions. So the results that I'm going to show you today, they rely on the algorithm that is described in these papers, and there's other papers that discuss the algorithm, but these ones are the key references. Okay, so now if you follow the algorithm that I mentioned, then you can build Gaussian process models. You can build these Bayesian models that are extremely efficient. And to illustrate this, I'm going to consider a reactive scattering problem. It's a molecule, a diatomic molecule interacting with an atom, to produce another molecule and another atom. So basically, a chemical reaction that typically evolves on a potential energy surface like this one. And And the question I'm going to ask is, how many potential energy points? What is the minimum number of potential energy points that one actually needs to know to describe a chemical reaction such as this one? Okay, now typically what we do in the traditional approach to a quantum reactive scattering problem like this one, we would calculate this potential energy surface at something like 10,000 points in this three-dimensional configuration space. We would fit this potential energy surface with some analytical functions, and then we would solve the dynamical, the quantum reactive problem, the scattering problem on this potential energy surface. Okay, now what we're going to do within our approach, we're going to treat it as an inverse problem. So we're going to, again, ask the question, what is the smallest number of ab initio calculations of quantum chemistry calculations that I need to produce a potential energy surface like this one to get the same dependence of the reaction cross sections on the collision energy as by the previous authors in the literature. Okay, and I'm going to solve this problem by this sort of a feedback loop. Again, you can refer to my earlier, illustration of a cat walking on those potential energy surfaces. So each iteration of this feedback loop is going to be producing one set of observables that I will be giving to that cat, and it will decide basically how to modify the potential energy surface to yield the desired result. So the black curve here is shows the dependence of the collision cross section. So this is the cross section for the chemical reaction, and this is for the H plus H2 reactive system. So that's the dependence of the reaction cross section on the collision energy. The black curve is taken from the previous calculations by other people, and this was produced using an analytic fit of the potential energy surface based on 8700 ab initio calculations. Now, if we use the approach that I just outlined, so we need 30 ab initio calculations. So, and this is just to illustrate the efficiency of the machine learning models that I briefly described. So basically, what this is saying is that you only need 30 quantum chemistry calculations placed, somehow in this three-dimensional configuration space to describe completely the reactive scattering problem. Okay. All right. Now, again, if our goal is to describe the dynamical problems involving complex species like the John Dole kind of molecules, so this is a problem with a high dimensional Hamiltonian. The configuration spaces for this kind of molecules are going to be very high dimensional. And again, we want to solve, we want to address this kind of problems with very few quantum calculations. Now, to do that, we need to be able to solve extrapolation as well as interpolation problems. And the kind of extrapolation problems I'm talking about are problems that extrapolate in the Hamiltonian parameter space. So you can think of a quantum problem in the space of the Hamiltonian parameters. And what we want is build models that take what we know or what we can calculate for the system of interest in some part of the Hamiltonian parameter space, and we want to be able to make predictions of the properties of the system in some other part of the parameter space. Okay, and to illustrate that this is actually feasible and it works with the kind of models that I've introduced, let me consider a problem from condensed matter physics. There's a couple of problems from condensed matter physics that we looked at in this Fizerev ladder. And so, but the particular problem, so the goal of this analysis was to see if we could consider a problem with multiple quantum phases, and if we could build models that would take on input the information about the properties of the system in one of the phases, and would produce would predict the locations of the phase transitions and predict the properties of the system in other phases where you don't have any calculations or measurements. Okay, so this was the problem that we addressed in this paper, and I'm going to show the results for two systems here. So the first one is the Heisenberg spin model, that can be solved exactly in the mean field approximation. So you can calculate in the mean field approximation, you can calculate the free energy of the system as a function of temperature and magnetization, and it looks like this. So, as you look at the free energy as a function of temperature, there's going to be a paramagnetic to ferromagnetic transition at some critical temperature. And we wanted to see if you can take the free energy of the system in one of the phases on input and predict the location of that phase transition, as well as the free energy of the system in the other phase. And this is the graph that illustrates how well it works. So the dashed curve here is basically what it shows is the minimum of the plot on the left here, which is the order parameter. So it's the order parameter as a function of temperature. And so we train the model by the free energy in the shaded region here in one of the phases. And then we let the model predict the properties, the free energy of the system at temperatures below this point here. So the dashed curve here is the mean field calculation, and the symbols here are the predictions for the machine learning models that we thus build. And as you can see, the machine learning models can predict both the location of the phase transition as well as the order parameter deep into the other phase. Just to give you another example, this is for a generalized Polaron model that describes an electron coupled to phonons with two kinds of couplings, one that modulates the potential energy of the electron and one that modulates the kinetic energy of the electron. And so in some of our earlier papers, we showed that if you look at the ground state of such a Polaron, it will exhibit two sharp transitions as a function of the Hamiltonian parameters. And these transitions are shown by the dashed lines here. So these dashed lines are the numerically exact quantum calculations from our earlier work. Okay, so now what we wanted to see in this work is whether we can build machine learning models that would take the properties of such Polarons in one of the phases, like the properties calculated at the positions of this parameter space shown by these dots here, and whether such models can predict the properties of the Polarons across the entire phase diagram. And as you can see, so the color map here is the prediction of the machine learning model, and as you can see, the models predict both of the phase transitions and it can describe the properties of the Polarons deep into the other phases quite well. Now, again, just to emphasize that it's not trivial to build these sort of models. You really need to follow the algorithm that I don't have time to explain today. It would take me more than half an hour to explain how it works. The algorithm that I mentioned, that we described in the papers I showed you earlier. So if you don't follow that algorithm, and if you just simply use kernel functions with the same complexity chosen at random, then you would get something like shown on the right here, which is complete garbage. So basically, the bottom line of this is that choosing better kernels not only makes extrapolation problems possible, but also allows models to extrapolate further. And I'd like to say that choosing better kernels is like replacing spectacles with binoculars when it comes to exploring quantum phase diagrams. Okay, I'm going to show a few more examples now. I'm going back to molecular systems here, and I'm going to show you a few more examples very quickly. So this is an application to the extrapolation of potential energy surfaces for molecules like H3O+. It's a 6-dimensional system, and what we did there, we built machine learning models trained by the potential energy of the system in the shaded range of energies here. And we let the models predict the energy of the system in the entire configuration space, including at energies above this range. And so again, the original surface is represented by the symbols here, and the machine learning prediction by the line here. And as you can see, there's a perfect agreement between the predictions and the original surface, even outside of the range of the training data. Okay, so what about higher dimensional systems? So let's look at a molecule that has 51 degrees of freedom. This one here, and again, a similar calculation that produces, machine learning models of the potential surfaces, trained by ab initio calculations in the shaded region here, and so anything above the shaded region is the comparison between the model predictions represented by the squares and the original ab initio points represented by the symbols here. So this is basically very efficient in interpolation and extrapolation of potential surfaces in a 51-dimensional configuration space. Okay, so now what this allows us to do is compute things that we couldn't imagine just a few years ago. For example, we can calculate wave functions of these polyatomic systems like H5O3 minus, with extremely high precision, like for example at the MP2 quantum chemistry level. And my student estimated that if you were to do this kind of calculations on the fly, it would take a single core of the computer. He was using 220 years, and this approach that we're introducing here allowed us to do the calculations in just 8 days. Now, how much time do I have? Not much.
You have 1 minute.
Oh, okay. So I just wanted to say that the same models can be used for transfer learning. I'm not going to say how, but again, so this could be used for applications that aim to improve the accuracy of approximate quantum dynamics calculations. And I guess I should refer you to this paper here that discusses this in more detail. And this is, again, particularly relevant for high-dimensional quantum systems, because for such systems, we always have to use approximations. And a lot of times, we don't know the errors of those approximations. So you can build models that actually learn the errors of the approximate approaches and then correct for the deficiencies of quantum approximations. And this is what's illustrated, on this slide here. Okay, since I'm out of time, I'm gonna wrap up by saying that what I've tried to show you today, well, I guess we all work on quantum problems that take Hamiltonian parameters on input and produce some observables on output. We all work on this kind of problems, whether theoretically or experimentally. So what I try to show you today is that we can build models that can interpolate and extrapolate very efficiently in multidimensional Hamiltonian parameter spaces. We can also build models that improve the accuracy of quantum dynamics calculations, as well as models that allow us to deduce the parameters that go as inputs into quantum problems from the observables produced either in experiments or by theoretical calculations. So if you're working on one of these problems and you'd like to see how our approach could be used to help you, please, by all means reach out. I'll be happy to discuss this further. Well, this was on the cover of PCCP that basically illustrated our ability to extrapolate quantum problems as well as to solve inverse quantum problems. Some of the key references, maybe just to mention the names of the students who did the work. Jie Tsui was one of the graduate students who started much of this effort, and Rodrigo Vargas Hernandez was another key player in this. So I'm going to stop here and take your questions. Thank you very much.
Thank you, Roman, for a very interesting talk. So are there questions, comments? I don't yet see questions, comments. So may I ask you just, perhaps it's a stupid question because I am quite novice in this field, but in the core of your approach, there is neural networks, right? So you are teaching neural networks how to deduce desirable parameters, right?
Yeah, Bayesian neural networks, that's right.
Yes, but there are different neural networks. So there are different types of neural networks. So which type of neural networks you are using?
Yeah, that's why, I didn't have much time to explain this properly. That's why it's important that we use non-parametric Bayesian models. So basically, if you have a neural network like this one, and you take the number of these hidden neurons to infinity, and you make the parameters of the neural network, all of the parameters, you make them random variables. Then the problem simplifies significantly. Then the problem doesn't really depend on the architecture of the neural network anymore, because whatever you produce on output by the central limit theorem is going to be a Gaussian distribution for a given set of inputs here. So the architecture of the neural network doesn't matter because, like I said, if you make this neural network very big, it becomes a Gaussian process. And then, much of the algebra involved in, I guess, in training this sort of models can be done analytically as opposed to numerically. And that's what makes, I guess, Bayesian machine learning feasible and practical.
Okay, thank you. And I see a question from Mariana.
Thank you for such a very interesting talk. So how general are those kernel models? For example, if you can build them for one molecule as applicable for the other ones. We've been interested in application of machine learning for complicated atomic physics structure, but
that's right.
I couldn't find really nothing in the literature to see how portable those things are.
Yeah, thank you, Mariana, for this question. Like I said, I wish I had time to explain this in detail. So the way we build those kernels is completely general. So most of the people in machine learning, they will choose a particular kernel function that would be like a simple Gaussian or something like that, and then they will build models based on those kind of simple functions. So now this is not what we do. I mean, like we can't, in order to do what I presented today, we actually need to build much more kernels. And the way we do this, we start with a bunch of functions as a basis set, and then we combine those functions into more complex functions through an iterative approach that increases the complexity of the kernel functions one step at a time. And we use a tree search approach that selects the appropriate kernel function at each step of this process using the so-called Bayesian information criterion. So I guess, I don't know if what I'm saying makes any sense to you, but the bottom line is that this approach is completely general. It's going to produce a different kernel function for a different problem. Like for each specific problem is going to be best described by a different kernel function. And but this approach is going to produce the most appropriate kernel function for your problem.
So, for example, if your kernel is to produce, let's say the properties, certain properties of type of molecule, it will work for different molecules.
It will definitely work for different molecules. Yeah. So I mean, like, it's completely general. So I mean, like we're going to be using the same code. Like if we want to say fit a potential energy surface for a molecule, so we're going to be using the same code for example, for methane and aspirin. Okay. So so the kernel that's going to come out of this is going to be completely different. I mean, like the dimensionality of the problem is going to be completely different, but the code is going to be the same. Okay. And again, what makes this feasible is the fact that we're using non-parametric models with adjustable kernels, and the kernels are built, like I said, in a general iterative approach that uses simple kernels used by everyone else as a basis set.
Thank you.
Thank you. So I see a question from Makoto.
Hi. Well, thank you for your nice talk. I'm actually really impressed. Well, first of all, I'm not an expert in this field, but I mean, I'm completely impressed by the fact that you can predict things like a phase transition from this technique. And I'm just wondering, I mean, apart from solving this Hamiltonian problem. Can you use this technique for other field of machine learning, for example, data analysis for particle physics experiments where you may have a limited data set, but you want to estimate the mass of some parameter or extract background from signal? Is that how general can your technique be applied to other stuff?
Yeah, absolutely. I mean, that's why I'm excited to present to this group, because what we're doing is completely general, and it will work for anything that is not white noise, right? And so we should talk if you have a particular problem in mind. But yeah, so I'm particularly excited about applying this to experiments. Again, if you have a problem where you have basically a bunch of parameters that go as input into your experiment to produce some observables, and you, for example, want to optimize these parameters, we can tell you how to optimize those parameters in the most efficient way, for example. Or if you want to deduce those parameters from given observables, again, we could tell you how to do this with very few observations. So where this approach is the most valuable is the limit of a very small number of observations, because if you have a lot of observations, then it becomes, then it's easier to treat this as a big data problem. And for that, there are well-established approaches. But if you have, like say you have a 50-dimensional parameter space, you have a 50-dimensional Hamiltonian, or another way to look at it is you're interpolating between different Hamiltonians, right? You have multiple Hamiltonians, and you have, like, say, 100 experimental observations. This is the kind of problems that this is the most suitable for.
Okay, thanks very much.
Okay. So thanks a lot. I don't see further questions and comments. Okay, so we can now go to the next talk in our session, and this talk will be provided by Mariana Safronova, and the topic is Clock with Radioactive Species for New Physics Searches. So Mariana, please.
Can you see my screen?
Yes.
Okay, so thank you so much for the invitation. It's a pleasure to give a talk here about clocks and the applications, specifically with actinides. And first, I would like to mention what do I mean by new physics. And you already heard many of those big fundamental questions about the universe at the workshop. Just to summarize, we have a lot of problems, but some of the main problems that we have a lot of missing matter. We definitely know that it's missing, as we have plenty of observational data on all scales, but we have no idea what it is. Then we seem to be universe is expanding at acceleration rate, and that's what we label as dark energy. And again, we have no idea what it is. In fact, we know even less about dark energy than about dark matter. Most likely, if you have missing matter and missing energy, you probably have missing fundamental interactions. For example, if you want to couple your dark matter to a standard model, most likely it's some different sort, particularly force which you can generate. And then, of course, the big question which was discussed in this workshop, it's matter-antimatter symmetry universe. And I'll talk a little bit about hierarchy problem. So why is the masses of known particles so much lighter than fundamental energy scales? And it's a really big problem. So while we can't answer all of those with atomic clocks, I will talk a little bit about how we approach those two. So first, why atomic clocks? Frequency, it's the best measured quantity in atomic and molecular physics. So if fundamental constants, for example, change due to some unknown new physics effect, and we can technically try to distinguish which new physics effect specifically we are looking for, then in many cases, the frequency of atomic transitions or molecular transitions will change. And the clocks at this point are so good, we understand systematics to a very, very high degree. And that's really the main point here, that the standard model signal in clocks is understood at the level of clock precision. So the fundamental standard model systematics is understood to 80 significant figures in those clocks, and it will be understood even better. So essentially what we're looking here, it's some sort of unknown physics effects, this unknown systematics which will change the frequency of the clock. And you may ask, okay, let's say your dark matter changes the frequency of the clock, but how do you know it from a bare frequency? And the important point here that it will affect different clocks differently. In many cases, the clocks based on lighter elements will actually have no effect, but clocks based on heavier elements would. And because many of these cases have relativistic enhancements. And for example, clocks with holes in F shells would actually be more sensitive to some effects than others. Clocks based on highly charged ions, nuclear clocks, will again have different sensitivities. So before going into how we would use dark matter to solve, how we'll be searching for dark matter with clocks, let me just show one slide of how clocks work. So there are 3 parts to your clock. Well, there are more parts, but from fundamental level, there are 3. So you have your atomic reference. So what your atom or ion does, it's to provide a perfect oscillator. So those atoms will oscillating in the same frequency for the same transition in the same environment, always into the presumably end of the universe. And what we need to do is to be able to build a device, a laser, which can be tuned exactly at that resonance. So, and then from this point of view, your clock actually works as a tuning instrument. So you have your laser, you tune it to a certain frequency, you tune it a little bit more and see whether atomic transition become more probable, less probable. So what you actually measure, it's a population of atoms here. And generally, your clock will operate, you put things in position of zeros and ones, and then you have another rotation, which then allows you to actually determine the phase and how much do you think you need to adjust your clock. And then you adjust your laser, and then you do repeat and repeat and repeat. And then you'll be able to get this curve of excitations. And that allows you to essentially determine what is your perfect frequency is. Then you lock your laser, and you actually count your frequency with another laser, which is optical frequency count. The great scheme here is that you do not actually need an absolute frequency standard to compare to clocks. So you can compare two clocks independently on cesium completely, than comparing them to the same frequency count. And that's our basic instrument here. So when we search for physics beyond the standard model with clocks, it's all started with looking whether fundamental constants are actually constant. And then several years ago, it was realized that dark matter itself can source variation of fundamental constants in either oscillator, transient, or perhaps stochastics variations. Then the test of equivalence principle can be done if you remember that our orbit of Earth is actually elliptical, or in fact, if you actually send the clock to space. And then searches for violation of Lorentz invariance turn out to be that clocks provide the best limits in the electron sector for those, and actually a very competitive limit for the photon sector as well. And then there's been a recent number of proposals of gravitation wave detection with both atomic clocks and atom interferometers. And in some of, at least one of them I heard, it's very sufficient to actually use atomic clocks at the current precision. If you talk specifically about dark matter searches, then the main question we would like to answer, which specific type of dark matter can actually affect the atomic energy levels? Because that's our observable here. If our clock frequency change, that's how we can actually look for dark matter or other fundamental physics. And here is the main question is which new particles, okay, those not necessarily have to be dark matter, could contribute a bit to dark matter, or it could be 100% dark matter. Can you detect, if you measure changes in atomic nuclear frequencies to say 18, 19, 20, or how optimistic you are digits? And there's really no fundamental limits at this point, within next few orders of magnitude of how precise technical clock can be, except that we actually get increasing dependence on the environment which you have to control, or actually you can turn it back and measure the environment with clocks. And of course, the bonus question which we want to answer, can our new particle also solve some other fundamental questions? And that's why, for example, a dark matter scenario for WIMPs was so powerful, because it always solves the hierarchy problem. Of course, since we haven't seen WIMPs and the LHC haven't found supersymmetry, that becomes more and more problematic. But that's kind of your best dark matter also solves some other problem, like axions do, for example, solve a strong CP problem. So can we actually have a dark matter which you can see with clocks, which also solve a fundamental problem? And the answer is yes here. First, when we talk about dark matter searches, let's be clear what we're actually observing. We are going to assume, and this is from our galactic observations, this is the right assumption, that there is a large hail of dark matter right here. So we're sitting in a hail of dark matter. And just because the sun is moving through this hail of dark matter, which for all purposes things stationary, with about 300 kilometers per second together with our sun, we assume that we essentially facing our dark matter wind. It will depend a little bit on the time time of the year, but this is dark matter we are detecting. We are not producing it, it's just here. I mean, in this cup, you're going to have your dark matter, and that's what we're detecting here. And then the next question, which type of dark matter can we detect? And here we actually look at parameters such as, is it a scalar, is it a pseudoscalar, is it a vector, what's its mass? And this mass answer is clear, it has to be ultralight. So anything which we be detecting with clocks would be actually a very, very light type of dark matter. And there have been other proposals, but I will talk now, for now, about the ultralight part. And when we look at the characteristic frequencies here, so we look at somewhere below 10 to the minus 12 electron volt, and I'll show why specifically this is a good idea, because it actually corresponds to characteristic probe time of clocks. And if you look at the lightest limit, generally people put 10 to the minus 22 electrovolt for something which could be 100% dark matter, just because that defines by a size of the smallest possible dwarf galaxy. The first thing which we know about ultralight dark matter, it has to be bosonic. Because if fermionic dark matter would have left our galaxy a long time ago, it cannot actually bind. Its escape velocity, its Fermi velocity is higher than our galactic escape velocity. So we're pretty sure that it has to be bosonic. And if it is bosonic, then the next question is, how many of those particles do we actually have per de Broglie volume? And the answer is a lot. So essentially, we're dealing with very large occupational number as soon as we move to the, below the EV scale. And then if our de Broglie volume actually have many of those particles, then it makes no sense to try to detect the dark matter as a sort of scattering of billiard balls on other particles. We're talking about really coherent dark matter wave here. And what we have, it's a cosine function. One here is dark matter mass, and here it's a bit spread of dark matter just because there is a spread of velocities. Here is a basic idea of why do we think it's possibly detectable with clocks. Let's say dark matter field, and we are going to say it's going to couple the standard model. And it's a good question whether it should or should not couple the standard model. But if it's been produced somehow by some sort of standard model interaction, therefore it should be detectable the same way. So unless the dark matter was actually produced gravitationally, it should talk to standard model. And here are the types of dark matter which we're looking at, which could talk to standard model. So then our dark matter field, let's say it's coupled to electromagnetic interaction and to normal matter like electrons and quarks. Then what's going to happen, I'll show you why it's going to happen, that it will make fundamental coupling constants and mass ratio oscillate. The simple idea, you take a standard model Lagrangian and you multiply it by an oscillating term. And that produces extra oscillating terms in all Lagrangian terms, which all define fundamental coupling constants and mass ratios. Let's say now, fundamental coupling constants such as alpha, fine structure constant, will oscillate. So what does it happen to do to atomic energy level? Well, they all proportion to Rydberg constant, and Rydberg constant has is fine structure constant. So therefore, if fine structure constant oscillating, then atomic and nuclear energy level will oscillate. Therefore, the clock frequency will oscillate, and therefore, all we have to do is just sit and watch our clock for a long time. And how long is a long time? It's debatable. It depends on what's your dark matter mass and how long dark matter remains coherent. But generally, you monitor this ratio of clock frequency, from days to years. In this case, depending on what dark matter mass would you actually look at. And those type of detectors are broadband, but if you have some possible detection signal, you can actually make it resonant. And here are the current limits. So those current limits for this oscillating dark matter bounds. The purple line is the microscope mission in space. It's the classical mission equivalence principle test. And then you have dysprosium bound, rubidium, cesium. And then you also have the most recent strontium and silicon to hydrogen limits as well. And then green ones are projected strontium silicon cavity limit. And in this case, you don't actually compare it to clocks. You can compare a strontium clock to its own laser cavity, just because it's so extremely ultra stable. So the main question here, how do we actually move many orders of magnitude more here? And as optimistic as we all are in how the clocks will progress, we expect maybe another orders of magnitude in, say, 5 years. The question here, can we actually do, say, 6, 7 orders of magnitude better in 10 years? And surprisingly, the answer is yes here, even though we're probably not going to improve clocks by 6 orders of magnitude in years, but we can build also different clocks. So the question here is then which new systems do we want to use? And this is also defined which specific types of dark matter we want to look at. And as I mentioned, there is this bonus question, can our new particle also answer some fundamental question? And here is actually a very interesting point that you can potentially answer as a hierarchy problem with ultralight scalar potential dark matter. And let me delve a little bit about what the problem actually is. So the Higgs field vacuum expectation value is small. So its average value at the sort of GeV-ish type scale. And let's say this is not natural. So if you actually try to model our universe from some sort of initial condition, what you will normally end up with is Higgs field is fully on, and then all particles at Planck mass scales, and it will turn into black holes, so no our universe, or Higgs field is off, and then there are no masses, again, no our universe. And mathematically, it's actually very simple to see what the problem is. So the Higgs is a scalar, so the first correction which you make, the first obvious loop which you can actually draw with, say, top quark results in quadratic divergences and puts Higgs mass back to Planck scale. And in this case, also besides top quarks, there are many other corrections. So for them to completely cancel out, to produce such a unique universe as ours is, it looks very weird. So the idea is maybe there's some sort of symmetry which protects it. And one of the most durable ideas was supersymmetry, and then there are also some different electroweak symmetry break-ins, little Higgs. And the problem is that no TV scale physics have been found so far, and it's been very puzzling. So one of the other recent ideas is dynamic relaxation. And in this case, you actually have its main feature being ultralight scalar particle, which is a relaxion. And I will not go into the detail of how that works, but the basic idea that you actually have a coupling of the Higgs to this new main actor, the relaxion, and it dynamically relaxes the Higgs with respect to natural value. So the Higgs starts rolling down, eventually it will, there is a back action from between Higgs and relaxion, and relaxion stops the Higgs at some small value. And you can make this model natural. You can also make this relaxion being dark matter. And we recently collaborated with Gilad Perez's group to actually see which type of clock can actually look for it. In a parameter space of relaxion here in green line is actually pretty hard to reach. The previous limits which I showed, the strontium silicon, is like up there, about quite a few orders of magnitude up. But surprisingly, the nuclear clock, and I'll talk about this, actually can reach the parameter space. And one of the reasons, because nuclear clock actually provides coupling to the strong interaction coupling constant, as opposed to just electromagnetic one, which is actually also sensitive too. And that's what provides the best possible reach for this relaxion scenario. And in the case if you actually have some possible solar halos or relaxions around our solar system, the nuclear clock, of course, will be actually have even more super performance. Well, because then you'll just have more relaxions to detect them. How am I doing on time? Timur? Just curious, how much time do I have? Okay, I'll just continue if you.
Yeah, what's the question?
How much time do I have?
You have 10 minutes.
Okay.
Oh, no, sorry, you have even 15 minutes, I guess.
15 minutes, okay.
15 minutes. Okay.
Okay. So, and that we would like to move to the question, so how do we actually significantly improve those tests? And that's where those clocks with the radioactive species actually come in. It turns out to be that all the really very, very good ideas for this really new physics, clocks actually turn out to be coming with a radioactive species. So first, as I mentioned, you can improve clocks, and there's totally different talks how to improve clocks. But then the second one is build new dedicated clocks, which are very specifically selected to have very high sensitivity to variation of fundamental constants. So first, let me talk a little bit, what do I mean by high sensitivity to variation of fundamental constants? So different elements would have different sensitivity to alpha. So all of the atomic transitions, of course, will be sensitive to alpha squared. The question is how much on top of the alpha squares do we actually get? And the answer is not much. So the answer for all the current clocks, just because most of those are neutral systems or singly charged ions, and most of them have electron about at the same space from the same radius from the nuclei, they are somewhere 1 or below, which means that if you measure the frequency ratio at 10 to the minus 18, if your difference of k factors for your clock pair is 1, then you get the same sensitivity to alpha variation as the accuracy of your clock. If it's less than 1, of course, you get even less. So now, out of all currently operating clocks, the only one with sensitivity more than 1, Mercury is not operating right now, is actually -6. It's a terbium-3 electric alpha pole transition, and the reason why it's so sensitive, because the clock transition actually, upper state has a hole in the F shell, and the F electron actually sits very close to the nuclei. This is a very, very specific case, which is different. This is a different energy level type from any other clock. And if you also, for example, have element which is not does not have a high sensitivity, you can always compare it to cavity, and that effectively gives you a sensitivity of about 1. So the question is, can we have much, much larger k? So can we have k of 100 or 10,000? In this case, if you can measure frequency to the same 10 to the minus 18, then gives you the alpha variation 10 to the minus 20, or maybe 10 to the minus 22. So for free, you have 2 to 4 or 5 or more orders of magnitude without actually building even more accurate clock. Of course, you do have to still build a clock at 10 to the minus 18, but even much less precise clock at 10 to the minus 15, if sensitivity is 10,000, already actually will give you better limits than the currently existing ones. And that's what the main question here is. And the answers here are either nuclear clock with a potential sensitivity 10 to the 4, 10 to the 5, and I'll show you how actually that could be determined, to actually highly charged ions with sensitivities for the pair approaching 100 or more. And I will start with highly charged ions. Those are actually very interesting for many, many different reasons. If you take a singly charged ion, then I mean it's smaller than your neutral atoms, but if you start tearing more and more and more electrons, then it becomes a very compact structure. So the highly charged ions are very compact, and there is a very special scaling with nuclear charges. For example, binding energy squares by z square, but QED will scale z to the 4th, and the hyperfine will scale z cubed. And in this case, what's going to happen that you actually have very interesting level structures, and you will have optically accessible transitions, which are not available in other systems. So for example, if you take boron, there is really nothing there which you can build a clock, and it's all outside of normal lasers. I mean, 250 technically inside the laser, but this is very fast living, not metastable transition. But if you actually take argon-13+, there you will actually have M1 transition, which is optical. And that's what we're looking for. We are looking for metastable optical transition, and generally what we're looking for is not M1, but E2 or higher, which is going to be very actually long-lived. And the great thing is that those will have reduced systematics because the Stark shifts are going to be suppressed because you have such a compact system here. For example, black body shifts are negligible in highly charged ions, and they plague current clocks. There has been a recent review on highly charged ions proposals for optical clocks, and there's been a lot of experimental progress. So one of the reasons before why clocks could not have been made from highly charged ions is because they were not subject to ultra-cold technologies, and that just recently changed. So in 2015, there was a first systematic cooling of highly charged ions by the MPIK group in Heidelberg. And what you're seeing here is that this is a Coulomb crystal and of beryllium plus, and you're injecting those large blobs, which are those large blobs are highly charged ions, and of argon-13+, and then you can actually melt the Coulomb crystal. You end up with one highly charged ion and one beryllium plus, and this is exactly how actually aluminum plus optical clock works. So you always talk to beryllium plus, but you actually your clock states are of argon-13+. And then merely 5 years afterwards, there was a coherent laser spectroscopy of highly charged ions demonstrated, and I would say this is probably the one experiment which has the largest improvement which I have ever seen. So just by making the ion highly charged ion cold, and yes, while so just, it's very difficult, of course, to achieve so. But the best previous measurement achieved of any accuracy in a highly charged ion for the frequency was actually 10 to the minus 8, and they actually achieved 10 to the minus 15. So it's a fractional frequency uncertainty already at the clock level, already 10 to the minus 15. And that's done by using logic spectroscopy. So you have a spectroscopy ion, and then you have your logic ion. And that's been understood how to do it in aluminum plus clocks, because in this case, you cannot directly laser cool the highly charged ion. So you're actually using your logic ion to do so. And we looked at a lot of possible highly charged ions, and two ions which actually turned out to be very interesting. And interesting meaning that they actually have clock transitions, which are E2. So here is a clock transition is at a very nice visible range. And so is here is both E2 transitions. They're very nice lifetime. So here is a few seconds, and here is actually over 1,000 seconds. And also those ions have fairly simple electronic structure that we're looking for. There is possible cooling M1 transitions actually on those. And the important point that here, the K factors, if you actually look at combine those systems, if you compare one ion against the other, it's more than 100. And that's what we're looking for. Turns out to be that is done with californium ions. And okay, californium does not have stable isotopes. But the good point is, if you have a very efficient loading system into your highly charged ion trap, presumably if you could, and there are techniques how to do that, so you don't actually need much of the californium. And it turns out to be that there are californium isotopes which are actually fairly stable. In this case, you have a half-life of almost 1,000 years. For the spin zero isotope, you actually have 13 years half-life. So this is experimentally actually feasible. Eventually, you will only need one or a few ions, but of course, the question is you actually do still need it to load efficiently. So this experimental program actually started looking at the first images. So what you see here is our theoretical prediction. In the paper, we actually give uncertainties to all of those numbers. It is better for californium 17+, but we are talking to be 1 to 5% precision here. So those can actually be predicted very, very accurately. And those are done with a combination of couple cluster and configuration interaction codes. And then I'll talk about nuclear clock. And nuclear clock is a very strange beast. You first ask, okay, why wouldn't you base your clocks on nuclear transitions? Because you have a large variety of those. And the answer question is because, well, these are not accessible by lasers. So what you're looking for here, it's something within like this yellow blob, when you actually have this optical clock region, and that's what you can actually access by tabletop lasers. And all of those red dots are some sort of atomic shell transitions used for clocks. And here is this blue thing. It's a range, and it's kind of shrink at this point already. It's a possible range of energy for thorium-229 isomer. And as you see, that's only one. There is really no other known nuclear transition, which is within tabletop lasers. And here is a kind of the closest one is uranium. This is already at about, I think, 86 CV. So it could potentially be in the future within the frequency comes, but for now it is not. And thorium-229, it's this very interesting sort of a gift from nature, which has about 150 nanometer transition. And the lifetime is supposed to be on the order of a few thousand seconds. It's actually important to find out eventually what lifetime is, and it's going to be hopefully measured in the near future. So this transition have been seen, meaning that they have been measurements of the transition, but it's not actually directly laser excited yet. So this is still in the future, but there are many groups working on it, and hopefully it will actually happen very soon. And there is a talk later today by Lars, which will talk specifically more about the nuclear clock as well. And there is also a recent review on the current progress and the future plans of how we go from actually 2 significant figures to next 15 significant figures. And it's a very ambitious plan, but it's we have a very good idea how to do that. So why are we so interested in nuclear clock? It's because you have this potential for this exceptional sensitivity to new physics. And there's a potential of K factor being a factor of 10,000 or 100,000 even more. And the reason being because the nuclear binding energy in thorium-229 is somewhere at the GeV scale. So we have a Coulomb energy and the strong interaction energy which almost compensate each other. And it's thought that the difference would be about MeV scale, and therefore sensitivity to alpha in sort of this hand waving regime would be your transition frequency divided by this different Coulomb energy, and that's approximately would be then 10 to the 5. So not only you're sensitive to alpha through the Coulomb interaction, you're also sensitive to quark masses and lambda QCD, to the strong interaction sector, and that's what you give this enhanced sensitivity to the reaction. The question is, how can we pinpoint this number? First, I would like to mention that unlike the cases of, say, EDM or purity violation, where you actually directly need to know this number in order to extract what actual, say, EDM or some sort of weak charge is. In this case, it's just give you the highest possibility of detection. So in order to actually find dark matter, you just want the highest factor possible. You don't need exactly what that factor actually is. So there's been a proposal by Berengut, Zubov, Lamau, and Porsev in 2009 that if you actually do a nuclear model and say, well, where would this difference be coming from in the Coulomb energy, that the two first terms would be that it could be coming from just difference in the charge radii, and could be difference from the quadrupole moments. And that recently have been measured. So the charge radii actually have been measured to a good precision, but difference in Qs actually was not precise enough, and therefore we still have actually very large uncertainty here. There's been a follow-up analysis which took the changes in nuclear radii and actual numbers for the ground state nuclei, and then used constant nuclear density ansatz to predict that approximately the K factor is somewhere in the order of 10 to the 4. And that's also much, much, much higher than for any of the current clocks. So here more measurements will follow, and more complicated, complicated analysis already had been done, looking for the octopole deformation, which looks like it's not really contributing significantly based on this paper. But it'd be very, very nice to have actually more nuclear physics computations to actually support what the enhancement factor actually is. And then it brings us to the question of how well the nuclear moments of the ground state are known. And that also brings us to the whole question is how we actually can measure the determine the magnetic moments and electric quadrupole moments of the nuclei for those radioactive species which are used in this workshop. And one way to do it is actually determine them from the hyperfine constants, and you make a very precise calculation, and then you make a hyperfine structure measurement, and that's you extract hyperfine constants A and B, and that so you calculate hyperfine constants A and B, and that allows you to actually extract mu and Q. And for thorium-229, there was a measurement by Alex Kuzmich group for the hyperfine structure, and we have computed hyperfine constants and determined the magnetic moment and electric quadrupole moment. The thing which we admit is we actually did not look at the Bohr-Weisskopf effect, because we thought since we're dealing with F4D states, it actually would be insignificant, and that might not necessarily be the correct assumption. So for expert in the audience, we use linearized couple cluster method with partial triple.
1 minute.
Partial triple excitation, also use the FIT. And then we have recent, much more complicated calculation in UD. So Sergei Porsev actually developed there's the full couple cluster SDT method. So it actually includes not only valence triple, but core triples, and it does include them completely as iterative equations and not perturbatively. And as you can see, it shows that we can actually get to the binding energies at the level of 0.3%. And each successive approximation of the method actually improves the energies better and better and better. And for actual energy levels, we get very high precision. And in this case, our estimated precision for the hyperfine constants are actually less than 1%, better than 1%. And the question is there, what actually do you do for the nuclear magnetization? And right now we are putting just a uniform magnetization of the charge distribution. And there's been a recent paper of how to actually estimate what the Bohr-Weisskopf effect is based on experimental data. So the idea is to compute the data for the point nuclei and for this uniform magnetization case and calculate this y, and then you solve equation using experimental numbers for the constants. And here, as you see, there is a very large extra uncertainty coming from this. So we really don't have a good idea what the magnetization is. So what we actually need relativistic, realistic magnetization distributions and also more precise hyperfine measurements. In this case, for the Q, we actually were able to improve the electric quadrupole to actually better than 1%, to actually factor of 3 better than before. But the message here is that we actually have a very, very precise code that we can actually extract nuclear moments, and that can be done also for other radioactive atomic system species. And just to conclude, we also consider the pathways to include this nuclear transition. Been a very interesting proposal to do before by another group, to actually do it via highly charged thorium-35 ion, because it has a transition which is very, very close to nuclear resonance. So idea you shine a laser photon here, and then when actually electron decays down, what it does, it actually gives all the energy to the nuclei, and the nuclei can actually get excited to isomeric state. And the prediction here was that it's actually close, but not too close to the current value. And we actually done a very, very large configuration traction computation with our new parallel MPI code, including 120 million determinants. And we actually find out that it looks like the energy is actually even closer to the now current experimental energy. So based on what energy actually is for the thorium nuclear transition, that actually could be extremely close to this case of thorium-35 plus, and that could enhance the excitation. So in conclusion, I would like to say that we have our new project to do computation as not as a sort of physics computation, but as a software to actually be able to do massive data generation with automatic all of our code. So idea is to turn research code and software and then put everything online. So idea is to compute all the atoms which you can compute routinely. We already started this project, and there is a website. It's udality.us/atom, and just one simple thing. I'll show you how it looks like. So here you have this portal for high precision atomic data and computation. For example, you click on Radium Plus, and you can see all the matrix elements, for example, for all the states. You click on transition rates, and you can actually get all possible transition rates. You can actually order them by wavelengths. There is more than 600 transitions Radium Plus. And then there are also many other data. There's polarizabilities, hyperfine constants in there, metastable state data. And we expect the new version of the site would actually probably come online in mid-fall 2021. And that will actually have more than 30 different atoms and ions. So I would say that atomic clocks have great potential for discovering new physics, many new development coming in the next 10 years. And I would like to thank our group and collaborators. Thank you so much for your attention.
Okay, Mariana, thank you for your nice report. And other questions? Okay, I see one question from Leonid.
Hello, very nice talk. So maybe I missed, how did you take into account Bohr-Weisskopf effect for extracting nuclear magnetic moment for thorium? Did you use some specific model or not?
Okay, so so the idea is actually come from Yuri Demidov and collaborators, and Misha Kozlov and actually Sergei Korsev worked out specific scheme to how to do it for the thorium-229. So the idea is the following. We are just going to approximate that if you have uniform magnetization, this d-nuc is going to be 1. If you have no magnetization, then it's going to be 0. So then you have a pointed nuclei. So A0 is computed with a pointed nucleus. Then AT here is computed with uniform magnetization. Then what we do, we take 2 best hyperfine constants which we measured, 5F5 and 6D3, and we pretty much just solve this system of 2 equations for G factor and for d-nuc, and we essentially extract them pretty much experimentally in this case. What we really need here, we actually need one more measurement. So I think we need S state here. Oh, and by the way, this is actually at the level of theory. So the experimental measurements need to be better for actually extract this better. But the basic idea is that d-nuc may be 1 here, but it could actually be 4. So, and this is a little bit information, hopefully, for the nuclear physics, so what magnetization distribution could actually be here. So we could constrain it better. Also, if someone computes some realistic magnetization distribution from the first principle nuclear physics, we'll be happy to put it inside of our code and see what we actually can get. But right now, we pretty much have nothing to put except that we can put Fermi distribution, we can put uniform bulb. It's not going to make a difference. It's just whatever RMS radii you have. It's pretty much just charge distribution what we're using right now.
So I would like maybe to, so maybe we can talk later.
Sure, yeah, I'll be happy to.
Okay, so I see one more question from Makota.
Hi, Mariana. Thanks for a great talk. I have a general question about the ultralight dark matter. Does it always coherently oscillate? Or is there a scenario that they're just kind of randomly interacting with each other and you don't see any change in fundamental constant?
Okay, so so within the question is that actually is specific to dark matter masses as to actually which scale is it coherent. And think about that dark matter has a Q factor of about 10 to the 6. And that goes because the speed with which we are moving through dark matter, it's if you look at what this velocity to the speed of light, that's about 10 to the minus 3. So, and it actually scales with the square of that, which gets 10 to the minus, 10 to the minus 6, which is a 10 to the 6 Q factor. If you send me an email, I send you references by Andrei Derevyanko and also collaborators on specifically looking how to analyze those processes. So generally, the idea is that generally you want to measure during several coherence times. So then you actually don't have decreased sensitivity. If you're only measuring through the one coherent volume, then you'll start losing sensitivity in this case. So, and that comes from scenarios that your dark matter is a scalar and it couples linearly or quadratically to your dark matter. Quadratic, of course, case is more difficult to detect, but there is a project by Gilad Perez's group to actually look further at quadratic couplings. So there could be completely different scenarios which don't work like this. So there is idea for the topological dark matter, and in this case, there is no oscillating effect. There are potential transient effects or potential environmental dependent on fundamental constants, which as far as you go from the Earth's ground, you can actually potentially see environmental dependence in those cases. So this is a totally different scenario.
Okay, thank you.
Okay, so I don't see more questions and comments. So, and at this point, I'd like to thank all the participants. So I think we are finishing now our morning session, so to say. Okay. Thank you.
Thanks so much.
Hi, Nick or Ronald. I just wanted to confirm that I'll be moderating the afternoon session. Is that correct?
That's correct, and I will be there to help you as well.
Okay, good. So I think I have learned the process from watching other people. So I think everything will be under control. So and I guess we'll start promptly at 2 o'clock then Eastern.
See everybody then.
Okay, see you.
Robert, are we meeting regarding the?
Yes, that's what I thought.
Do I have time to get a bit of food from the garage across the road?
Yeah, shall we? Yeah. If this, shall we then meet in half an hour, or what would be the?
Okay, something like that would work for me.
Yeah, does it work for everybody else as well? I hope so, right? So
it's okay. At which room we will have meeting?
We just meet in one of the breakout rooms. 10 is our number.
Okay, cool.
Okay, I'll join.
Let's meet in half an hour. Yeah.
Hi.
Nick. Hello. Hi, Nick.
Good to see you. Thanks for coming and giving a talk here.
Oh, thank you. Thank you very much for having me here. It's been amazing to see all the great work that you guys have been doing. And I hope you keep doing it, because I know it's disheartening sometimes not to find anything, but even not finding something is important to know. But it's just, I've been, yeah, it's been really remarkable what you guys have been doing. So.
Yeah, likewise. I think it's in terms of like really exciting, remarkable stuff, this is definitely one of the best like gatherings that I've ever been to. So I'm pretty excited.
Yeah.
Okay, well, I see that it's 2 o'clock, so we should get started. Welcome back to the afternoon session of this wonderful workshop. My name is Jaydeep Singh. I'm at Michigan State University, and I'll be moderating the afternoon session, at least if you're in the US. And the focus will be largely on other very interesting opportunities. And it's my distinct pleasure to introduce our first speaker, Asamina Arvantaki, sorry, of the Perimeter Institute, who will be talking about the piezoaxionic effect. And so I'll ask you to share your screen.
Yes.
And as usual, the talks have been 25 minutes, so I'll give a warning with 5 minutes left. And then we'll have 10 minutes for questions afterwards. So you can start when you'd like.
Perfect. Thank you so much. Can you see my screen? And can I see me changing my slides?
Yep,
Yes.
we can see your screen, and
Perfect.
the slide changing looks good.
Okay, great. So thank you so much for having me here. As I was telling Nick, this has been a great gathering. It's great to see all the amazing accomplishment the field has done over the past, well, decades, but especially in the last few years. So I'm a particle theorist, so I'm extremely grateful of this work of looking for fundamental physics, and even finding nothing is also important to know. So in this talk, I would like to take the opportunity to present to you a new idea that we have. It's a new observable for axion dark matter that we call the piezoaxionic effect. It's work that we hope to publish very soon, in a few weeks' time, that I'm doing with my student Amelia Maiden and Ken Van Tilburg, who is now a professor at NYU and CCA in New York. So I will first tell you a bit about axion dark matter, given my audience is experimental, and then I will tell you exactly what this observable is and how to look for it. So the most famous particle called axion is called the QCD axion. And it has been proposed to explain the smallness of the electric dipole moment of the neutron. So in the standard model, as many of you probably know, in the standard model Lagrangian, one can add a term, a GG dual term, that if introduced, it breaks CP. If introduced, it produces an electric dipole moment for the neutron. We expect the coefficient of that term, the dimensional coefficient, which we call theta QCD, to be order 1, because CP is not a good symmetry in the standard model. But we haven't been able to find anything. In fact, the best thing we have been able to do is constrain this parameter to be less than 1 part in 10 to the 10. Now back, and this has been a problem for decades now. Back in the late 70s, early 80s, people proposed a solution by promoting theta QCD to a dynamical field, a particle, and called it the axion. Now, the cosmological evolution naturally laxes this value of this field close to 0, and thus giving a dynamical resolution to this problem. This particle, this axion, gets a mass from non-perturbative QCD effects, and its properties are uniquely characterized by a single parameter, what we call the axion decay constant. And if this decay constant is close to the Gutt scale, what you will see is that the Compton wavelength of this particle is over a kilometer, or you see a mass that's like 20 orders of magnitude smaller than the mass of the proton. So we're talking about an extremely a light particle. So I should say this particle is an excellent dark matter candidate, and it also presents an excellent experimental target because it's a one-parameter model. Now, if you go beyond the standard model with its simplest extension, the QCD axion, you find, and you try to embed the standard model in bigger theories like string theory, you find that the axion doesn't come alone. And in fact, it may come with many axions that have similar properties to it. And this is because, for example, string theory, and this is not, and I will mention string theory, but this happens in many theories beyond the standard model. So for the specific case of string theory, this happens, you get extra axions because string theory has three fundamental ingredients. It has extra dimensions that are needed for the theory to be mathematically consistent. You have gauge fields, you have particles that live in these extra dimensions. And you also have topology. These extra dimensions, which are spatial in nature, need to be compactified in order to give rise to our four-dimensional world. So you can compactify them simply on a torus or a sphere, or you can compactify them. The ways you can compactify them is only limited by the imagination of the person that's write down the compactification. Now, it turns out, combining these three ingredients, these extra particles living in these extra dimensions, turns out after the extra dimensions are compactified, manifest themselves as massless particles, and these particles can be axions with properties similar to the QCD axion. And as I said, they can be excellent dark matter candidates. So how are you supposed to think about such dark matter candidates? Mariana talked earlier about, in her talk, a bit about this. I will expand a bit on this given the current audience. So usually when we think about dark matter, we have in mind a picture like what you see here. So you have particles like WIMPs that are zooming around in the galaxy. Now, in reality, we know that we shouldn't really think about particles, but we should be thinking about little wave packets whose size is determined by the de Broglie wavelength of the particle. If the mass of the particle is heavy, these two pictures, the particle picture and what I call the wave picture, are equivalent. As you start making the dark matter mass lighter and lighter, though, you will see that at some point, these wave packets want to overlap. And at that point, for example, it tells you that fermionic dark matter candidates won't work so well. And we know there is a lower bound on the fermion dark matter mass that's about 70 eV from just cosmological observations. So now for a boson, as we start making lighter and lighter, there's no such problem. And in fact, when these particles start overlapping, it's more convenient to not talk about individual particles anymore, but to talk about a scalar wave dark matter who oscillates coherently in the galaxy. Now, for us in our galaxy, this happens when the dark matter mass, this transition from this convenience transition, I should say, from the particle picture to the wave picture happens when the mass of the dark matter is lighter than about 1 eV. Then it becomes much easier to describe dark matter in terms of its amplitude and its oscillation frequency. The amplitude is proportional to the square root of the local dark matter density. It's inversely proportional to the mass of the dark matter. And its frequency is set by the total energy, rest mass plus kinetic energy, of the dark matter. This wave, as Mariana said before, it's not monochromatic because dark matter is virialized inside the galaxy. And in fact, given that the virial spread of velocity is about 10 to the minus 3 of the speed of light, you find that the line width of this dark matter wave is about 10 to the minus 6 of the nominal frequency. So how does this dark matter have come about? And I would like to spend some time on it, because usually when people talk about dark matter candidates, they ignore the production mechanism, even though it's an important part of the full story. You need to explain where dark matter is coming from. So for a scalar field, there is something called the misalignment mechanism. And you can understand what that means by looking at the evolution equation of scalar dark matter in an expanding universe. You see that that equation is very similar to that of a harmonic oscillator. So you have the mass playing the role of the resonant frequency, and you have the Hubble friction playing the role of the loss factor in a harmonic oscillator. Now, in the early universe, when the universe is very hot, the Hubble friction is larger than the nominal frequency. So this harmonic oscillator slash wave, scalar wave, finds itself in the overdamped regime. And it's frozen. It's like it's moving through thick honey. Now, the question is, do you expect it to be at the minimum? And the answer is no. For several reasons, the zero here, the minimum, is not a special point for this field. And if we even expect inflation, during inflation, quantum perturbations to kick this field around. So we don't expect this field to lie. We expect this field to be misaligned from its equilibrium position. And this is where the name misalignment comes from too. Now, as the universe evolves, Hubble drops, and eventually you transition from the overdamped to the underdamped regime. So, and when this happens, the scalar field harmonic oscillator does what it's supposed to do. It starts oscillating, and you find that the energy density stored in it scales exactly like what dark matter is supposed to scale. So this is a production, this misalignment mechanism, thus is a very efficient production mechanism for spin zero particles, and it's a non-thermal production mechanism. So it doesn't depend on the thermal history of the universe. Now, how you look for it, and I should say today, the amplitude drops, and today you can see that, for example, for the QCD axion, the amplitude, the dimensional amplitude of this dark matter, which I will be calling theta bar for this talk, is about a few times 10 to the minus 19 in our galaxy, okay? So we're talking about a very small oscillation amplitude. So the question is, how can you detect the small oscillation? And there are ways to detect axioms, and they depend on how axioms couple. And they couple with a finite number of ways. The most famous of which is the axiom coupling to photons. So if you have a background B field, dark matter axioms can convert to photons of the same energy. Now, if the P field is applied on a cavity whose size matches the Compton wavelength of the axiom, then you get resonant conversion. And this is the idea based on the very famous ADMX experiment, which is operating, and it's actually one of the first experiments to probe the QCD axion parameter space in a laboratory setting. Now, other more recent ideas involve a spin precession. So axions couples to the spins of fermions, so they act like an anomalous magnetic field. So if you put spins inside in this axion field background, they can precess around this P field. And this is the idea behind the Casper experiment, which I believe Dima Butker talked about. Now, there is another coupling, and in particular, which is model independent for the QCD axion. This is the coupling to the gluons. The term essentially that's responsible for solving the strong CP problem. Now, in this case, you put if you put a spin inside an atom or a fundamental, let me correct, a fermion, a quark will have an EDM due to the coupling of GG dual to the axion. And this electric dipole moment, if you put a strong electric field, which is in a background electric field on ferroelectric material, then this spin will precess if there is axion dark matter. And this is the idea behind the Casper electric version. Now, the new thing that I will be talking about is based on the things that I've described before, on the fact that axion dark matter is essentially a time-dependent parity and time-violating background. And in piezoelectric material, this that inherently breaks parity symmetry, the axion dark matter will result in a strain. So you can design an experiment that resonates with the strain. So you rely on mechanical resonance to enhance your signal. So you can try to detect dark matter through that. This will happen for all the axion couplings that I talked about before, but turns out the most promising coupling for this type of observable, the one that will give the largest signal, is the coupling to the gluons. So I will tell you about how this observable works a bit more detail and give you a potential experimental setup. So as I alluded to, just a brief review of piezoelectricity for the layman's. I'm pretty sure there are experimentalists there that will be cringed into this. So if you have a piezoelectric crystal, mirror symmetry is broken. And you see this, the most famous, perhaps, material that we know of that's piezoelectric is quartz. And quartz, the quartz crystal is this tetrahedra where is a helix, essentially, of tetrahedra, where at the edges of the tetrahedron you have oxygen atoms, in the center you have a silicon atom, and you have two possible orientations. You have left-handed, what is called alpha quartz, and right-handed alpha quartz. Turns out that that one that has the most natural abundance is the alpha quartz. And in this type of material, any electric field leads to stress, and any strain that you apply to the field will lead to a displacement field. To the material will lead to a displacement field. So this is something basically that is, so for example, something that is parity odd, like a displacement field, will result in a strain, which is a parity even quantity. So there's intrinsic violation of parity in this material. Now, when you have an axion background, and let's say one of the nuclei in the material has a spin, and these spins are polarized in the same direction, you find that the spin polarization can also lead to stress. At the same time, it can also lead to a displacement field. So in the equations that I wrote down before, you need to add what we call a Xi, a piezoaxionic tensor. And there's also going to be a parameter called zeta, which is an axioelectric tensor in this material. So for the rest of the talk, I will focus on this Xi parameter because it turns out it's the most promising experimentally. And I will tell you how we can estimate it. So where does this piezoaxionic tensor come from? For an atom, as many, I'm sure many of you know much better than I do, I can put if I have a nuclear shift moment, it interacts with the electron cloud, and there is some sort of energy shift that depends on the product of the shift moment times the gradient of the delta function, where the delta functions acts on the electron cloud. Now, for an atom, we know the shift can only be zero if you have a background electric field. But turns out it can also be non-zero because of symmetry when you have a piezoelectric crystal. And this is a characteristic size of this energy shift for the QCD axion. It's very small, and I will argue that nevertheless is potentially measurable. This epsilon s and epsilon p are the admixtures of the valence electron wave function with s and p orbitals. P is the polarization vector, and M is some matrix element, basically some angular dependence matrix element, and relativistic enhancements are also included in this estimate. So now, how do we go from the atom to the crystal? Then we have to take into account that when we observe the crystal, it will be in perturbations. We have to consider perturbations around this ground state. So we have to take the derivative of this matrix element with respect to the strain. And this gives us this piezoaxionic tensor, which we can estimate to be proportional to the shift moment, inversely proportional to the cell's volume, unit cell volume, And xi tilde is a parameter, order 1 parameter, that basically incorporates all the uncertainties that we have from the crystal. And we expect it to be proportional to the piezoelectric tensor. So as long as the material has large piezoelectricity, this xi parameter will also be analogously enhanced. So how can you measure this xi parameter? So this is a very pictorial of a possible experimental setup. This is by no means a full-fledged experimental proposal. So what you take is you take the piezoelectric material with nuclear spins, you put them in a strong magnetic field to polarize the spins. Now, the field doesn't have to be on all the time. Turns out nuclear spins in solids can keep their polarization for quite some time. So you turn off the field, and then if there's an axion dark matter, then the material will start to oscillate. Now, if the oscillation frequency, basically the frequency set by the axion mass, matches the acoustic mode of the crystal, it will be resonantly excited. So this resonant excitation we can pick up with very well-known techniques from resonant mass detectors that people have been using for decades to measure gravitational waves, and more recently other things. So the most famous resonant mass detectors is the Weber bar from the 60s. The first such, so Weber took a huge chunk of aluminum and put sensors on it, and said that if you have a gravitational wave going by in the right frequency, it will resonantly excite this bar, and you can measure the strain. He was sensitive to strains of size of about 10 to the minus 17. In fact, the problem was that he thought he had seen gravitational waves. Turns out he didn't. Today, this technology has been quite mature, and there are experiments there have been experiments like Auriga, Nautilus, and Mini-Grail that have shown strain sensitivity at the level of 1 part in 10 to the 25. So this is this part, the resonant mass detector techniques, and now there are experiments from Michael Tolbard in Australia, where this shows that this is, in a way, a mature technology. Some aspects of the setup are a very mature technology. Now, turns out, so how do we need to go beyond, though, for this observable that I talked about, we need to go beyond the Weber bar. So first of all, we need to use not just an aluminum bar, we need to use piezoelectric material. And turns out that's not a very hard requirement to satisfy. Turns out 20 out of the 32 crystal symmetry classes are piezoelectric. You need this piezoelectric material to contain, obviously, nuclei that have large shift moments, like neptunium, europium, and many others. You know the material, yeah, thank you. You know the material has to have low mechanical losses, okay? And so that it has a high Q factor, because you need to suppress noise and also properly enhance your signal. Finally, this is a list of possible compounds. There are many more that we can perhaps use. So we don't believe that material choice will be a limitation factor in the setup. So we don't have a precise calculation of what, for a very specific crystal, of what the piezoaxionic tensor will look like. We have an estimate though of what it can be, and based on that, we can project the potential reach of this type of setup. And this is a plot that shows exactly that. This is a plot that shows the axion mass, and this is the axion coupling basically to gluons. The blue line is the QCD axion line. What you see here in gray are known constraints from one is supernova 97A, the other is from an effect that is known as black hole superradiance. I don't have time to talk about that. There is another constraint in this parameter space that's usually ignored, and I need to point that out, that it shouldn't be ignored. When an axion couples to gluons, and it couples with strength much bigger than what the QCD axion with the same mass would do, There are matter-dependent effects that give the axion a mass close to the Earth and close to the Sun, and also change its minimum. So there are severe constraints in parts of the parameter space, just because we haven't seen a huge force between the Earth and the Sun. And this is something that, this is something that I should point out. Now, what you see here in orange is a possible sensitivity for a single setup. And what do I mean about single setup? Take some small piezoelectric crystals, put 16 of them in series, cool them down sufficiently, and integrate for a year, while at the same time reading out the signal with a squid, while at the same time changing a bit the inductance of your circuit so that you tune the resonance frequency. So within a year, with a single setup, in principle, you can cover a large range of the parameter space. Not only that, you have the potential to reach the QCD axion line in a regime where you haven't probed it yet in a laboratory setting. If you go beyond the simple estimate here, we believe that this technique can be applied anywhere between masses of 10 to the minus 12 and 10 to the minus 7 eV, which is frequencies between 10 to the 1 kilohertz and all the way up to something like 100 megahertz. So this is a technique that's largely complementary to cavity searches. So first of all, there are backgrounds, and we've estimated those. We believe those can be small if you have the right material. You need low radioactivity. There are magnetic impurities that need to be controlled, and this can be demonstrated at the right level. There's going to be EMF from fluctuating nuclear spins that can also be small. This is not a problem, limiting factor for us. We're in fact limited probably more by the squid noise and the crystal noise. So as I said, I talked about the axion coupling to gluons, but in reality, all axion couplings will do such a thing. And this is an estimate of the size of the strain. Just a reference for the gluon, the expected strain is 10 to the minus 26. But you see here different sizes for different axion couplings. The main take-home message, yes, the effect is non-zero for other axion couplings, but probably this is the largest one of the effects, especially for the QCD axion. And with this, I would like to conclude. I briefly described to you what we believe to be a new observable for axioms, in particular for the QCD axion. Based on largely, part of it is based on known technology, and it can give good sensitivity to action at frequency above 1 kilohertz, and in a regime that's largely complementary to cavity experiments. So with this, I would like to thank you, and I'll take your questions now.
Okay, thank you. We have plenty of time for questions. If you have a question, please just put an exclamation point in the chat, and I'll endeavor to call on you in the order that you commented. So Andrew, I think you had the first question.
Great talk, Mina. I chatted with Ken briefly about this idea a couple of months ago.
Oh, yeah.
Can you go back to, okay, you have the sensitivity slide here. That's
yeah,
fine.
I can go back. Let me go back. Try to go
to
back.
the big one.
Yeah, let me go back to the big one. If I can go back here, doesn't always work here. Yes.
Yeah, great. I was just kind of for this, I don't even know, a couple questions. The inductive tuning sounds great. I was just wondering, are you guys, several questions, are you guys considering multiple modes across each?
Yes.
So multiple mechanical modes?
Yes, so basically you can count the modes. You see the peak, because you know between modes you have, if you have the fundamental mode, the next mode in between the modes, they add up with the opposite sign. So that's why you see the suppression, the little spikes. So this is scanning several modes, not just this fundamental mode.
Got it. And then what type of mechanical cues are you guys considering? And then what atom choice went into maybe the atom choice is almost the most intriguing thing for me.
Yeah, so I'll tell you. So this is, I can tell you there is no, so let me go back. So we estimate, because we're using some loss angle here, the effective Q factor is probably around 10 to the 8 or 10 to the 9. It may sound a bit scary, but Actually, we know that for quartz crystals, for example, Tobar has demonstrated Q factors in excess of 10 to the 10. So we are not worried about that fact. Now, what atom, we don't have specific things in mind. I mean, we have specific crystals in mind. Here we take an idealized setup. So what atom? Something that has a shift moment, which is order a few times theta bar if femtometers cubed. Basically something like what you would expect from neptunium or europium or something like that. And something that has a cell size similar to what you would expect from quartz, not too big, so that it has nice dense material. And a large piezoelectric constant, which we take to be order 1. So there is not, in principle, I mean, this is, as I said, this is not, this is, I was like, at first when I wrote this slide, I wrote it as this is a sensitivity in Coates plot, because in reality, we don't know what the best material would be, because we haven't done, and this is very important, we haven't done full DFT calculations for this. We know what the size of the effect should be. So we use some idealized crystals with what we believe to be reasonable parameters. And but the atom, we imagine something like europium, neptunium, or even uranium-235 sounds great. So yeah, thank you.
Okay, our next question comes from Nick. Go ahead.
Thanks for a really interesting talk. Have you thought at all about using optical effects, some of which in materials depend on the sort of intrinsic parity violation of the material, like second harmonic generation? Something
you mean like non-linearities in material?
Yeah, like, but which sort of depend on a parity breaking, like, for example, second harmonic
usually
generation.
those things, if I understand those things correctly, we've thought about this a bit in the past, but if we are thinking of the same thing, first of all, I should qualify this, those effects were not very large, because those effects on light, you need to have the light going through. It's a small fraction on top of whatever the usual parity preserving stuff is. So here you already start with a 0 background in principle, and you're trying to set a small effect. Usually in those experiments, you try to see, you have a huge parity preserving background because you have a lot of photons, and then you try to see. And there was a proposal by, I think, Ronnie Hennig, based on some similar idea, but the reach is not fantastic, and they don't really have a setup. Like, backgrounds are a complete mess. And I don't think that's a more promising, if we're thinking of the same thing. I mean, I'll be happy to discuss your line more on that.
Thank you.
Okay, we still have time for questions, and the next one comes from Arian. Go ahead.
Oh, hello.
Hi.
Kind of related to the previous question, have you considered maybe using color centers like nitrogen vacancy centers or silicon vacancy centers to read out the strain and stress in these materials? Would that maybe give you, I don't know if that would give you better sensitivity or not.
I don't think so, because usually those things are more noisy. Here, you really take advantage of a bulk property. So it's not clear to me. I should say that on resonance, mostly we're sensitive by noise. It would help to have less squid noise in some part of the parameter space, but doesn't necessarily gain you anything. I don't see how. Right away. I mean, it may help if you want to measure things that are associated with electron spins, because there things are much more noisy, but then you will lose in terms of density. So, yeah.
Yeah, I guess I was just thinking of like embedding, if it's possible to embed them in the piezoelectric crystal, but that might be very complicated if the crystal structure isn't amenable to that.
Yeah, I mean, you have magnetic impurities already, and adding more stuff in it actually brings down the Q factor. So in principle, you want to take advantage of the high purity material as much as you can. But I don't know, I'm not a material science. There may be better ways to read it out. We just, actually for the readout, I should say, we just stuck to things that people know how to do. We didn't want to reinvent the wheel there. We just wanted to ask, had the principle one revolution at a time. So the revolution was the new material. So the readout is something that's tried and tested.
That makes sense.
So that's
Thank
why,
you.
yeah.
Okay, I don't see any additional questions. So let's thank our speaker again, and then we'll move on to our next presentation. So I would like to introduce Paul Hamilton of UCLA, and he will be describing the Hunter experiment searching for sterile neutrinos in laser-trapped cesium-131. It looks like you're sharing your screen.
Good, you see the slides, not the presentation.
Hi, Paul. Yeah, I see your title slide. Can you try changing your slides real quick? Oh, yep, looks great. Okay, so you can start when you'd like, and I'll give you a warning at 5 minutes.
Thank you, JD. And thank you very much to the organizers for having me here, especially Nick with the invitation. It's really been quite fun hearing all the great progress here. A little bit of background on myself. I had actually worked on molecules for my PhD doing lead oxide EDM experiment in Dave DeMille's lab. But after that, I pretty much ran away from molecules. I've been sticking to atoms ever since. So the title for this workshop, I feel like with a lot of the talks we've had so far, maybe it's more like radioactive and/or molecular species. For my talk in particular, I won't be talking about molecules. I'll be focusing on the radioactive part of the workshop for it. A little bit about my lab at UCLA. So I'll be talking about a search for sterile neutrinos with the Hunter collaboration. We also have other experiments using atoms, an ion gyroscope, a force sensor using neutral ytterbium atoms, and then I'm also part of another collaboration that uses magnetometers that searches for different types of cosmological fields. So the Hunter collaboration that I'll be talking about today, the idea is to use radioactive atoms to look for neutrinos. It's a collaboration between some particle physicists. Jeff Martov at Temple is the spokesman for our group. UCLA, we really have the AMO expertise. Eric Hudson, myself, and Christian Schneider has really led a lot of the development of the apparatus, as well as Peter Myers and Andrew Renshaw at University of Houston and Princeton. So what is this Hunter collaboration? Well, Hunter stands for Heavy Unseen Neutrinos by Total Energy Momentum Reconstruction. And here's the basic idea. So we'll be trapping radioactive atoms. In our case, it'll be cesium-131. And these particular isotopes decay by electron capture. So for those of you that may not be familiar with this, basically what happens is one of the inner shell electrons in the cesium atom is absorbed in the nucleus, and you can think about it, the proton absorbs it, turns into a neutron. This is nice because it gives a very simple decay that you get an ion that recoils in one direction and you get a neutrino in the other direction. So it's a two-body decay at this point. Of course, things aren't quite that simple in reality. If you take an inner shell electron out, the rest of the electrons in your cesium atom are going to rearrange. You can get an X-ray photon out as one of the outer electrons falls into this hole in the inner shell. And you can also get electrons that are shaken off in the rearrangement for this, called Auger electrons. So the idea of our experiment is going to be to measure the recoil momentum of the products, so the ion that comes out, the X-rays, and the electrons, very precisely. And if we can do this well enough, we can detect or place limits on kind of KeV scale, mass scale neutrinos emitted during these decays. So why are we interested in heavy neutrinos? If you remember from the title, it was Heavy Unseen Neutrinos in Hunter. So brief outline, I'll talk about why that's interesting, go into some more details on how our experiment's actually going to work, and then what the current status is in the future reach. So the heavy neutrinos, there's a couple reasons why we find them interesting. Typically, we're interested in heavy sterile neutrinos. Those are neutrinos that don't really interact via the weak force. And there's two main, let's say, classes of motivation for it. The first is astrophysics, that it turns out that this kiloelectronvolt scale neutrino is attractive as a warm dark matter candidate. On the particle physics side, you might also ask, In the standard model, we know that the neutrino masses are extremely small. So the neutrinos that we detect every day are sub-eV scale, even lower than that. So these two motivations for us tell us that this is an interesting place to look. There's actually quite a bit of interest in this. There's a huge review in the archive that has dozens of authors talking about these KeV stereoneutrinos. And we think we can do a pretty sensitive laboratory experiment, so nothing that's too large scale and pretty cost effective to search this range of masses. All right, so for the astrophysics motivation, we've probably seen this several times in the workshop already, that we know the standard model is incomplete. Astrophysicists tell us if we look at the contents of our universe, there's not much we know. So we know this little sliver quite well, the ordinary matter. We've had many, many tests and very few definitive violations of the standard model. So the question is, what is the rest of this stuff? In particular for this talk, we'll be focusing on what is the dark matter. And I'll argue that neutrinos could be a good candidate for this. So what do we know about the dark matter? Well, we can go and look at references, and one of my favorites here for this is actually the webcomic XKCD. And you look at what are the range of masses that you could possibly have for dark matter candidates. And you can see there's quite a range on here. This is actually a pretty good list of many of the real candidates. There's also some funny things over here as well. What I'll be focusing on are these lighter scale over here. We see stereoneutrinos for this. So a little bit more serious. If we look at the standard model, what are the range of masses for the particles that we know about? Well, we have neutrinos that are kind of the milli-electron volt scale, up to electrons at 500 keV. Heavier particles, such as the top quark, get all the way up to hundreds of GeV for it. So there's huge range of masses here. There's been a lot of focus on dark matter searches so far, both with underground ton scale detectors and things like particle colliders at kind of the GeV or above scale, as well as a lot of these atomic physics experiments looking for heavy particles that could, from things like EDMs, that could cause EDMs. So far we haven't seen anything or any hints yet in these GeV scales. Another possibility is to look, as I mentioned, this KeV scale. And it turns out if we look at, from galactic rotation curves, we know that there's dark matter in our galaxy. And if you look at the typical production mechanisms, a 10 keV stereoneutrino gives about the right dark matter density in the galaxy. There's one issue with this is that you can't have too strong of a coupling between this neutrino, otherwise it can decay. So it needs to decouple quite weakly. And if you have a coupling constant of about 10 to the minus 4, that'll give you stability over the universe's lifetime. KV neutrinos are also interesting because they solve several other astrophysical problems. If we look at the normal neutrinos, the kind of MeV, milli-electron volt scale neutrinos that we've detected in our laboratories, they would produce dark matter that's too hot. But this KV scale is kind of warm. It's not quite cold. It's not too hot. It would help to explain things like the fact that we don't see as many satellite galaxies around dwarf satellite galaxies around the main galaxies. Also things like if you look at the dark matter density, it doesn't appear to be peaked enough for cold dark matter. Same thing that we should see denser dark or dwarf satellites as well. So this warm KeV scale dark matter, roughly speaking, smooths out density distributions. One other hint from the astrophysics is that we have seen some KeV X-ray signals that could come from the decay of stereoneutrinos, although I should mention this is still being debated. So these X-ray hints come from the fact that here we have a couple of Feynman diagrams. If I have a stereoneutrino come in, it can actually decay into X-rays with energies given by half of whatever their rest mass is. In 2014, there was unexplained X-ray signals from both galaxy clusters and from the galactic center around 3.55 keV, so this bump here. And that could be a hint of stereoneutrino dark matter. If you look at what the coupling would have to be, it's extremely small, though. It's around 10 to the minus 10 for that. So it'd be around a 7 keV stereoneutrino. And I should mention, this is still being debated. There's arguments about late analysis of this. I don't know if the debates have actually been resolved yet. Okay, from the particle physics side, we know that neutrinos are weird, and we'd like to understand more about them. So I'd say there's two strange things compared to other particles about neutrinos. The first that we know is that neutrinos are different than the other types of particles like quarks and our leptons, in that they both have left and right-handed versions. Neutrinos, in the weak force, we know that the way it interacts is we only see left-handed neutrinos for that. So we haven't seen right-handed neutrinos. Another strange thing with neutrinos, and maybe not quite as strange because it's somewhat true for quarks as well, is that the flavor eigenstates, meaning the electron, muon, tau, the eigenstates of the weak force, don't match up with the mass eigenstates. So here I just have a diagram showing two possibilities that we've measured 3 different masses. Actually, we measure mass differences squared with experiments in the lab. And if you look at the content in terms of the weak flavors, each one of these masses is actually a mixture of many of the different flavors for it. So we have a mass mixing matrix where an electron neutrino is not just one mass, but it's a superposition of 3. That's what leads to things like neutrino oscillations. Okay, so stereoneutrinos, it turns out, I won't go into too many details for it, we're missing the left-handed version of neutrinos in the standard model. There's many models beyond the standard model where you add in right-handed neutrinos. And generically, they're one way that you can help to explain why these other neutrino masses are so small compared to the rest of the masses in the standard model for it. There's something called the seesaw mechanism, where if you have heavy right-handed neutrinos, through some mixing, you can explain why you have low masses for the other neutrinos. Okay, so what would a sterile neutrino look like kind of in the concept of our experiment? The idea, again, is that we have our nucleus, it decays by this electron capture, and it's going to emit a neutrino that's in a weak eigenstate. In our case, it's going to be an electron neutrino. As I mentioned above, the electron neutrino is not a single mass eigenstate. It's actually going to be a superposition of the 3 mass eigenstates that we know from the standard model. And if we also add a 4th sterile neutrino state, we can imagine there's some small mixture of it as well. So the idea would be that our electron neutrino is really mostly the 3 mass states that we've seen from neutrino oscillations, plus this coupling parameter would be small, some small admixture of a sterile neutrino. And that's what we'd like to detect. Okay, so how does this work? So again, in the Hunter concept, what's going to happen, as I mentioned before, we have this decay with electron capture. We have a neutrino that's emitted, our nucleus recoils, and we have a couple products that we're going to measure out of that. So with cesium, the idea is that we will laser cool this, basically suspend it in vacuum using laser cooling, measure these products. For cesium, it turns out that the Q value, the amount of energy that can be released in this electron capture decay, is about 350 keV. So we could detect neutrinos. It's possible to produce sterile neutrinos up to this mass scale. And what we'll see is that typically the decays will be consistent with standard model masses. In other words, very small milli-electron volt scale neutrinos. Actually won't be able to resolve those. But occasionally we might see a heavy recoil because of this small admixture that we had up here of our sterile neutrino component. So if this coefficient out here is small, squaring that will tell us how many of our decays will look like they were a heavy neutrino mass. So again, experimentally, what happens, we have our atom, it decays, we detect an ion, trigger X-rays, detect electrons, we don't see the neutrino. We can do a simple mass reconstruction formula, just using our special relativity, and look at what the reconstructed masses of that missing neutrino, basically by looking at what the missing energy is and the missing momentum from this reaction. And once you do that reconstruction, what our eventual data would look like is something where we have a reconstructed mass versus number of events. Standard neutrino events basically are going to look like 0 mass on the scales that we're talking about. So we'll see many, many events at 0. And then if there was a KeV neutrino, the sterile neutrino, we'd see a separated mass peak at its mass. So here I've actually plotted it against mass squared. The nice thing about this is it's model independent. Doesn't matter whether this is dark matter, doesn't matter what your model is for neutrinos, as long as it has this mass and a coupling, we would see it. Okay, so how did we arrive at the choice for cesium-131? So we thought about this for a while before the experiment began. Actually, it was mostly Eric Hudson and Peter Smith at UCLA that did this. And there were several properties that we wanted for the isotope in this experiment. The first was having an electron capture reaction. This gives us the simple kinematics that allow the reconstruction. We wanted something laser coolable. We'll see the reason for this is we want a very low initial kinetic energy. We need to know what the initial momentum is very well to reconstruct the missing momentum. We wanted something that wasn't too radioactive, so a half-life greater than a day. So no accelerator needed, although I should say this is just for now, especially at this workshop. It'll be interesting for future versions of this to have higher flux sources. And we also wanted something for now that was available to us easily. And it turns out that there are many isotopes available for medical purposes. So going through the chart of the nuclides, there's about 60 possible candidates, and there's basically one that met these requirements. I should mention there were a few others that were close. Strontium, for example, has an isotope that would be laser coolable. It would be interesting for this as well. Okay, so what is cesium-131? The relevant properties for it has a half-life of about 10 days, undergoes 100% electron capture decays. Again, the Q value, the amount of energy released in this electron capture is 355 kiloelectron volts. So that's the max scale that we could see for our stale neutrino. And it's going to emit a stable nucleus, which is nice. We don't have to worry about radioactive products for it. The neutrino that we're interested in, X-rays that are in the 4 to 35 keV range, so nothing too high energy, and Auger electrons from 3 to 150 electron volts. It's also commercially available. You can buy it for about $10,000, plus an extra $1,000 for a Curie, which is quite a bit. Okay, so how do we actually do the measurement with cesium? Well, here was our mass reconstruction formula. And basically what we need to know is how well do we need to measure this missing energy and momentum. Most of the momentum is going to be going in the recoiling ion. So to first order, we can ignore the electron and X-ray. If we take our formula here and just focus on solving for the momentum of our ion, we can get this approximation. And what we can see from this formula is if we plug in a 10 keV mass of our sterile neutrino that we're interested in determining, compare that to 350 keV energy, or the Q of the reaction, it's going to change if this exists. It'll change our ion momentum by about 0.04%. So this really sets the scale for what the accuracy is that we need to reconstruct the momentum, as well as the source temperature. So we need to have the initial distribution momentum smaller than this value. For cesium, this corresponds to about 150 microkelvin thermal distribution. And with laser cooling, this is easily surpassable. So it's pretty easy to get down to tens of microkelvin. All right, more details on the experiment. So this is a pretty complicated plot here, and I'll step you through it. So the center of this here is where our laser cooled source of cesium atoms will be, the 131 cesium. So we'll have 6 laser beams coming in, holds it in place in the center of a vacuum chamber. This will be surrounded by a big solenoid that produces a magnetic field, as well as a bunch of rings that produce electric fields for extracting out the charged particles during the decays. This is a standard technique called a reaction microscope. And the idea is that once the decay occurs, you extract out your charge.
Oh, it looks like Paul is frozen.
Oh,
you're back. Okay, go ahead.
Can you hear me?
Yep, we can hear you now.
Okay. How long was I frozen for?
You were just describing the reaction microscope.
Okay. Right. So the reaction microscope, we have a solenoid that produces a magnetic field of about 8 Gauss along the axis, as well as electrodes that produce electric fields to extract our charged particles out. And the idea is to push them towards detectors at the end of 2 long tubes, at least for atomic physics experiments. This is a pretty huge scale experiment, a couple meters long. And we have position sensitive detection using an MCP array at either end. And we can also measure what the time of flight was. So we do that by having X-ray panels. And what's going to happen is our decay occurs, one of the outer electrons fills in the missing hole in the inner shell that emits an X-ray. The X-ray comes out, hits our detector. That's nice actually for us because that acts as a trigger. It tells us exactly when the decay occurred. and we can count time of flight or how long it takes for the decay products to reach the detectors based on that trigger from the X-rays for it. So we can collect almost all of the ions in all directions at decay. The electrons, the magnetic field is used to create a spiral so that they're actually going to stay near our detector. We only collect about 6%, so there's a loss in our detection rate because of that. But in general, this is a method that's been used by many atomic physics groups. And in fact, using MOTS as sources has been pioneered by several groups, such as the TRIUMPH group as well, for radioactive studies as well. Okay, so we've done many simulations, full simulations of all the electromagnetic fields, simulated the decays, seen what our resolution is. And the take home from this is after all these simulations, it seems that we can do better than the resolution of 0.04% that we needed to reach this kind of tens of keV resolution on the mass for it. Since I'm more focused on the AMO part, I'll focus a little bit on how we are going to do the magneto-optical trapping. Turns out that cesium, well, we chose this because it's one of the simplest MOTS that you can make magneto-optical traps. Most of you are probably familiar with this. It requires 852 nanometer light and optics that are all standard. It was one of the first MOTS that was made. Here's a picture from my postdoc work where we made MOTS of about 10 to the 9 cesium atoms at 20 microkelvin. And you can even get bigger MOTS. We've seen over 10 to the 10 or more with lower temperatures if needed. 5 minutes. Thanks. So there'll be some challenges doing this with the radioactive species. For 131 cesium, there'll be different isotope shifts and different hyperfine structure from the usual one. But luckily, our nuclear friends have measured all of these things in the past, even in the 80s. It's a completely man-made isotope, so how will we get it? Well, as I mentioned before, it turns out that it is used in medical therapy, so it's quite easy to order. And for safe handling, at least at UCLA, we can't use too much. The national labs, you guys can probably use quite a bit more. But we do have experience at UCLA, both with radioactive barium for a ion project we have using qubits with this, and also a thorium-229 search that's being done by Eric Hudson's group. Okay, so where are we and where will we be with this experiment? So one of the things that we developed over the last about year and a half is a high efficiency source for 131 cesium MOT. We're using the basic design from Harvey Gould called an orthotropic oven that should have close to 100% efficiency. And the idea is that you take a high work function material, which is platinum, and then you have a low work function. And basically you take some cesium or whatever it is that you want. And since this has a high work function, it's going to strip off an electron, create an ion. If you apply a voltage between these two parts, you can have the ions go towards your neutralizer here, the low work function, I'll neutralize it. Maybe it bounces off, it goes somewhere again, but it can come back because it's ionized by the surface of this. And eventually it goes out a hole. So you have multiple chances, and the only atoms that get out are neutral atoms that go through this well-collimated beam here. So we've demonstrated this using a non-radioactive solution, just regular cesium for it, and shown that we can create a beam with high flux that we can control even with the bias between the wall and the neutralizer in this. So we've finalized the design for this oven here. We actually have a way that we can have it reloadable so that we can just send it to the company to load it with their 131 cesium. And currently we're working on an ultra-stable laser system for complete amplitude and polarization control of the MOT. So we want the initial position and size of our MOT to be very, very stable so that this thing can run for weeks, months without any attendance. So we have things where we have complete control using little motors for all 6 beams of Vermont over all polarization and amplitude as well. During the pandemic, we actually got our vacuum chamber in. It's been assembled with it. This is huge, at least compared to typical AMO experiments. And we're actually in progress of finishing the final fabrication for the spectrometer. So all these different electrodes that you need to put to extract the ions and electrons. Okay, so what will we do with the experiment? Well, there's 3 planned phases for this, and the details are in a recent article in the Quantum Science and Technology Journal. In the phase 1 approach, we just want to do proof of principle and show that the science idea works here. We're cost limited in that if we had more money, we could buy more detectors and have higher detection rates. So we have a table just going through what all the efficiencies are for our detection. And here's a simulation showing for our first run, 1 year of data, if we assume a 60 keV sterile neutrino and a coupling constant of 3 × 10⁻⁴, we'd expect this 0 peak background from standard model neutrinos and a peak over here. In this case, this is about a 5 sigma peak at 60 keV. So that's what it would look like if the sterile neutrino existed with this coupling. Farther down the road, we want to improve basically by more coverage with our detectors, larger MOTS, larger sources for it. And we think that, phase 1, we can reach somewhere around here. So this is the mass range for the sterile neutrino. Again, the interesting range for dark matter is around here. Here's the coupling constants on the vertical axis. And we believe that there's orders of magnitude of room for improvement with both of these. All right, I think with that, I'll stop. And again, thank the collaboration. A lot of this work was done by Christian Schneider and Eddie Chang at UCLA. And just in summary, we'll be placing constraints on the mass and coupling of keV scale sterile neutrinos, which could be interesting as a dark matter candidate. Thank you.
Okay, thank you, Paul, for a very interesting talk. So I'll again ask members of the audience, if you have questions, please put an exclamation point in the comments, and I'm already seeing them. So it looks like, Asamina, you can go ahead. You have the first question.
Yeah, thank you. I have a question regarding your reach. Can you go back to that plot that you showed?
Mm-hmm.
So these are very large mixing angles. And those things would be in equilibrium with the left-handed neutrinos at BBN times. So this is, I suspect, a very highly constrained parameter space from BBN.
From BBN, you're saying?
Yeah. And also X-ray observations, because the moment you couple strongly to left-handed neutrinos, you can avoid producing it, because if you mess up with left-handed neutrinos, you mess up with big bang nucleosynthesis. So you mess up the helium fraction of the universe, you mess up the deuterium fraction, things that we have measured very precisely. So
yeah, that's interesting. So I think most of there's a lot of literature on limits for this, and I don't remember seeing too strong constraints on BBN from that. There are limits for supernova, for sure. I think I have another slot here. So depending on the fraction of neutrinos, if they are dark matter, then there are limits here from X-rays. If you assume 1% is dark matter, you would get coupling limits something like this across there for it.
Yeah, I can show you plots about this. There are constraints. This assumes you have dark matter, but you don't ask where it's coming from. All I'm saying is that the 100 keV mass particle with a large 10⁻⁴ mixing angle will be in thermal equilibrium with the standard model. So you have constraints from BBN.
Yeah, and I agree, like the first stage is definitely the 10⁻⁴. We're not expecting that we're going to reach down the interesting regions. It's going to be the later versions that are more interesting for this. When we get down to the kind of 10⁻⁻10-ish range, I'd say.
Yeah, I as a theorist, I would appreciate these things to be shown on these plots, because messing up with big bang nucleosynthesis is not really model dependent. You have to build some pretty ugly models to make this go away.
Yeah, I mean, we have theorists at UCLA that have models for that some of it depends on what the temperature was, I think, during the Big Bang for that. So they have things where you have a lower temperature for it to evade it. And then again, it depends on how much of this, I guess you're saying two things. So just the X-ray background, you'd say, is not from the constraint you're talking about. You're talking about.
I'm sorry, the X-ray background here is agnostic, the way I understand it being drawn here, is agnostic about where these particles are coming from. All I'm saying is if you have a 100 keV particle, in principle, it's can be produced in thermal collisions during BBN, because we know at the start of BBN, the temperature of the universe was like 5 MeV. So, so the point is that these large mixing angles will affect not only produce, there is an irreducible contribution to the dark matter abundance, that's one thing, and then you will have a constraint from X-rays, but you'll also have a constraint from affecting the helium abundance. So these things are, I mean, maybe the models that I have seen in the literature to try to make this work are not the most, they are contrived to say the least. So messing up with BBN is not a model dependent, it's a measurement, it's an experimental observation. You won't have stars if you don't have the right helium fraction or the right deuterium fraction.
Yeah, I'd be interested in seeing that because I don't remember there being super strong constraints from BBN in these review papers for that.
Yeah, I can send a link to a plot.
Okay. Yeah, and I think from our side too, you know, talking to particle physics people as well, that you're right. I mean, there are astrophysical constraints. There are different models out there, but it's always nice to go in the lab and just measure these things as well.
No, I agree, but it's a question of cost, as always. Like, astrophysics is not. I mean, yes, some cases this is definitely true, but in some cases, some of these are very blunt objects and constraints, and trying to ignore them is not the right strategy. At some point, we need to just give up looking for these things.
Okay, so I think, John, you have the next question. Go ahead.
We always cite Graciela-Galbini's low reheating Big Bang, low temperatures after reheating to suppress the number of the neutrinos early on. And certainly those are unusual models, absolutely. But we always cite them explicitly ourselves. Paul, I had a more technical question. You were just going to cool with your nice oven in 2D, but you're not going to try to cool the third dimension before the
No, actually, so our oven will be going.
I'm sorry.
For the oven, we'll be going into a 3D mont, doing full cooling in a 3D mont, and then basically dropping that into the main.
And that's enough? You didn't think about cooling the third dimension besides with the mod, making a longer region of cooling or something, like a Zeeman slower or something?
Sure, yeah, so the first version, we're just going to go straight from the oven into the 3D mont, but later versions would be upgrade to basically get higher efficiency in the first stage mont by using a Zeeman slower.
Thanks.
Okay, we have time for more questions. Robert, you can go ahead.
Yeah, thanks a lot. I must admit that I'm a great fan of the reaction microscope for obvious reasons. And my question is, if you just trigger on the X-rays, then you, of course, don't have a 4π detector for this, right? Wouldn't it be sufficient to just, trigger on the Auger electrons which you detect and then use this to get the information when your decay was? Or is there a strong delay for the Augers?
Yeah, I mean, they're certainly moving a lot slower for it, and there is a delay. It's an interesting question for it.
I mean, you can test it experimentally anyhow, right? If you have the X-ray, then you can check if you just trigger on the Augers, right? And if you lose anything, because then, I mean, you have a 4π detector, which is, of course, much nicer than just having a fraction of those. Okay.
Yeah, I mean, X-rays, I think experimentally it's nice to have the trigger and run it, but you're right. Like if we did that and afterwards go back and analyze what happened. Yeah.
Okay, we have a few more minutes, so if there are other questions, we can take them. Oh, okay, sorry, John, I didn't see you raise your hand. Please go ahead. My apologies.
Sorry, no, I was using the wrong procedure. I went to the exclamation point instead. So yeah, this is really very interesting. Oh, you can leave that plot, the plot you just had back up. So I think it really does sound to me, I'm not an expert, that there's a real convincing argument that this could be a very interesting area, a very interesting part of phase space for looking. And it's certainly an experiment this size is well worth doing. What I'm kind of wondering is the, I guess I would say, it almost seems like an overlooked area of this space. And I'm wondering, do you know of any other kind of thoughts about why dark matter would be in this range? And let me tell you the context, because when I talk to people, there's this very, very long, wide range of possible dark matter candidates. And it's a huge ocean, right? It's a huge ocean to be fishing in. And any kind of hints, even from maybe not so standard theories would be quite interesting. Is there any other justification for this kind of KeV range other than the two very good ones that you gave?
No, I don't think so. I mean, I think the astrophysical hints that it could be something that is not super cold is one good one. In terms of the KeV range for the neutrinos, I think part of that motivation is trying to evade these limits combined with the lower initial temperature during the Big Bang. If you go anywhere else, then you can't evade the limits. But
are there any other support for the seesaw mechanism?
Yeah, maybe we'd ask the theorists. I feel like that's the main explanation. I don't know if there is another explanation for how the neutrino masses are small.
Yeah.
Other than seesaw, that's the only main one I've heard before.
All right, thanks.
Mm-hmm.
Okay, it's time for a break, but I'll, as my prerogative as moderator, I'll let Asmina make one more final comment before we go.
Yeah, so let me just say this again. At some point, we need to let theories die. So I think, yes, I agree with the last, maybe perhaps phase 3, the bottom corner may be allowed. But at some point, I mean, we shouldn't, if we modify our theory to add, for example, the Gelmini, I've seen the Gelmini, some of these papers, they sometimes have also mass dependent, they have a scalar field and you change the mixing angle and the mass of the neutrino based on the mass of the scalar. So they add ingredients just to modify the theory so that you open up the parameter space. At some point, we need as a community to we just need to let things die, because the parameter space, as has been mentioned before, is ginormous. And we need to be able to allocate the resources very, very, very carefully.
Yeah, I mean, I guess that's, I feel like, one opinion. I think many of the other theories, even the low mass things we're looking for, are pretty exotic as well. And this is, a lab scale experiment. It's not a LHC experiment. It's not a particle collider experiment. It's something that's pretty small scale.
Yeah, but the other things are not included by anything already. Sorry. The other thing is, let me say the other thing that, what I want to say about the seesaw, that's a general comment. The seesaw mechanism requires that the right-hand neutrino are at close to the GAD scale, maybe at the TeV scale. I mean, you could have very light Yukawas and make it, but it's not necessary. KeV is not special. So I'm not trying to dampen anything. I just, as a theorist, and I know there is another community, but I can tell you there is a large part of particle theorists that respects astrophysical constraints, and these are BBN. When you test these things, you're testing a theory that is, I mean, in a way, you have to add the scalar, you have to add the low heat. You're not testing just the scalar neutrino, you're adding all the requirements that remove the constraints you already have to the minimal scenario. So you're no longer testing a minimal theory. That's the thing. That's all. In principle, and in principle, yeah, like we should do everything. Like, honestly, we should do every experiment, and in principle, checking things that are maybe already excluded is also good. But in reality, at some point, we should say this is probably not here. If our assumptions, if we finish everything and then we find that our assumptions that, oh, well, it looks like there is still a hint after everything we've done, when a parameter space that was still excluded, then we go back and look at it.
Okay, we're getting sort of into our break time, but I'll let John have the last comment.
Okay, yeah. So I certainly don't entirely disagree with what Mina is saying. But I do feel like to chime in. One is that those constraints can just simply be wrong, and they come from a different community. So having two different ways of connecting with them is a good thing, right? That's how we kind of move forward in science. The other is, I would just say that, when you're doing a precision measurement like this, if you are, this is just my opinion, kind of a, what do you call, broad opinion about experiments, is if you're doing a precision measurement that pushes a value, really quite far in one direction, the history of science has kind of shown that you may not find what you were expected to find, but it's almost always worthwhile to do so. And of course, I agree completely. It depends on what level of resources you're applying, right? If it takes a day in the lab, you can, I once did a cold fusion experiment for a day in the lab, right? And if it's on the other hand, something, like a multi-billion-dollar, accelerator, I would say that there was, perhaps as exotic things that were done to justify that. So I just, it's a really interesting debate. I think it's a great debate to have because it keeps our field healthy to figure out what makes sense. So anyways, that's my 2 cents. I wish I had a beer.
No, the only thing I would like to say, just to finish, I would like to ask you as a theorist to put in your plots. You can do that. Put the astrophysical constraint on your plots. Can you do that? Like, just put them on where the curve is. The BBN ones, no, they are not there. Those are not it.
Okay, you'll have to show me that. I mean, we have it.
I send a link to a plot. Please put them there, and then you can argue. We can check them, but please be upfront about it.
There's even a corner of space at very high admixture, around 100 keV, where the lifetime is so short of these horrible things that they decay before the BBN era. I mean, I know that sounds crazy, but that's on the plot, and it doesn't actually need low reheating temperatures even. There's actually a corner because the constraints are so poor, and if they can just even phase one would help with that particular set of constraints. That doesn't break BBN or anything. It's a really weird slice of safe space. So
that's great, but put a line on it because those lines are there. I sent a plot. These are old papers. Please put them on. That's all. And there is still parameter space. Just be upfront about it, about what we're checking, what we know, what we don't know, and then people can make their judgment whether to accept these things or not.
Yeah, I mean, it's tough. We can have 20 different lines on there, and the other point is this is an experiment that we're placing these constraints. Whether or not it agrees with all these other astrophysical constraints. We mention them in our papers for sure. We reference it. But we will be placing these constraints in the laboratory of a coupling and a mass scale for this.
Okay. Well, I'd like to politely interject. So I will point out that Mina put an interesting link in the chat. So if you're interested, you can follow up on that. And I'd like to thank both of our speakers again for the wonderful talks. And so I think we should probably have a little bit of a break. So I'll request that the people at MIT, if you could open up the breakout rooms. I think we'll have like a 7-minute break. We'll reconvene at 3:25. But if you can open up the breakout rooms, and I'll ask if Mina can go to the first breakout room, and Paul, if you can go to the second breakout room, and then people can ask some more questions, and we'll reconvene at 3:25. Thank you. So Paul, are you able to join breakout room 2? Oh, yep.
Yeah, he just did.
He just went. Okay, great. Okay, thank you. Hi, Lars. I don't know if you're online right now, but if you're ready and if you'd like, maybe you can maybe try sharing your screen and make sure there are no technical problems.
Sure. Can you hear me?
I can hear you. Yeah.
Great. That's perfect. Well, I'm practically ready. I can share my screen now. So. This is working?
Yeah, I see your title slide, and maybe you can try to advance one slide. Yep, that looks good.
Perfect.
Oh, and the animations even work. Great. Okay. Yep. Yeah. Okay, good. Yeah, I assumed that everything would work okay. If it didn't, then I don't know if 5 minutes is enough time to fix the problem, but we don't have to worry about that.
Just give me a second. We'll be right back.
Yeah, no problem. Okay, so I'd like to request the MIT tech support if you can give people a 1 minute warning to close out their discussions in the breakout room so we can start the next session shortly.
You got it.
Thank you. So Lars, we'll just wait about a minute to let people come back in, and then I will introduce you, and then you can give your talk, and then as I did for the other speakers, I will attempt to politely interject when there's 5 minutes left, just to give you a warning. Okay, so it looks like people are returning from the breakout rooms, and I appreciate the lively discussion, and so hopefully we'll continue to have that. But we should start our next session. So I'm delighted to introduce Lars van der Vense, who is at Gilla currently, and he'll be talking about prospects for constraining temporal variations of fundamental constants with a thorium-229 based nuclear frequency standard. You'll have 25 minutes for your presentation, 10 minutes for questions, and I will interject when there's a 5-minute warning. Lars, you can go ahead.
Yeah, thank you, Jaideep, for the kind introduction. It's my pleasure and also an honor for me to present here the most recent progress towards the development of a nuclear optical clock, with a particular focus here on how a nuclear frequency standard could potentially be used to probe for temporal variations of fundamental constants in the future. So now actually we just checked it, but now changing the slides doesn't work anymore.
Oh, okay. Maybe you can unshare and try resharing again.
Yeah, probably I need to. Sorry for that. Oh. No, still frozen. I think I have to. 1 second. So it's working on my screen now. Now I'm trying to share again.
Okay.
So now, sorry. So a quick outline of my talk. I will start with the motivation, then coming to the main part of the presentation, which actually is a probe of potential temporal variations of fundamental constants using thorium-229. And finally, in the third part, I will discuss a little about the most recent progress in this field. So we all know that laser spectroscopy of the atomic shell has led to significant fundamental physical progress. And we have heard about many examples in this field, which is the electron EDM search, for example, the search for fundamental symmetry violations, search for dark matter, and also, of course, the search for temporal variations of fundamental constants. Now, the principal idea is also the nucleus, and you all know this, possess a large number of excited states, and potentially we could do maybe the same thing with nuclear transitions instead of only focusing on electronic shell transitions. So we have a total of about 2.7 times 10 to the 5 nuclear transitions known, but unfortunately not a single of these nuclear transitions has been investigated via precision laser spectroscopy. Although if we could do this, actually this would offer great prospects for additional fundamental physical research. So the idea is, why can't we just shift all the progress that we made for atomic spectroscopy into the nuclear regime? And Well, there is a simple answer why this has not been done yet. And the reason is that most of these nuclear transitions have a lot larger energy scale, which is in the kiloelectron volt to mega electron volt range. And opposed to that, the laser technology is actually located in this electron volt regime, because laser technology makes important use of atomic transitions. So there is practically almost no overlap between the nuclear energy scale and the electronic energy scale or the energy scale of laser technology. There is, of course, this one exception with this free electron lasers. However, free electron lasers are broadband. So with this regards, they cannot consider as precision machines, although there is certainly hope that this will change in the future. So there is one exception, though, which is this particular transition of the thorium-229 nucleus, which has an excitation energy of only about 8.1 electron volt. And how special this is indicated here in this energy half-life diagram, where all nuclear metastable excited states are indicated that are known by today. And as I said, most of them are in the electron volt region of keV to MeV. But then, like 3 orders of magnitude below this, there is a special thorium-229 nuclear transition, which is actually not in the region typical for nuclear excited states, but more in the region of electronic shell states. And also the lifetime is somewhere in a region where optical atomic clocks are operational today. So this is a potential, offers a potential for future precision laser spectroscopy of a nuclear transition. And this is just a short advertising slide. So why thorium-229? As I said, we have a total number of more than 3,000 isotopes, 175,000 known nuclear levels, almost 270,000 known nuclear gamma transitions, but there's only this one particular thorium-229 excited state, which would potentially allow for direct nuclear laser spectroscopy. It has the lowest nuclear excited state of all isotopes with an energy of about 8.1 times 10 to the 11, 8.1 electron volt, sorry, and a radiative lifetime of about 10,000 seconds. So the line width, the relative line width of this transition is exceptionally small in the 10 to the minus 20 range. So this would be suitable for the development of a nuclear frequency standard. So the principle of operation is practically exactly identical for those of optical atomic clocks. So what you want to perform narrowband laser spectroscopy of your nuclear transition, and you want to stabilize your narrowband laser to this nuclear transition frequency by a feedback loop. So you can, for example, imagine that there are photons emitted in the decay of this metastable excited state. You detect the photons, and in this way you feed the information back to your laser system to actively stabilize it to the nuclear transition. In this case, you know that your frequency will always be constant, or at least always be matching that of the nuclear transition. So you can then count the frequency of the laser oscillations with the help of an optical frequency comb. And this gives you your frequency standard or even your clock signal. There's one interesting advantage that was always considered, namely that the nucleus is very small compared to the atomic shell, which leads to very small nuclear moments. So potentially this nuclear clock may have advantages in terms of stability, because due to the small nuclear moments, like external perturbations are less coupling to this nuclear transition. And the expected systematic frequency uncertainty was predicted to be on the order of 10 to the minus 19, which is about a factor of 10 of improvement compared to the currently best published accuracies of optical atomic clocks. So now there is not only one type of nuclear optical clock, but there are like a couple of different concepts. The one that is probably most famous is the so-called single ion nuclear clock, where you simply trap a single thorium-229 3+ ion in a Paul trap. You then laser spectroscopically excite your nuclear transition, and you probe whether this nuclear excitation was successful by probing the hyperfine structure of the atomic shell, because this is expected to shift, because the spin states of nuclear ground and isomeric states are different. So you get a different hyperfine structure for these both nuclear states. And this is something that you can distinguish by laser spectroscopy of the electronic shell. Now one can, of course, also consider to not only use a single thorium-229 ion, but you can probe a chain in a Polar trap, like a linear Coulomb chain of thorium-229 ions. In this way, you gain significantly in statistics, which would help you in the end in terms of stability of the clock, which we consider as a multiple ion nuclear clock. But the principle is identical here. Now, there is a fundamentally different approach, which is a so-called crystal lattice nuclear clock. And here you make use of the idea that the nucleus is to a large extent unaffected by the electronic shell. So you can potentially combine multiple of these nuclei in a solid state crystal lattice environment. And here you gain drastically in statistics, because here you can have like 10 to the 13 or even more atoms that are sitting on a very small volume. So you gain significantly in density and therefore in statistics. The idea is to do the same thing, like perform laser spectroscopy of your nuclear transition, but now the way you detect whether you have successfully excited your nuclear state is via the emission of photons that are emitted directly in the isomer's gamma decay to the ground state. And there is a fourth concept which was recently put forward by us, which is that you can, instead of using the photons here, you could also potentially use the internal conversion electrons that are emitted in the internal conversion decay of the isomeric state. And in this way, perform laser spectroscopy and use these as a signal to feed back towards your laser system. So these are the four different nuclear clock concepts that are currently investigated by different groups around the world. And how can this help us to actually constrain temporal variations of fundamental constants? So the idea is essentially that a nuclear frequency standard provides us with a novel physical platform, because here the laser frequency couples directly to the nuclear Coulomb energy of your system, and any change of the fine structure constant alpha leads to a change in the Coulomb energy. So essentially you couple your fine structure constant alpha via some parameter towards a frequency variation of your system that you probe. Now, if you look into detail into that, it's a little more complex, because actually, so the ground state energy consists out of a Coulomb energy term combined with an energy term that is coming from various different components of the strong interaction. So this is for the ground state, but you have the same thing also for the thorium-229 excited state. So you have a Coulomb energy component and a component that constitutes out of different various strong interaction terms. So in case now that the Coulomb energy term of your ground state and the Coulomb energy term of your excited state would be just exactly identical. Now, if you couple with your fine structure constant and start to stretch these Coulomb energy terms somehow, because you say you changes your fine structure constant alpha, and these are exactly identical. In this case, you wouldn't see any difference in the frequency, right? Because simply the frequency would change, or both energies would change in parallel, so that in the end, the frequency, which is just the difference of these two things, wouldn't change at all. So essentially, your sensitivity towards a fine structure constant change relies on the fact that you must have a Coulomb energy difference between these two states. And this is exactly this delta VC, which is part of this parameter here, which gives you the sensitivity of your coupling. And now there was a lot of theoretical effort and trying to actually infer how large this Coulomb energy difference was, and the predicted values ranged from, I think, 10 to 6 to 0. So essentially the result was that it was impossible, purely based on theoretical input, to infer a value for this Coulomb energy difference for a long time. So all this was put forward by Victor Flambaum for the first time in 2006. And then there was some trouble in actually inferring this value for delta VC. And then in 2009, Julian Berengut came up with an idea that one could potentially actually infer this Coulomb energy difference by experimental observation. And the idea was that you could probe the hyperfine structure of the ground state and the excited state, but the hyperfine structure of the shell laser spectroscopically. And then he gave a formalism, or Julian Berengut, together with the Flambaum group, gave a formalism that allows one to derive a value for delta Vc as soon as you have the fine structure, shell fine structure measured. And this was done for the first time in 2018 by PTB. This was this paper of Johannes Thielking, and we were working at the time in collaboration with them to perform laser spectroscopy of the ground state and the excited state. And we were hoping at the time that it would be possible to derive a value for delta Vc for the first time. But unfortunately, at that time, the error bars were so large, so our measurement was not precise enough to allow for a secure exclusion of zero of this delta Vc. So no conclusion could be drawn at the time for potential sensitivity enhancement of this nuclear state for alpha. Now, very recently, actually in 2020, the Victor Flambaum group used these results in combination with some additional input, namely that the nuclear density of ground and excited state is constant, which is a very reasonable assumption. And by inserting this additional assumption, for the first time, they were able to derive a value for this Coulomb energy difference that is inconsistent with zero. So for the first time since 2020 now, and this has been going on for the past 15 years, we have a value at hand that tells us, okay, we really have a drastic sensitivity enhancement of a nuclear optical frequency standard for temporal variations of fundamental constants. So approximating this as 10 to the 5 electron volt, and then inserting this value here and saying we have about 10 eV here, we have a sensitivity factor of 10 to the 4. Now we can combine this with the predicted precision of such a nuclear frequency standard, which was estimated to be 10 to the minus 19, and we come up to that we can probe potential changes of delta alpha over alpha with a sensitivity of 10 to the minus 23, which would pose a 5 orders of magnitude of improvement compared to the currently best constraints that were given. So this offers some exciting opportunities for using the nuclear clock actually to probe temporal variations of alpha to high sensitivity. So if this is so great, why hasn't the nuclear frequency standard yet been built? And the problem is that for a long time, the community had a fundamental problem, namely that the thorium-229 isomeric energy was not sufficiently well constrained to actually start with this precision laser spectroscopy experiment. However, also this situation has recently changed to some significance, namely that since 2019, 7 new energies were published, which essentially solves this long-standing problem. And what I show here is the development of the measured values for the isomeric energy over time. So it started back in 1994 with about 3.5 eV. Then there was another value, 2005, which was 5.5 eV. Then for a long time, this value of 7.6 eV, slightly corrected to 7.8 eV, was around, which was from 2007, 2009. And now we have these 7 new values starting from 2019. And if we take the weighted mean of all these 8 average values, we obtain an energy of 8.1 eV, which corresponds to roughly 150 nanometer. I think the more important information is even that within the past couple of years, these measurements were relatively consistent. So we think that we get slowly getting a good feeling that the nuclear isomeric energy is actually there where we had expected. So it's kind of saturating here. Now, the value that was obtained in my former lab here in 2019, this was at the time highlighted by Nature as a title page. And this is the measurement that was done in my former PhD group. And this is why I would shortly shortly explain how this measurement was done. It was based on a previous direct observation of the thorium-229 isomeric decay. And if I talk about the direct observation of thorium-229M, I have to distinguish between different decay channels. So one decay channel is the ordinary gamma decay, where the metastable state just fades down to the ground state via emission of a photon, which is a standard gamma decay. However, for all energy nuclear transitions, in particular the low energy nuclear transitions, there is a competing decay channel, which is this internal conversion decay, where the thorium-229 metastable state decays down to the ground state via the emission not of a real, but of a virtual photon, which then immediately couples to the electronic shell. And actually what's happening is that an electron is emitted from the shell, which releases this energy. So these thorium-229 internal conversion decay is favorable by 9 orders of magnitude if it's energetically allowed. And it's energetically allowed in this neutral thorium-229 atom. So in case that we want to measure any gamma decay, we need to work with thorium-229 ions, because otherwise this 9 orders of magnitude IC decay will just strongly hit in. It also reduces the lifetime from 10 to the 4 seconds, which is the radiative lifetime of the isomer, to about 10 microseconds, which is the same 9 orders of magnitude reduction. And this gamma decay has not been observed under the present day, whereas in 2016, we managed at the time to experimentally observe this internal conversion decay of the isomer, which was the central result of my PhD thesis. So now, how did we use this internal conversion decay to obtain a value for the isomeric energy? And the way we did was we populated the isomer in a natural decay branch in the alpha decay of uranium-233, which populates the metastable state via a 2% decay branch. So most of it, of the thorium-229, which is produced in the alpha decay of uranium-233, is in the ground state, but we have 2% in the isomeric state. And then we created a pure thorium-229 ion beam from that with 2% of the ions in the isomeric state. We neutralize the ion beam, which triggers the internal conversion decay. And then we measure the kinetic energy of the internal conversion electrons that are emitted in this decay. So this is the experimental setup that we used. Essentially, we were starting with a uranium-233 source, which was placed in a buffer gas stopping cell. And this produces continuous thorium-229 nuclei. And these nuclei are then capturing electrons, and they have sufficient kinetic energy to actually leave this thin uranium-233 source. They are stopped. So these ions that we are producing in this way are stopped in a buffer gas stopping cell. We collect them with a radio frequency funnel system, and then they are ejected through a Laval nozzle and injected in the radio frequency quadrupole, where we form an ion beam from this nuclei. And afterwards, we mass purify the ion beam. We neutralize it in a graphene foil, and then this neutralization triggers the decay of the internal conversion, and the internal conversion electrons are then captured by a magnetic field and guided into a magnetic bottle retarding field spectrometer, where we can apply retarding fields to measure an integrated kinetic energy spectrum of the electrons. And this is a spectrum that was actually measured. Now it's an integrated spectrum, and unfortunately it consists not out of a single line, but it consists out of multiple lines, because it's not only the ground state that is populated after the neutralization, but we populate multiple excited electronic states in the neutralization, and also multiple excited electronic states are populated after the internal conversion decay, which leads to a complex multi-energy spectrum, and it takes some theoretical input to draw conclusions to an actual energy value from the spectrum, which was with great support of Pablo Bilou and Adriana Palfi, obtained a value of 8.28 electron volts at the time.
5 minutes.
Sure, thanks. So what do we learn from that? So this new information that we have now about the isomeric energy opens new opportunities for laser spectroscopy of thorium-229M, because now for the first time, the energy is sufficiently well constrained that we actually can start to perform laser spectroscopy experiments. And 5 groups worldwide are currently aiming or preparing experiments along this line. One of this is our experiment that we are preparing right now in the group of Junye, Gila, and Changkun will talk about this in the next presentation. There are two groups that are working on 4-wave mixing in a noble gas, which is the group of Eric Hudson at UCLA and the group of Eckhard Pike at PTB. And there are the three groups, Gila, the group of Peter Tirov at LMU, where I was previously working, which are investigating the 7th harmonic of an ytterbium fiber system, and the group of Torsten Schumm, where the 5th harmonic of a titanium sapphire laser system is investigated. And these are all frequency comb experiments. I would quickly highlight the experiment that is going on in the group of Christian Schneider and Eric Hudson at UCLA. They are using pulse diode lasers, 2 pulse diode lasers. One of them is frequency doubled, the other one is tunable. And then they overlap them and form some frequency mixing in a xenon gas jet to generate tunable pulsed VOV light. And this light is then used to irradiate a thorium-229 coated substrate. And the idea is then to measure like the internal conversion electrons that are emitted after each laser pulse with an MCP detectors. And excitingly, these experiments are just about to start these days. So this brings me to my summary. I told you that laser spectroscopy of a nuclear transition has not yet been achieved, although if successful, it would offer exciting new opportunities for fundamental physics. In particular, it is expected and one could gain by 5 orders of magnitude in the probe for temporal variations of the fine structure constant alpha. Today, due to its low excitation energy, thorium-229M seems to be the only known nuclear excited state that permits direct laser excitation, and recent improvement in the measurement of the transition energy offer now novel opportunities to perform nuclear laser spectroscopy. There are 5 experiments ongoing worldwide that prepare this, and some of these are starting soon. So I hope I have convinced you that there are some exciting new prospects for the development of a nuclear frequency standard. And of course, there are many more groups working on that, and I could only give a small fraction of the ongoing research on the thorium-229 nuclear transition worldwide right now. So this gives you a rough impression on the groups that are working on this development. And with this, I would like to thank you and also point out that this work has been done with a large collaboration with many people involved directly or indirectly. And the people that I've been working with is in particular Changkun and Jack Doyle, Peter Tirov, Benedikt Seifel, and Junye, who is our current boss and pushing this opportunity with great enthusiasm. Thank you.
Okay, thank you for a wonderful talk, and I will speak on behalf of everyone and say you've convinced us this is extremely exciting. As we have time, we have plenty of time for questions, so if you'd like to ask a question or make a comment, please just put an exclamation point in the chat, and I'll call on you in the order that it appears. While we're waiting, I'll mention that Jacek has made an interesting comment in the chat with a link to a paper. Maybe Jacek, if you'd like to comment on that, you're welcome to unmute yourself and comment.
Thank you, JD. I'll be most happy to explain what I mean. What I call the basic nuclear property is the pairing phenomenon, by which, if you look at nuclear configurations, they are mixed. They are not pure, and the mixing is of the trivial type, namely configurations which are close to the Fermi energy and close in energy one to another, are mixed 50-50. So whatever the source of these two configurations, the configuration of the ground state and the isomer in thorium, if you include pairing correlations, they will be 50-50 mixed. It means by definition, the Coulomb energies will be just the average of the of both configuration and equal for both states. So we invoked this argument in this paper in 2009. I don't know how experimentally this could be proved, but if this argument, well, it of course can be contested by saying that pairing description is based on DFT and it's not an exact solution. However, there is an overwhelming evidence that pairing is in action in nuclei across the mass chart. And that would be really interesting to disprove this argument. So, yeah, I'd like to hear your opinion on that. But nevertheless, the talk was fantastic and very interesting, and the idea of having a clock is great. The only thing which I would contest here is the possibility of using this for measuring time variation of the fundamental constant. Thank you.
So thank you very much. If I understood correctly, so the question is if this delta VC of 10 to the minus 4, which is assumed here, is actually correct, or if this is actually a useful quantity to use for defining the sensitivity of fundamental constant search. I think well, we rely mostly actually on the theory that was put forward by the group of Victor Flambaum. As far as I understand, they use very fundamental physical approaches to derive these values, but I think I cannot give a qualified answer to the question if this is actually now, so this paper, this Fadeev paper, which was published 2020, if this is now really the end of the story, or if there will be future changes to this constant, which may, as you said, in the end then turn out that everything what is put forward has been put forward so far is actually wrong, and canceling this term back to zero, which would be, of course, a very unfavorable situation.
Yeah, very sad conclusion. I fully agree.
I think if Victor is here, he can probably comment most qualified on this, but I'm not sure if he's actually right now in the meeting.
That's a good question. He certainly was here earlier this week, but it doesn't look like Victor is on right now. Arian, you can ask your question next.
Hi, just brief question. When you say shine 153 nanometer light on this atom to excite the nucleus, say, how do you make sure you don't ionize it?
Oh, I mean, depending on which concept you want. So we have this different concepts. So in the single or multiple ion nuclear clock concepts, essentially you have thorium-3 plus ions, and thorium-3 plus has an ionization potential. I think it's more than 20 eV that you need to further ionize it. So certainly you can't ionize it with this 150 nanometer laser light. Here in this case, the crystal is simply transparent. So you wouldn't ionize them, and thorium-229 is in the 4+ charge state in this crystal lattice environment. So the only concept where you ionize is actually this concept here of the internal conversion clock. And there you definitely will ionize. And this ionization will absorb a large fraction of your light wave, which is defined by this distinction coefficients, how quickly your light distincts in the material. But still, you can propagate with this light to about 1 nanometer, 10 nanometers into the material. And there in this first 10 nanometer layer, you will still have sufficient light intensity to excite a large fraction of your nuclei. And afterwards, immediately it will grab electrons. So you ionize, but of course you have a quick supply of additional electrons because your substrate here will be a metallic substrate. And then for the internal conversion electrons, you want a neutral, right? So you immediately neutralize again.
Thank you.
Okay, we have another question from Makoto. Go ahead.
I thank you for really the exciting development that you reported. I'm just trying to get a feeling about this 10 to minus 19 estimate that you quoted for the clock precision, and the normal optical ion and atom clocks sort of pushing beyond 10 to minus 18 and maybe towards 10 to minus 19. And so, I mean, if it's, I guess, I mean, if it's the same, then I mean, the normal atoms is easier to handle. So I guess, is this 10 to minus 19 estimate was kind of conservative, or is it it's beginning and you can go much further than regular optical clock in the end, the regular atomic clock, or what's your feeling about? I mean, notwithstanding this fundamental physics aspect that I think is great, like this the constant change, variation and stuff. But as a optical, there's also a frequency standard. What's your feeling about this?
My personal feeling, but yeah, well, it's only a feeling. I think this calculation at the time were done very, very carefully. So I think this 10 to the minus 19 is a quite good number to assume. On the other hand, I think it will not go significantly beyond that. So admittedly, I think that in the end, the accuracies of optical atomic clocks and nuclear clock will probably approach the same limits finally. And then, as you said, the atomic clock would be a much simpler device to handle. So I think the fundamental physics aspects are really dominating the interest, or start to dominate the interest in this nuclear transition. At the time, 2012, when this value was published, I think optical atomic clocks were in the 10 to the minus 16 range, and they still gives this argument, we can get 3 orders of magnitude better. And but in the end, it turned out that optical atomic clocks are just extremely high accuracy, and there is no fundamental limit yet approach for the accuracy of optical atomic clocks. So my feeling is that both will in the end go to the same limits.
Okay, thanks very much.
Okay, great. So let's thank our speaker again, and we should move on to the next speaker. So Lars, if you could unshare your screen, and I'll ask our next speaker to go ahead and share your screen. So I will, as usual, we have 25 minutes for the talk. I'll interject at 5 minutes. And then we'll have 10 minutes for questions afterwards. So I'd like to introduce Chuan-Kun Zhang, also from JILA, who will talk about toward direct VUV frequency comb spectroscopy of the 229 thorium isomer nuclear state. So you can start when you're ready.
Okay, can you hear me now?
We can hear you, and we can see your title slide.
Great. Thank you very much for your introduction. I'm Chuan-Kun, and I actually work with Lars together in Professor Jun Ye's group at the JILA and the University of Colorado Boulder. So today I would like to share with you our experimental effort toward the direct VUV frequency comb spectroscopy of the thorium-229 nuclear state. As we have already learned from the previous talk given by Lars, and also actually from the talk of Mariana Safronova earlier in this morning, it's great to have a nuclear-based optical clock using the thorium nuclear transition. As a recap, I'll repeat saying that we have the potential opportunity of building a very accurate optical clock using the thorium nuclear transition, just because of its much smaller size and high resistance to external perturbations compared to atoms. And this 10 to the minus 19 predicted clock accuracy, as we discussed before, is also rivaling today's best optical atomic clocks as an alternative. Also, since the nuclear transition is largely decoupled from the electronic states, we can embed potentially a large number of nuclei into a solid state environment whether a crystal or a thin film. This would give us a large statistics for high clock stability. Also, we can potentially, since this is a solid state optical clock, it can potentially be made portable for various applications outside of the lab, various precision measurement applications outside the lab. The most exciting thing for us, of course, is that we can use this nuclear clock as a very sensitive probe for fundamental physics. And as also was explained before, we are essentially probing the nuclear energy scale on the mag electron volt level, hopefully, with a precision measurement tool of sub-millihertz accuracy. So this gives us a huge enhanced sensitivity for temporal variation of fundamental constants. And what I find interesting is also that we essentially are probing a new quantum system that wasn't explored well before. So this gives us new opportunities in probing coupling between, say, for example, nuclear and electronic states, and for potential new discoveries. In the past few years, we have witnessed a great improvement in the nuclear transition energy determination by several different experiments. And we have seen from the last talk that one can probe the direct decay of the thorium excited state to its ground state and extract the transition energy by doing internal conversion electron spectroscopy. Also, in a perhaps more historical approach, one can do indirect gamma ray spectroscopy, measuring essentially the gamma ray transitions from the higher excited state to excited state or to ground state of this thorium clock transition. And these gamma ray spectroscopy can be done very accurately, actually, using these microcalorimeters, which essentially measures the individual gamma ray photon energy very accurately. So this kind of approach also produces very recent results in the past year. Just now with all these experiments, we now know the nuclear transition energy is at about 8.1 electron volt, corresponding to about 153 nanometers with plus minus 2 nanometer-ish uncertainty. Now, this uncertainty is small enough for us to start our direct laser excitation searching for the nuclear transition using a laser. And by using a laser, we also expect that we can get another 10 to the 6 improvement compared to the previous energy determination values. And in our approach, our technology and the knowledge can be directly used for constructing a nuclear-based optical clock. So the biggest challenge actually for doing this laser spectroscopy of the nuclear state is that there are essentially no CW lasers operating at 153 nanometers today, unlike the visible and near infrared. So you may ask, why don't we simply build one? Because after all, building a laser could be as simple as putting some gain medium inside an optical enhancement cavity. However, at 153 nanometers, this is almost nearly impossible, because there are, in the first place, not many materials even transparent at this wavelength. And essentially, we don't have any gain medium suitable for developing such a laser. Also, the optics performance is generally not great, so one cannot construct a high finesse cavity for 153 nanometers. Now, this means we need to rely on a nonlinear frequency conversion to reach this 153 nanometer wavelength. However, another challenge is that essentially today we also don't have phase-matched nonlinear conversion crystals for doing so. So all the nonlinear frequency conversion experiments has to be done in either gas or very thin films. This means we need a very high laser peak intensity to achieve efficient frequency conversion to 153 nanometer. So we want to operate our laser in a pulsed operation modes. Also, on the other hand, we want to drive a nuclear clock transition. So we need an extremely narrow laser line width. Now, the two requirements of having very short laser pulses and a very narrow laser line width seems contradictory. However, these can actually be realized simultaneously using an optical frequency comp. So basically, optical frequency comp, we have a femtosecond pulse train in the time domain. So we have high laser peak intensity due to the very short femtosecond pulses. But this femtosecond pulse train is so stable that that its Fourier transform in the frequency domain is composed of very narrow frequency spectral lines separated by the frequency comp repetition rate. And all these narrow lines would be extremely suitable for precision spectroscopy experiments. So I want to highlight that there are currently a worldwide effort in developing different laser systems for the nuclear spectroscopy. And one way, as Lars mentioned, was doing resonant four-wave mixing in a xenon gas. So basically, you can rely on the a two-photon resonance in xenon and generate a broadband tunable vacuum ultraviolet nanosecond laser. However, it's a broadband pulsed laser, so essentially you're sacrificing the very fine spectral resolution for the broadband tunability, making it very suitable for initial transition searches, but cannot be directly used for the nuclear clock operation. Another different approach is to use a Ti-Sapphire laser and generate the fifth harmonic of it in a very thin aluminum nitride film. So this is a very nice all solid state approach and it generates a coherent frequency comp. However, only very relatively low powers, less than 1 microwatt, has been demonstrated so far. In our lab, we choose to actually use the 7th harmonic of a ytterbium fiber frequency comp. So in this approach, we also get a coherent frequency comp, and actually we have a relatively high, in this case, more than 500 microwatt of average power available for the thorium spectroscopy experiment. So the way we generated this 7th harmonic frequency comp is really a very nice combination of precision spectroscopy and strong field physics. For the precision spectroscopy aspect, we wanted to have a highly coherent frequency comp. So we need a high frequency comp repetition rate, typically on the order of tens to hundreds of megahertz. On the other hand, we wanted to generate the 7th harmonic of this comp efficiently. So we work in the non-perturbative harmonic generation regime, where high laser intensities on the order of 10 to the 13 to 15 watt per centimeter square is typically used. So in combination with other reasonable parameters, this essentially means that we need a very nice coherent femtosecond frequency comp with on the order of 10 kilowatts of average power. Now, this is very challenging in single pass experiments, but what we do is we use a femtosecond enhancement cavity to get a very high average laser power. So in the frequency domain, we can view this as each of our frequency comp lines shown here in blue, separated by the frequency comp repetition rate, actually can be matched directly with each of the cavity enhancement cavity resonances shown here in red, separated by the cavity free spectral range. So by doing so in the time domain, we have a largely enhanced pulse, a few hundred times more stronger than the input laser pulses inside our enhancement cavity, and we can place a inert gas target right at the cavity focus and generate our 7th harmonic inside this gas medium. So the idea of or the approach of using enhancement cavities for generating such a frequency comp in the extreme ultraviolet really took almost 20 years of research of development effort so far. The initial idea of using enhancement cavity to enhance the fundamental femtosecond laser in the infrared was proposed already in 2002 and was demonstrated in 2004. And already in 2005, the first demonstrations using such essentially this concept to generate XUV comp was already published. But at that time, for the initial demonstrations, the available frequency comp power is relatively low, about a few hundred picowatts per harmonic order. But since then, in the next few years, there has been a significant technological development in this field. And already in 2012, we demonstrated in our group that one can do direct frequency comp spectroscopy using such a XUV comp for argon transition at 82 nanometer wavelength. So one might ask if this very intense high harmonic generation process inside the enhancement cavity could deteriorate the phase coherence of the frequency comp and maybe result in the eventual corruption of the frequency comp structure. And actually in 2014, we already measured by performing optical heterodyne measurement of 2 XUV frequency comps generated separately. Essentially, we find that in for measurement times longer than 1 second, we don't observe any decoherence or phase noise degradation due to the harmonic generation process happening inside the cavity. In 2018, by the full understanding of the plasma dynamics, etc., inside the generation medium, we achieved phase-matched XUV comp generation for the first time. This gives us another order of magnitude boost in the available frequency comp power just 3 years ago. And just last year, we so it's one thing to generate the XUV comp efficiently inside an enhancement cavity. However, because there are not many transparent materials, essentially, it's also very hard to extract the generated XUV comp out from the enhancement cavity. So in the last year, we've constructed a noncollinear enhancement cavity geometry where we have 2 beams crossing each other and generating the harmonics right at the bisector angle. So by doing so, the generated XUV comp can directly be extracted out from the enhancement cavity. And we now have more than 500 microwatts of available XUV comp power per harmonic order, more than 6 orders magnitude improved from the initial demonstrations in the past 15 years. So going to our actual experimental setup for the nuclear spectroscopy experiment, we start with a ytterbium fiber frequency comp, which I'll go into more detail in the next slide. We couple that into our enhancement cavity to generate the 7th harmonic. And the 7th harmonic is then selected and directed to our detection system for doing the nuclear spectroscopy experiment. So I want to highlight that our fundamental frequency comp is really the first tunable high-power ytterbium fiber frequency comp designed specifically for this thorium spectroscopy experiment, and it's pictured here. So we have some basic parameters. We have 75 megahertz laser repetition rate, 150 femtosecond pulse duration. We get more than 50 watts output power from this comp. A very nice feature is that we can tune the central frequency, central wavelength of this comp from about 1040 nanometers to about 1070 nanometers. So this allows us to cover a bit larger range than the 1 sigma uncertainty of the thorium-229 nuclear transition using its 7th harmonic. Another very important, very crucial requirement for this fundamental comp is that we need a ultra-low phase noise. This is because in the 7th harmonic generation process, essentially it's the timing jitter that is transferred between the fundamental and the 7th harmonic. or when we are considering noise, it's the timing jitter that is transferred. So for equivalent timing jitter, the 7th harmonic, due to its 7 times higher carrier frequency, we accumulate a 7 times more larger phase error compared to the fundamental. So if we wanted to have a very coherent 7th harmonic frequency comp, we needed to have a really ultra low phase noise in the fundamental. In this plot, I'm showing you the phase noise of our phase noise power spectral density of our fundamental frequency comp when it is locked to a CW stable reference laser multiplied by our enhancement cavity transfer function, actually, because our enhancement cavity here in the green line essentially low pass filters the phase noise of our fundamental comp. So integrating from high frequency down to 10 Hertz, we get a little larger than 0.02 radians of phase noise. And even considering a phase error, and even considering the 7th harmonic generation process for the phase noise scaling, we would still have more than 97% of power remaining in our VOV frequency comp carrier. So in our, then we couple this infrared frequency comp into our enhancement cavity and generate our 7th harmonic inside such an enhancement cavity using a xenon gas target. And here in picture, you can see our generated 7th harmonic on top of, or shining on a fluorescent screen. We recently estimated that we have about 5 nanowatt per frequency comp mode. And in the frequency domain, essentially, we have 10 to the 5 frequency comp modes, which can be all scanned in parallel, which would allow us to cover a very large spectral region with a still very fine spectral resolution. Our nuclear resonance is expected to be about 16 kilohertz in line width, and our frequency comp modes are separated by 75 megahertz as our comp repetition rate. So as we scan the frequency comp modes, if one comp mode is overlapping with the nuclear transition, we can excite the nuclear transition, and in the end, we would be able to directly determine the nuclear transition frequency relying on the frequency comp structure. So we don't need another spectrometer for finding out the exact transition frequency. In our actual experimental scheme, we excite our nuclear state inside a solid state sample. So this is the solid state approach that Lars has introduced to you before. We essentially have a 10 nanometer of thorium oxide electroplated on a stainless steel wafer shown here. As a VOV photon comes in, if it's on resonance with the nuclear transition, it can potentially bring one nuclear, one thorium nuclei to the excited state. And in the excited state, actually, the lifetime of this transition is about 10 microseconds due to the internal conversion decay process. Then it will decay down to ground state and directly transfer its energy to an electron. Now this electron would have enough kinetic energy to fly out from this 10 nanometer thick thorium oxide layer, and would be our spectroscopy signal that we observe. So essentially, in one of our experimental cycle, we would start by irradiating the thorium sample with 50 microsecond laser irradiation time. And during that, we would excite a number of nuclei. Then we turn off our laser abruptly, and then watch for the internal conversion decay of the thorium. So during and we would detect this delayed electron emission in a 10 microsecond detection window. Using this experimental scheme, essentially we would be able to irradiate 10 to the 13 nuclei in parallel, which would greatly enhance our signal level that we can expect. Also, the internal conversion channel actually works in our favor to allow us allowing us to do a faster detection in the detection cycle. And by observing electron signal instead of fluorescent photon or other signals, we can have a very low background. So this allows us to have a high signal to noise ratio in our experiment.
5 minutes.
Thank you. So in our actual detection system pictured here, we have our VOV frequency comp focused down to our target at a 45 degrees incidence angle. It's focused down tightly so that we can use a very small target for background reduction reasons. Essentially, we have a magnetic bottle spectrometer kind of set up using a permanent magnet and a magnetic field coil to generate the magnetic field and guiding the electrons to our detector far away from the target and outside the direct line of sight, also for reducing the background. So our main experimental noise background actually comes from the alpha decay of the thorium-229 sample itself. We measure in the experiment that we have about 200 counts per second background rate. And with the parameters shown here, we have we estimate that we have a signal to noise ratio of about 50 in about 3 hours of scanning time. So with that, I would like to come to the conclusion. In the past 2 talks, you have seen that the great advance in the thorium-229 energy determination. And also, I hope I've convinced you that the past 20 years of VOV frequency comp effort development and also a novel spectroscopy scheme using a thin solid state thorium-229 layer really leads to our direct frequency comp spectroscopy experiment for the thorium-229 nuclear transition for the first time. And in case of success, this can also be directly used for building a thorium-229 based optical clock for the various fundamental science applications as well as precision measurement applications. So with that, I would also like to acknowledge our thorium spectroscopy team in Gila at Professor Junye's group. Lars, you already know, is our great postdoc, very knowledgeable about everything. Jack Doyle recently joined our group as an undergrad student researcher, and that's me over there. So thank you very much for your attention, and any questions?
Okay, that was a wonderful talk. Real tour de force effort to make this interesting wavelength. So as usual, I will request that if you have any comments or questions, that you put an exclamation point in the chat. And before going to our first question, I'll just mention that Jacek has updated the reference that's relevant to this question about the delta VC. So for interested parties, you can have a look at that. But going back to this presentation, Luke, looks like you have the first question. So go ahead and the floor is yours.
Hi, nice talk, thank you. You maybe said something about it and I missed it, but could you talk about how, after you've done your spectroscopy with the comb, how you identify which tooth it is that's excited the nucleus?
Oh, yeah, sorry, I actually didn't explain that in detail because of the time. Oh, on page back. So essentially, we have a very good idea of the frequency comp repetition rate, and this can be measured very precisely. So there is also a thing, there's also the frequency comp carrier offset frequency, which we also know very precisely. So essentially, you can know by one measurement, many like integer combinations, or integer, not combinations, many integer multiples of the frequency count repetition rate can potentially be the nuclear transition frequency. But but the next thing we will do immediately would be changing our frequency count repetition rate to a different value. And by doing multiple measurements, eventually we will be able to constrain the frequency count mode number that is used for exciting this nuclear transition. And that way we know the actual exact frequency of the nuclear transition.
Okay, cool. Thank you. That makes sense.
Okay, we have time for more questions. So if you just put an exclamation point in the chat. So Makoto, the floor is yours.
So on a related question, so when you actually scanning this, you had to scan 75 megahertz window with to catch a 16 kilohertz line. Is that how it works?
Yes, exactly. Mm.
And is that a kind of a normal thing? That, I mean, it seems like a kind of a little bit of effort there, but you're not worried?
What do you mean?
Well, I mean, your resonance line is very narrow compared to the window you had to scan, and you also laser line was one kilohertz.
Yes.
Also. So I mean, does it take a long time to you expect to find the line, or?
That's actually the great advantage of doing a frequency count spectroscopy. So that's a very good question, because so this essentially still takes in our case a few hours of scanning time, but because we have so many frequency count lines, we only need to scan for 75 megahertz. As imagine if one needed to scan this with a CW laser, then one would need to scan like 2-3 nanometers, several nanometers for that. That would be like almost impractical. But yeah, that's a very important question, and we actually do like scan through, like with fine steps through the 75 megahertz gap between the two count modes.
But you expect that scan takes only a few hours?
Yeah, only a few hours.
Okay, thank you. That answers the question. Thank you.
Okay, we have a few more minutes for questions. If anyone else would like to ask, you can just put an exclamation point in the chat. But while we're waiting, I have a question for both of our speakers about this interesting thorium-229. Oh, well, I won't ask my question. Ask me to go ahead.
So I wanted to ask, what is your time scale? When will we have a nuclear clock? I mean, which would be so cool as a probe of all sorts of fun, interesting physics. So are you guys willing to place bets? I'm a theorist, I don't care. You can tell me whatever you want, I'll believe it.
Yeah, so we are currently still tuning up our laser in the lab, and our target has we already have a target in the lab as well. So I would say, I hope in a few months, unless something goes wrong, like me burning the fiber laser or something. And also, as Lars mentioned, there's this other UCLA effort that is starting soon. So I think like within a few months, we will see this transition. Yeah.
That's fantastic. That's amazing.
Yeah, thank you.
Yeah, very cool experiment. Thank you.
Okay, Lars, go ahead.
Let me put another bet here. I say 5 years.
Fine, 5 years is not 30 years. Most of us will still be alive by then, so it's okay.
Okay, so I think let's we're finished with our presentations for this afternoon. So let's thank our speakers again, and we are now going to shortly have some panel discussions. And so I will request the folks at MIT to open up the breakout rooms. And the idea is that the first breakout room will be about science impacts. The second breakout room will be on theoretical developments. The third breakout room will be experimental challenges and facilities. And the fourth breakout room will be on community building. And the remaining rooms can be used for discussions if you for other discussions. And then I think aside from that, that'll sort of I think we'll end at 5:10. So yeah. So and Ronald, if you have any other announcements, I'll hand the floor over to you.
No, I think that's it. So just to say that this is the people that is coordinating this panel, but so we'll invite all of you if you are interested. So the idea is please join different panels. Don't feel that you only will join one panel. So I will encourage you to jump between different panels. I think it's very important to collect ideas. So at the end, we would like to write a kind of white paper. Nick, would you like to say a few words that you are coordinating it?
Yeah, for sure. So like Ronald said, we would like to write a white paper. This is something that is a topic of discussion for panel 4, community building. We have a rough idea based on discussions in previous groups and panels, what sort of content we want in there. But one of the big questions is, should we write it as part of one of these like programs or efforts like SNOMAS or the long range plan, like the nuclear science long range plan, or if there are similar like European counterparts to these things that we could try to take advantage of, with the idea being, well, it's sort of one centralized place. We can collect all of these like really interesting ideas we've heard about, but also maybe to try to increase greater community support and attract other people and resources to this area. So that's something that you can hop into breakout room 4 if you want to talk more about that. And we will also talk about it at the panel discussion on Friday, tomorrow.
Right. Yeah. And all ideas from the different panels will go to that. Although panel 4 is coordinating this effort, the idea is that different panels will also collect the ideas. Okay. I think we can just go to the breakout rooms. So panel 1, room 1, 2, and so on. Let me stop sharing.
Hey, Robert, are you guys all set? Oh, sorry, you're muted.
Sorry, no, I'm no longer muted. Okay, yeah, wonderful. We are all set. Work very well. Thank you very much for staying tuned. And yeah, then I will be gone as well, right? See you.
All right, sounds good. Have a good one.
Bye.
See you tomorrow.